away from the Anatolian coast. Although the island has been inhabited since the Paleolithic times and has a dense web of prehistoric sites, and you can see that on the map, Thermi, which you can spot with a blue dot, is located on the eastern coast of the island. And it is the only prehistoric site to have been systematically investigated so far. Thermi was excavated on behalf of the British School at Athens by Winifred Lamb between 1930 and 1933. And the results published a bit afterwards in an exemplary volume in 1936, which you see on the slide. And these excavations revealed 5 main successive construction phases, which are dated to the early Bronze Age, and they are known as Town 1 until to 5, and you can see this on this table. And today, only a small part of these phases are visible, and because Lamb's excavations were backfilled. Similarly to other synchronous sites in the Eastern Aegean, like Polyochnion Limnos, Thermi exemplifies one of the earliest examples of urbanization in the Mediterranean, with centralized planning and communal organization, craft specialization, social stratification, and distant exchanges from the beginning of the 3rd millennium BC. And because of close similarities with the material culture with the Anatolian coast, Thermi has been characterized as an outpost of Anatolian migrants. And let's now look at the architectural phases that produced the rich ceramic assemblage that I analyzed, so that we understand the transformations over time. So starting from the earliest phase, Thermi was founded around 3200 BC on the natural rock as a small town with an organized pericentric layout and without a fortification wall. The next phase documents the introduction of an enclosure formed by the house outer walls, while the following phases have an arrangement with a more systematic protection of the central part of the settlement. Major changes appear in Thermi 4, during which a new settlement layout and orientation of the buildings emerges, and is now protected by a defensive wall. A more refined settlement organization and stronger defensive wall appears in the final phase, which is Thermi 5, with evidence for gates, bastions, a linear town planning, and a central road. And I hope you can see that on the right side of this slide. After that, the site is largely abandoned and is repopulated in the Middle Bronze Age period. Similarly to architectural changes, ceramic production at Thermi shows remarkable transformations across different phases. The classification of the pottery assemblage was organized by the excavator into 3 main categories or classes, and here you can see the 3 classes that I will talk about. The first one, class A, corresponds to phases 1 and 2 and consists of black burnished wares, and is used for the manufacture of bowls of various types, pyxides, jugs, cups, lids, and then we also have these red coarse wares that you see on the bottom of the first column, which consists of tripod cooking pots. Class B corresponds to phases 3 and 4A and documents the appearance of new shapes like bowl types, globular jars, pithoi, and cooking pots, which continue unchanged from the previous phase. An important difference from Class A is that the surface of Class B is now brown burnished or mottled. Finally, Class C corresponds to phases 4B and 5, and pots have brown to grayish brown surfaces and new shapes like shallow plates, 2-handle cups, winged jars, and colored transport jars appear. But beyond the characterization of the local ceramic production, a number of suspected imports were recognized morphostylistically, and you can see them on the right part of the slide. And these pottery imports were also found together with metal and stone artifacts from the Cyclades and other regions, which both testify to the external contacts of Thermi. And that's what we knew so far about Thermi through the publications. So in order to test the variability and changes in patterns of ceramic production and consumption and circulation at Thermi, I selected 72 samples to analyze with a combination of contextual, typological, and chronological criteria. Thin section petrography was used for the analysis of both pottery and raw material samples, so clays mostly, to characterize composition, reconstruct technological practice, and suggest provenance. A subset of these samples is planned to be analyzed by WDXRF to test the intragroup variability, but today I will focus on petrography. The raw materials prospection resulted in the analysis by petrographic means of clay and sand samples that I collected from several locations along the east coast of Lesbos that represent different geological formations, but also rock samples collected from lava formations. Selected clay briquettes were prepared and fired at 2 different temperatures in 700 and 900 degrees Celsius. And then I compared these to pottery to test the ceramic fabric variability. This variability was first examined macroscopically, and at least 3 main macrofabric categories could be distinguished with a USB digital microscope. One, with distinctive black glassy inclusions corresponding to probably lava rock formations. One with elongate fibrous green rocks, preliminarily identified as metamorphic rocks, and one with felsic-rich white transparent inclusions. So based on the variability that I presented morphostylistically, but also in terms of the macroscopic fabric, the petrographic analysis of samples resulted in the following fabrics. Fabric 1 is a heterogeneous group that relates to the mixed lithology of the ultramafic geological formation and the sub-ophiolitic melange that outcrop in the vicinity or maybe close to Thermi. Main non-plastic inclusions comprise ultramafic minerals like epidotes, pyroxenes, and others. I'm not going to bore you with details on this. And the location of Thermi in proximity to different formations like the ultramafic unit and the sub-ophiolites could probably explain the presence of a combination of rocks in this fabric, which was also supported by the matching clays collected from the area. And I hope you can see this on the right part of the slide. You can see the clay thin sections, so the fabric from the clays that I collected. And if you compare them, I think you can see how similar they are. And this was an indication that about the provenance, the geological provenance of fabric 1. And fabric 1 was used mostly for the manufacture of bowls in the first phases, and then there is a change because they use the same fabric for the manufacture of storage vessels. A similar fabric has been identified that it's kind of similar to fabric 1, but it also includes different rocks and calcite fragments, and it's used exclusively for the manufacture of jars and jugs. Then fabric 2 is the largest clay recipe that I identified, and is very consistent for the manufacture of black burnished tableware vessels that you can see here for phases 1 and 2. And it is characterized by pyroclastic rocks like ignimbrites and welded tuffs, and its provenance is most likely in central Lesbos and the Polychnidos and Skopelos ignimbrites. This observation about the geological provenance was also confirmed by a clay sample that I collected, and here you can see how similar they are. And this is the potential area of provenance of this fabric, which is quite far from the site. Fabric 3 is characterized by intermediate and acidic volcanic phenocrysts and lava fragments and their dissociated minerals, and suggests a distinct clay source than fabric 2, and more specifically in small volcanic outcrops. This fabric is used during phases 4 and 5 for the manufacture of brownware storage vessels. Now, a completely different series of fabrics, which are designated as fabrics 4, 5, and 6, are geologically related with the schist and marble unit and the sedimentary deposits in the vicinity of Thermi. More particularly, fabric 4 is characterized as sun-tempered and contains a range of well-rounded metamorphic fragments that correlate well with sand samples from the area. And here you can see again the similarity between the raw materials with the clays. Fabric 5 and its variants are compositionally similar with the metamorphic content of Fabric 5 and of Fabric 4, and is used for the manufacture of brownware jugs. And finally, Fabric 6 is also compatible with the provenance in the sand deposits of Southeast Lesbos. So in this study, beyond analyzing the local production at Thermi and identifying the raw material sourcing strategies, we have also uncovered preliminary evidence of external connections. We have identified fabrics from at least 6 distinct off-island sources, mostly closed vessels, and these imports suggest connections with the Cyclades and other nearby regions. For example, a granitic fabric likely originates from Naxos, while 2 metamorphic fabrics point to the Western Cyclades. I will now summarize the main findings of this study, which demonstrate Thermi's active role in both regional and broader developments. So we have identified 4 main lithological categories of raw materials used at Thermi, which show the active role of different groups of potters in raw material exploitation and procurement strategies. The different sources are aligned with Eastern Lesbos' complex geological landscape. These materials suggest distinct production areas or workshops across the island, corresponding to various geological formations, as I have shown. In terms of clay processing, the potters generally use unrefined natural clays with some fabrics, like the metamorphic ones, tempered with sand. Chronological and functional correlations were also noted. For example, Fabric 1 was used consistently across time, while other fabrics like Fabric 2 was specific to early phases, primarily for tableware vessels. Fabric 3 was used for storage jars in later phases. In terms of forming techniques, the pottery was hand-built, showing evidence of coiling, slab building, and pinching, with differences likely reflecting, again, different potting traditions or communities of practice within the settlement. Aside from the main clay recipes used diachronically and synchronically at the site, a number of loaners have also been identified at Thermi, and the so far petrographic data suggests the importation of closed ceramic vessels during phases 1, 2, and 3, with just a single example in phase 4. Although more analytical work should clarify the question of geographical provenance, we can preliminarily identify connections with several Cycladic islands, other Eastern Aegean islands like Chios, and perhaps also Western Anatolia. Finally, I want to emphasize the value of reanalyzing old material from legacy excavations, as it has the potential to provide a more detailed view of technical choices by the potters, information that might have been overlooked on a typological and stylistic level. And with this, I want to finish my presentation and thank again all funding sources like the University of Cyprus, the British School at Athens, and of course the Aristeas grant, which allowed me to undertake this research. And thank you all for your attention.
Thank you very much for this very systematic and interesting approach to the old excavated finds from Lesbos. Are there any questions? Please, on Dr. Menelaos.
Maybe it's too early.
No, everything was clear? Yes, please.
Thank you. So much work on
there is some work, and I think we can ask our colleagues just sitting behind you. They've done quite some work in the Meander Valley, mostly, the Meander River Valley. Yeah, yeah, there is some work, but I don't know how this can be compared to the islands. Yeah, sorry. So what's the question?
You mentioned the possibility that some of the ceramics.
Yeah. But I said, I mean, I'm suggesting this because I've seen actual ceramic fabrics from sites in Western Anatolia, because we have a database at the Fitch Lab with analyzed pots. So I'm not suggesting this through through clays, but through ceramic fabrics.
Okay, thanks a lot.
Yeah, thank you.
I have a question.
Yeah.
You identified many supply sources for the raw materials, and I was wondering if this choice that they made was based on the technology that they want to realize, or the type of pot, or other reason. Just wondering if you have an explanation for that, why they change so much to the supply source in. Okay, it's a long time, but
Yeah,
find an explanation.
I'm thinking about this, yes, but I haven't reached a conclusion yet about this. If it relates to technical reasons, or if it's tradition, or because at some point at the settlement there's an overlap. Yes, we have these clear-cut fabrics. Let's say fabric one is used mostly for the early phases, and black burnished one, so you can see it's clear. It's very different from the later ones. But then it also continues. Yeah, that fabric continues also a bit later, and in phase 3, and then this is when fabric, I don't remember now which one starts. So there is some kind of an overlap. So I think it relates more to the existence of groups, of different groups of people exploiting different sources, because they make the same pots more or less. There's similar shapes. So I don't think it's a technical reason behind this. Maybe for the achievement of the surface treatment, but that also relates to firing. And then, yeah, not sure. I have to develop this more. I don't know. Yeah, thank you.
Any other questions? Okay, I think we can move forward to the next.
Thank you.
So the second talk for today is by Dr. Sarkar Boyadzis and Zaharias, Pottery Manufacturing Strategies at the Market Town of Bagastra, India, Indus Valley Civilization, a detailed case study. See.
Hello, not a doctor yet. Good morning, everyone. My topic for today is pottery manufacturing strategies at the market town of Bagasra, Gujarat, Indus Valley Civilization. So let me take you on a journey to the east. I'm going to start with a very brief background. So Indus Valley Civilization, as some of you might know, is one of the earliest civilizations of the world, along with those in Mesopotamia, Egypt, Greece, and China. And the territory that Indus Valley has is twice the size of Mesopotamia. So the region that it has is massive, which brings it to have lots of regional variations taking place in the Indus Valley civilization. And the Indus Valley civilization is chronologically divided into 3 phases if you do not consider the antecedent phases. And the stages are called regionalization era, followed by integration era, and finally localization era. And each of these phases were further subdivided into different subphases. For example, the integration era was divided into early urban, urban, and post-urban. And this year also marks the century of the discovery of Indus Valley civilization. Just a little bit more background, because there is just so many different regions with different personalities and all of that. Because I cannot talk about all the different regions, I'm just going to focus on the region that my site is based on. So my site is in Gujarat, and Gujarat was important to the Indus people primarily because of 2 reasons. One was because of the big coastline that it had, which facilitated lots of trade activities with the Mesopotamian and Egyptians, but also because it had lots of raw material sources, such as for semi-precious stones, such as carnelian agate, And these were used to produce and transport and trade it with other regions inside of Indus Valley as well as outside. And additionally, there were numerous different, along with the Indus Valley civilization, there were different contemporary cultures which coexisted with it. Some of them are Sorat Harappan culture, Anartha culture, among others. And these are some examples of the pottery that was present during that time. Now, finally, I'm going to talk about my site. Um, and so my site is Bagarsara, which is, as you can see, with the arrow marked. The excavations result showed that there were 3 phases at the site. The first phase is known as pre-fortification because that was when a group of classical Harappans migrated to the site, which was followed by phase 2, which was fortification, where the fortification wall was built, and the settlement was divided into 2 different parts. So there was a group of people living inside, and there was a group of people living outside. And then finally, the third phase, where the site and the settlement kind of started declining, which was followed by abandonment of the site. And finally, the another group of population moved in and at a much later date. So the site is interesting because it has lots of different evidence of production. One of that is shell bangle production, which they found heaps and heaps of raw, rough cutted shell, so that was used to produce shell bangles. Another thing that they found was evidence of fanes manufacturing. Another was raw and uncut stone bead, and other evidences were that of copper production, but there was no exact evidence that was found. But we didn't find a kiln or a pot, but we did find inglots. And other evidence of trade was black slip jar, and those are the classical Harappan steatite seals. Finally, the aims and objectives of my study is to investigate the pottery production strategies at the site. Second is to explore the relation between different production strategies and if it varied, because there are lots of different parameters that I'm interested in looking at, so such as if it varied with culture, because there are 3 different cultures which were present at the site, such as Anartha, Classical Harappan, and Sorat Harappan during 3 different phases. And finally, the comparison between if it varied inside the wall and outside the wall. And to see and understand the role of these market towns, because not much is understood about that, and to also understand if there was any kind of standardization, because it is widely taught in India, at least, that there was high degree of standardization of the classical Harappan pottery, which I would like to study. So for this, I chose 73 samples from the 3 phases, which were roughly 20 from each phase. And as you can see, it kind of nicely also, the distribution kind of nicely shows us the decrease in classical Harappan and increase of the Sorat Harappan culture, which came in the phase 3. And for this, I've used lead and XRF to understand the clay paste. I've used SEM EDAs to understand the surface decoration, if there was any. And finally, used SEM EDS, FTIR, and FTIR and XRD to understand the firing temperature. I'm going to duplicate the production stages of pottery and discuss that. So firstly, preparing the clay. Looking at the plot over here, it kind of shows that there were 3 different clusters of the clay paste. The first clay was rich in silica or quartz, and the second cluster was a more balanced mixture of clay. And finally, the third, which was more aluminium slightly, it was still well balanced, but it had a higher ratio of aluminium in it. And finally, some of the outliers, and I also found some crogs which would give you slightly different um, ratios. The other tempering material, let's say, was calcite, and uh, this kind of shows, and there was an inverse relation between calcite and silica. So as calcite was added, or calcareous clay was added into the clay, which was silica rich mostly, there was a decrease in the total amount of quartz or silica rich clay. There was also evidence of organic temper, and there were two kinds of organic temper. One was where they used seeds, and the other was using chaff to increase porosity. And it kind of varied through the different phases. As you can see, the first phase and the third phase kind of had more where they used seeds, while in the second phase there was not much the use of seeds, but more of chaff. Now I'm going to complicate things just a little bit and try and put it in a ternary plot to understand the different clusters and the production strategies, or the rationale behind using the different clay pastes. So the first group on the top is again silica rich clay, which kind of gave the pots some kind of thermal stability and less shrinkage, whereas the group in the red was more rich in calcite, so that kind of worked as a flux, but also helped and strengthened the vessels, whereas the group in the middle in purple was more of a mixed clay paste. And finally, the group on the right was a group of outliers. I presume this was mostly from a different source. Now, seeing the clay paste in relation to the culture, we can see that the pre-fortification and fortification layers, there was the pottery production strategies was relatively similar throughout the three stages. However, the group of outliers on the right, which is highlighted with the green circle, only consists of classical Harappan, whereas all the other has the Anartha and Sorat Harappans are seen in the three other groups. When we try and understand it through the different phases, we see a similar pattern. However, interestingly, we can only see the third cluster, which is in green, again in only the first two phases, and it kind of disappears in the third phase, which is interesting, which could also relate to a disappearance or a close down or of some kind of link between that source or that group of people that this site or settlement kind of had the samples from, the vessels from, sorry. And when we try and understand the clay paste in relation to the shape of the vessels, there is very little usage of specific recipes for specific vessels. So for example, the red goblets usually had a similar pottery production strategy where they used calcite to enhance the strength of the vessel, whereas groups of cooking pots or serving vessels had high silica content, whereas the small medium pots were all scattered throughout the different strategies. Now, a little bit about the shape. This is a beautiful example. They were all wheel made. This is a beautiful example of when a fabric is used to cut the pot, which gives us a glimpse into also the fabric that was used for the clay, for shaping and decoration. And these two other examples are also of shaping, which tells us with the help of carenation marks that there was they were produced with the help of a wheel. And then I used SEM to understand if there was the presence of any slip, and the slip was present in 3 samples, and this was determined with the help of understanding the ratio of the clay paste, the clay body with the surface. Now, finally, because no pot is complete without firing. I'm going to talk a little bit about firing. So firing for a few samples, for this example, we use SEM, and because of the platy and absence of glassy filament structure, we can see that the firing state, not much fire was done to the samples. Similarly, when we see the XRD diffractogram of the two samples, which is 41 and 61, with the help of the presence of muscovite and high amounts of calcite as well as albite, we can say that these were fired in a lower range because muscovite and albite start to disappear around the range of 800. And finally, the FTIR peaks. The FTIR spectra shows similar results where we see primary calcite on the first peaks at 1425, which is characteristic, which is followed by the SIO bands and other peaks, which all suggest a firing range between 600 to 800, and other samples which had the same firing range were 17, 24, 29, and 74. There were some samples which were fired between 800 to 900, and this was on the basis of the evidence of very isolated pores, bloating pores present in the sample. Additionally, we can see that the amount of albite and muscovite is less compared to the other previous samples. And finally, with the evidence of recalcination of the calcite in the samples, we can recalcination is basically when the firing of the pottery happens, and then after the clay decomposes, there's a range between 800 to 900 before it reaches and forms higher silicate phases, and this is if it's not fired enough to produce the high temperature silicate phases, the calcite in the sample recrystallizes and reforms. And this can be only one of the best things about using FTIR is that it shows you the recalcination of the peaks. So this is a secondary calcite, and the peaks are characteristic at 1450, around within the range of 1430 to 1450. And lastly, some samples were fired within a range of 900 to 1000, with the evidence of fine bloating pores which were throughout the vessel, slightly glassy phase. Additionally, there were presence of galenite in the XRD data and diffractogram, as well as one sample also potentially showed evidence of moonlight, which I'm not 100% sure about, but yes. And looking at the FTIR wavelength, we found that because when you fire the ceramics, the peaks in FTIR, as they gradually increase, it kind of disorders and broadens. So this is evident in the large SI silicate phases peak over there between, and this suggests evidence of firing around 900 to 1000 degrees. And other samples which were fired around the same range were 31 and 48. Finally, the conclusions. Pottery production strategies throughout were the first settlers. We do not know exactly where the first settlers migrated from, but this investigation clearly shows that they were well versed in the art of producing pottery. For example, they mixed calcite-rich clay for producing strong vessels such as goblets and storage jars, used organic temper to increase porosity and lower firing temperature, and used quartz or coarse utilitarian vessels such as cooking pots, and used quartz for that. And while they used a mixed balanced clay paste for all the other vessels, and all of this suggests some degree of standardization. However, pottery from other sites need to be studied to get a more detailed understanding of what was actually happening. And 4 groups are present in the phases 1 and 2. However, during the third phase, it kind of disappears. So this is again correlates possibly to the emergence of Sorat Harappans and collapse and slight decline of the classical Harappans present at the site. Or another interesting thing would be to try and figure out how it was affected by the 4.2 Ka climatic change event, which is also one of the reasons that kind of led to the decline of the classical Harappan or the Indus Valley civilization. And we do not completely understand how the market towns played the role in the ethos of Indus Valley civilization, but this kind of sheds a little light on what was happening. Yes, thank you.
Thank you. Would you have any questions for Sid's presentation? No? May I ask you?
Yes.
Could you please elaborate a little bit on these outside the fortification and inside the fortification productions? I mean, why this is so important in this culture?
So this was a typical settlement plan which emerged in the classical Harappan and urban phases, where there was division between two groups of people, and it is believed that in general that a different class of people lived inside the fortification wall compared to outside. The kind of structures, the kind of houses, all of that was different in comparison when we consider inside and outside the fortification wall. The food was different inside and outside as well. And this all kind of suggests a different class of people living inside and outside of the wall. But on this site, there was all the craft producing and manufacturing activities were happening inside the fortification wall. And none of it was happening outside with the exception of pottery production kilns. So it is interesting because it kind of possibly shows that the group of people believed that these production strategies needed to be fortified. So there were possibly also other kinds of people with higher status living inside, which is why I was interested in trying to understand what was happening. As well as when I was going through the whole assemblage, there were more coarser ceramics outside the fortification wall and compared to inside the fortification wall. Yes.
Thank you. Any other questions? Okay, let's give Sid another
Thank you.
round of applause.
So the next presentation is on I-type pottery from Bogaskoya Tusha. You can rate my pronunciation from 0 to 10. Okay. The authors want to understand production through petrographic and chemical analysis. The study is by Mustafa Kibaroglu, Milke, and Shishman Tukel.
Yes.
More or less. So please.
Okay, perfect. So good morning, everybody. We are coming back to Eastern Mediterranean. I will talk about the Hittite pottery. And so first I will give a very, very brief introduction about the Hittite pottery. I'm sure most of archaeologists know Hittite pottery, or Hittite, of course, and the samples that we have selected for our archaeometric analysis and the methods, and I will present the results and finally the conclusion of our results. So, as you know, Hittite was one of the main power in Eastern Mediterranean, and as you see here, so sorry. And of course, this civilization has a very typical pottery tradition. And this pottery tradition generally, also based on archaeological studies, classified in 3 main groups. The first one is, can you hear me? It's okay. So first group is plain ware, which defined actually a common ware and it's a simple ware, and this is undecorated, and there is a lot of shapes of this simple ware, and the plainware produced in very large amount and in all Hittite territorial area. And there is very different forms, depend on the function. We have very different plainware. And we have here red lustrous ware, actually two different decorated ware. One is very typical red lustrous, red slipware, pardon, not red lustrous, red slipware. It's less common. It's not very common like plainware, and obviously it's produced for in a very specialized production because of surface decoration. And some archaeologists related this ware type for some, yes, associated with elite groups or some ceremonial context. Same is also for white ware, white slipware. And typical characteristic of Hittite pottery is the uniformity of the forms. So you can find, this is general forms, you can find the same forms in Hattusha or in other Hittite settlements. The question is why it is so. There is main factors which obviously played a main role to uniform to this Hittite pottery types. But generally, it's accepted that the pottery type is rooted in pre-Hittite Anatolian tradition. But there is, in terms of during the state development, there is some key factors which relate to this uniformity with typical Hittite pottery. Some are, for example, technological innovation, use of, for example, fast potter's well, and introduction of two-chambered kilns. But in this context, obviously, the centralized workshops, which is controlled most probably by Hittite administration, also played a main role in a homogenization of this form typology. So this led to the large production and uniformity. So to understand this Hittite production, we started a new project. Actually, it's not really new, but it's going on. Founded by German Research Foundation. Our main aim was to understand the production and distribution of Hittite pottery using archaeometric analysis. We include 5 important Hittite sites, of course, Hattusha and Uşaklı and Ortaköy. And this is, I think, just a minute. Yeah, Maşatöyük and Oymaağaç. So our aim is to understand general production mode. So in this talk, I will present the results from Hattusha. Our aim is actually is very simple. First, to characterize the material and the provenance and some information about the production technique. For this aim, we collected representative samples, plainware samples, which include coarse, middle, and fine, and red slipware and white slipware, which compose of very from different ware types. We include also clay samples from the research area. This is Hittite, this is Hattusha, and 29 clay samples from this area. We considered also, of course, the geological surface geology of this area, which is we have here a large area ophiolite or ophiolitic melange. We have peridotite and serpentinite and volcanic rocks, and here we have young deposits. And in this area, it's interesting. I will talk about this here. It's totally different. Mainly consists of surface geology is composed of volcanic rocks, and we collected clay samples from uncontaminated surface. And we we analyzed this both ceramic and clay samples using petrographic or standard methods. And chemical analysis, we applied laser ablation ICP-MS. Prior to analyze, we prepared very homogeneous, ultra-fine, so-called press pellets, as it's not in situ analysis, to obtain a very high quality chemical data. So this is the results of petrographic analysis. If you look at this thin section images, and you see very different, very heterogeneous fabrics. And we have also inclusions, which is large inclusions, and also very fine fabrics. And we have identified 5 petrographic group, and we have here 8 different fabrics which present only one samples. So we have here very heterogeneous group. And first group, petrographic group, is characterized by large inclusions of fine-grained metamorphic rocks, but we have also serpentinite, chert, limestone, and volcanic rocks, which most probably come from ophiolitic rocks. And here we have also mainly inclusions which most probably come from ophiolite, but we have no, for example, or very less few fine-grained metamorphic rocks, slate or phyllite. And third and fourth groups is more or less similar. We have here some inclusions, for example, serpentinite or like this, but in addition, we have here sandstone. Therefore, I divided this group in separate groups. And here we have, in addition, some carbonite, and matrix is also more carbonate rich. And in fabric group is a total different. So we have here no serpentinite, nothing, and only muscovite and shell fragment as feldspar. And this is this so-called individual groups. As you see here, we have here very in situ clay. For example, this is most probably from volcanic rocks. This one also, this one. And there's another group which is quite different. And chemical analysis of these samples show not really very clear match to our petrographic data, but there's some similarity. So we have very scattered pattern, and only if you, this red one, this is petrographic group 1, which is rich in fine-grained metamorphic rock. So there is some difference, but not really clear. Even also is individual clays, fabrics show some difference, but it's not really clear pattern. So if I try to combine both results, petrographic and chemical results, and to establish or to create so-called archeometric groups. So we have here 5 different archeometric groups, which also there's some future subgroups. And if we compare this archeometric group with type and form groups, and for example, first group, it include, of course, mainly coarse plain ware, but also a middle plain ware, and in other groups, the red slip ware. Okay, okay. So there is no any correlation between fabric groups or archeometric groups and forms or ware types. Okay, the provenance, the main question. I will talk very fast. So the first group is, which is include these fine-grained metamorphic rocks. We have clay samples from this area around 7 or 10 kilometers. We have, this is phyllite, and we have clay samples from this area. It's very similar, also in chemical analysis. So we can assign this raw material area of these fabric groups to this area. And the second and third groups is different, mainly come from or contain serpentinite and ophiolitic rock fragments. And we have here clay samples. These are from this area, so we can assign both group to this area, but we have, of course, different processing of clay raw materials. So the group 4 and 5 is some difficult group 4 maybe it's not really from this area, but maybe somewhere in this area. But Archimetric group, which is composed of consists of a white slipware, is totally different. As you see, it's also different in chemical composition. So I mean, this is okay. The individual groups can be assigned some of this group to distinct area, especially there is in this area which we, I said, there is a large area of volcanic rocks and clay samples or clay deposits which come from volcanic materials. Okay, so this is also individual groups. There is also not really overlapping. So in conclusion, we find out that the majority of pottery produced was local material in Hattusha, also included plainware and also red slipware. They use multiple local clay sources with varying properties as of coarse and also purified clay samples. Clay materials has been also purified. And there is also no strict preferences for specific clays for particular forms or ware groups. And there is one exception, it's called large plate, it's up to 80 centimeter. Obviously, the potters used a very specific clay, which is this petrographic group 1, for the production of large plates. And if we look at or compare the plainware and red slipware, there is no really differences between both ware type. So in terms of material characteristic, only the differences is surface decoration because of maybe for special use, and white slipwares and both is also red slipware is also local production, and white slipware is something different. It's not local, and the clay is also different. So most probably is import or not. We say now a non-local production. And this show also that Hattusha was involved in exchange network. And in terms of production technique, we could obtain some information. For example, we know also that in all samples or materials was manufactured in oxidized atmosphere. And we have different procurement strategy and use of coarse clays on purification, and firing temperature is around maybe 7,000 or 8,000, but we will make some mineralogic analysis, for example, XRD. So interesting result is for us is that this uniformity of the form is not really related to unified production process. So it's more complex than we thought. And in next step, we will analyze samples from other sites, and we will compare all results, and we'll try to obtain a general or comprehensive understanding of the Hittite ceramic tradition. So thank you very much for listening. Sorry that I have to.
Thank you very much for this presentation on very interesting pottery and sites, also all the correlation. Are there any questions, comments from the audience? Any? Microphone? Please. Yeah, otherwise they don't listen to you.
Thank you. Thank you very much for your very interesting talk. Since Bukoskoy is the Hittite capital, might you predict, sorry, this is a bit of an unfair question because I know you're going to
maybe louder, I cannot understand everything.
Oh, forgive me. So, since Bukoskoy is the Hittite capital, do you think that ceramic production there might be organized in a somewhat different way from other smaller, less important settlements in the Hittite area?
I mean, this is also one of main aim of our project. So we will see. I mean, we have some information, for example, now from Ortaköy. So obviously, it's not really complex like in Hattusha. So we observe, based on our analysis, the production of pottery production in Hattusha was complex. So it's not, I mean, we have very unified, very forms, but the complex means the procurement is very complex. Obviously, not only local material, but they also have some clay deposits from very far from, I mean, maybe 10 or more than 10 kilometers far from Hattusha. But in Ortaköy, we observe now, it's very preliminary results, it's more homogeneous. So they use most probably one main clay deposit, but they use tempering. So to produce, for example, coarse plain ware like this. And yeah, it seems not really so complex like in Hattusha. Yeah.
Thank you.
You're welcome.
I'll go for one, if you don't mind. It's on method, because you said you analyzed the chemical analysis were made by laser ablation.
Yes.
So my first question is how big it was, the spot analysis, and the second question is, given the capability of laser ablation to analyze especially the tracer elements, did you find any clue for provenance on those parts of the?
Sorry, it's
because given the capability of
Yes.
laser ablation to analyze especially trace elements, okay, did you find any clue or any information, additional information that can help you distinguishing the provenance of this material based on trace elements?
Yeah, first question is
So the first one was the spot.
yes, spot analysis. So it's laser ablation is this spot analysis, but you can also make some line analysis. So to increase the results, it's not only one spot. We measure 5 different spots, and all result signals compare, and yes, and then we have results. If you are not really sure, then you should maybe use this line techniques. But to obtain very good quality or high quality data, I try to homogenize the powder. So also in that condition, and then you have really very fine, I mean, the main problem is this matrix effect by laser ablation, and to correlate to minimize this disadvantage. And of course you can analyze more than maybe 40 trace elements, including rare earth elements, which is very useful. And in our case, I can also measure elements. So it's not really like XRF, but according to normalization methods, which is used especially in obsidian analysis, it's possible. And we have also some experiment which our measured element is true compared to XRF, for example. And the main advantage is that you have it's a very high, very large element, and with high precision. So it's therefore it's a powerful method, I would say. Welcome.
Anybody else? So thank you very much again.
You're welcome. Thanks.
On now to the characterization of donor ceramics, multi-technique analysis and historical implications by Dr. Biscotti, Manelli, Magnore, and Gianosa. Please.
Thank you. Good morning. This study deals with ceramic glass produced in all the Apulia areas, Daunia, Peucetia, and Messatia, from the Iron Age until the beginning of the Hellenistic period, and we focused on Daunia. Between the end of the 10th century and the beginning of the 7th century BCE, the Apyge geometric became widespread. And these ceramics were influenced from Mycenaean and Greek geometric, and Yapyge geometric pottery have been divided into two classes according to the period of production. The oldest one called proto-geometric, and the more recent called geometric. These potteries are characterized by a primitive geometric repertoire, and decoration are mainly simple lines, lines alternating with dots, or zigzag lines. The extensive diffusion of Yapyge proto-geometric and geometric pottery throughout Apulia inspired later a new Daunian class called subgeometric. Over the course of 4 centuries, Daunian ceramics underwent various influences that led to change in decoration with foreign formal and decorative elements. And from the beginning of the 7th century, the production of subgeometric Daunian ceramics began. These potteries are divided into 3 phases. Subgeometric one is the richest phase. The pottery was modeled by wheel, the decoration was made by a single color, brownish black. Then in the subgeometric 2, the most characteristic phase of the periods, the entire indigenous production was distributed. This pottery is derived from the previous phase for the modeling techniques, always by wheel. And these latter features highlight stylized geometric and zoomorphic pattern with monochrome and dichromatic colors, such as black, brown, and bright red or wine red tending towards purple. Finally, the subgeometric 3 is characterized by an impoverishment in quality, and there was an unexpected return to monochrome at the expense of bichromy. There are some cases with 2 colors decoration, but always with black alternating with brown without red color. Concerning the decorations, the new plant patterns were introduced. So the aim of this work is to characterize the ceramic bodies and surfaces of this ceramic class from 2 archaeological sites in Daunia, Ordona and Canne della Battaglia. The information acquired contributes to a larger ongoing research project on ceramics in Apulia from prehistory to the Middle Ages, and will help to identify the raw materials and the manufacturing techniques used. So in order to obtain complete characterization of the finds, an integrated approach of analytical technique was chosen, exploiting the strength of the various techniques and overcoming the limitations imposed by the uniqueness and the preciousness of samples. The provenance of an artifact can be assessed as the chemical composition of a finished product is linked to the composition of its raw materials. It's therefore possible to distinguish between objects produced in different geographical areas based on chemical parameters such as composition. A joint analysis of the mineralogical composition highlighting the presence of particular crystalline phases can support the results obtained by chemical analysis. So to explore the elemental chemical composition of ceramic bodies, LAICPMS analyses were conducted on the samples, and the data obtained were subjected to a multivariate statistical treatment. Then, to evaluate the production technologies, the samples were subjected to SEM-ADS analysis. And finally, Raman investigations were conducted on the surfaces of the samples to identify the pigment used for decorations. So multivariated statistical analysis of ceramic bodies shows two clearly distinct clusters, grouping the samples according to their discovery sites. Differences between the samples belonging to two clusters can also be seen in the mineralogical composition. The samples from Ordona sites have less micaceous and much richer in K feldspar ceramic body than those from Canne. And within the clusters relating to the Canne della Battaglia samples, a further subdivision can be noted. The samples that deviate from the main group are those that archaeologists have classified as geometric. In fact, the ceramic bodies of these subcluster are more refined than those classified as proto and subgeometric. They have a silty grain size tending towards sandy, and good degree of isorientation of micas and pores, indicating greater care in production process. In all the samples from both sites, the degree of sintering is not so high, indicating not very high firing temperatures or not sufficiently long firing times. Red, black, and brown decoration with not very cohesive and poorly vitrified structure are present on the surface of the samples. The surface of the artifacts belonging just to the geometric group before being decorated were covered with a layer of a lighter color than the ceramic body. Its presence was identified on the basis of its different composition compared to the ceramic body. And based on the composition, it's reasonable to assume that the coating on the surface was obtained by adding a bone powder to a clay matrix, as suggested by the presence of hydroxyapatite highlighted by Raman analysis. SEM and EDS analysis show the presence of iron on red decorated surfaces. And the Raman spectra attribute this iron to hematite, showing its characteristic signals. For black pigments, SEM EDS shows the presence again of iron, but also of manganese. Raman spectra attribute this iron again to its oxides, so hematite, magnetite, and goethite, and it identified also amorphous carbon. The identification of manganese oxides and oxides hydroxides by Raman spectroscopy is extremely complex, so it was decided to use the term manganese oxides hydroxides. As regards the brown pigments, the Raman investigation identified the same compounds identified for black, with the exception of carbon. The morphological characteristics and chemical composition of the identified pigment are compatible with use of terre rosse, that is a continental sedimentary deposit commonly found in Apulia. Their mineralogical composition mainly include partially crystalline iron and aluminum oxides and hydroxides, clay minerals, quartz, feldspar, mica, and so on. So it's reasonable to think that the only terre rosse were used in order to obtain red color, that they added to terre rosse just manganese in order to obtain brown, and manganese and carbon to obtain black. Finally, it's interesting, I highlight the presence of sulfur in all pigments and its absence in corresponding ceramic body. This presence can be attributed to pyrite, typically presents in additional phases in ferrous deposits. So the results obtained have highlighted a difference in raw material used to produce the vases in the two sites of Ordona and Canne della Battaglia. And given the homogeneity of the characteristics, the Ordona samples, it's possible to hypothesize that the production technology remained unchanged throughout the production period, while the differentiation highlighted in the Canne della Battaglia samples would lead to think that the production technology became more refined in the geometric period and began to lose quality again in the subgeometric period, exactly as for the decorative apparatus. Thank you.
Thank you very much for this interesting talk. Are there any questions? Would you allow me one? I was quite interested and also excited about this bone.
Yes, but it's not so strange. It's almost common in Apulia technologies. You're welcome.
So we will have now the last one because the Archaic Mediterranean Exchange won't present the the study, and we go with Islamic glazed ceramics from Mertola in Portugal, an archimetric study of metallic luster glazed wares by Nicola Ianni, Jose Mirao, Gomez Martinez, and Beltrame. So please, thank you.
Hello, everybody. I will be presenting my thesis on Islamic glazed ceramics from Mertola, an archaeometric study of metallic luster glazed wares. So, as many of you may know, Iberian Peninsula was under Islamic rule for around 8 centuries, starting with the Umayyad Empire and continuing with the Almoravids and the Almohads up until 1212, and ending with a surrender of the Empire of Granada in 1492. So we can assume that this long period had an impact on the material culture of the peninsula. And we have a characteristic example of the lusterware glazed ceramics found in excavations all around southern Spain and Portugal. Some information about the glaze. It's a glass layer applied on the ceramic surface and integrating with it through the firing process. The main components are silica, lead, and alkalis. That the concentration varies based on the productions. Some words also about the luster. Is a very thin layer made from nanoparticles of copper and silver and integrated with the glaze matrix. The aims of the thesis is the determination of provenance of lusterware samples from Mertola, the identification of glaze and lusterware technology by comparative analysis with samples from Coimbra and Calatrava, and a potential confirmation of a lusterware workshop located in Mertola. For the materials, we used 10 decorated samples from Mertola with a variety of luster colors as red, green, and golden, 2 samples from Coimbra with amber and brown luster, and 5 samples from Calatrava with green and golden luster. And to establish the provenance for the samples from Mertola, we also had 6 samples of commonware. The methodology was optical microscopy, X-ray diffraction, X-ray fluorescence, and scanning electron microscopy, energy dispersive X-ray spectroscopy. So starting off with optical microscopy, the samples were divided into 3 pottery fabrics. The first pottery fabric includes only one sample. It's a commonwear sample from Mertola that had very low concentration of inclusions that differentiated it from the rest of the samples. For pottery fabric number 2, we have commonwear and decorated samples found in Mertola. We have a variety of inclusions as quartz, potassium-rich feldspars, plagioclase, chert, and a circular grains of muscovite. The fragments and the inclusions match with the region of Mertola, as the phyllite slate quartzite group is rich in quartzite and gray wake that was found in the thin sections of the samples. Finally, in the third fabric, we have the lusterware samples found in Calatrava. Mineralogically, we have quartz, muscovite, potassium-rich feldspars, and biotite. But what actually differentiates these samples from the samples from Mertola is the presence in fossils. Specifically, we have planktonic foraminifera found in all the samples. And also we have the presence of secondary calcite filling porosity visible in all the samples. Moving on to the result of XRD, the samples were divided into groups based on the presence of pyroxenes and galenite, which contradicts the results of the optical microscopy, as the decorated samples from Mertola are rich in calcium, and they are considered in the calcareous group amongst with the samples of Calatrava and Coimbra. Continuing with the ceramic paste, we can see that the results of X-ray fluorescence confirm the division into 2 groups of calcareous and non-calcareous. Also, the same results, more or less, are found in the ceramic paste analysis from SEMIDS. And here it's also included the samples from Coimbra that were not included in the XRD. Moving on to the glaze morphology and technology. Based on these images from all the samples, we determined that all of the samples had the glaze, a corroded glaze due to weathering, a lot of cracks and a lot of bubbles, and thin crystals all over the glaze. From all the samples, we can see that we have a limited interaction layer. The interface is very limited, which gives us the information that the glaze was applied on already fired ceramic bodies, as the glaze and the ceramic paste did not interact that much. For the glaze chemical composition, we have 2 different technologies. We have tinopacified alkali glazes for Coimbra, and for Mertola and Calatrava, we have tinopacified high lead glazes. One sample from Mertola presents very similar technology with the samples of Calatrava, as you can see. But also, we can say that samples from Mertola are higher in silica. And finally, the luster. We did analysis of the luster of 5 samples, and we have 3 different technologies. We have silver and copper nanoparticles for samples from Coimbra that are compatible with the brown and amber color. We have silver nanoparticles for the sample from Calatrava, which gives this golden color. And for Mertola, we have copper nanoparticles that give this red distinctive color. The presence of lead in the glaze gives a metallic shine to the luster, whereas the alkalis make the luster opaque. Here we have 2 pictures of the luster layer, and the samples high in lead glaze are significantly narrower as the lead increases the ionic mobility of the nanoparticles, so they all accumulate to the surface layer. Concluding, we did not, in fact, determine the provenance of the lusterware samples found in Mertola, but we figured some technological information about the glaze. We have two different productions, tin opacifier alkali glaze and tin opacified lead alkali. And for the luster, we have three different methods of production. For the samples from Coimbra, the silver and copper nanoparticles are not compatible with the technology of the region. So they are very similar to the Abbasid luster that used silver and copper for the luster, and also alkali glazes for the glaze, alkali particles for the glaze. So we can say that we have three different lusterware workshops, and for the future, we suggest studies to determine the provenance of the lusterware samples found in Mertola. Thank you for your attention.
Thank you.
Thanks.
Any question, comments? This very well done. Please.
Sorry, it's me again.
Hi.
Very interesting talk. Thank you very much.
Thank you.
So quite a bit of work, as you know, has been done on lusterware from, well, other lusterware from the Iberian Peninsula, but also Iraq and Syria and so on. You talk about the nano size inclusions causing the luster. What size are those nano inclusions?
Yes, so the nanoparticles are 2 to 15 nanometers. So it was like with SEM, it was really hard to find them and locate them in the luster.
Could you actually see them with an SEM at that scale?
Yes, yes,
Okay.
it was on the slide, but it was a very long process. This is why we only did the analysis of 5 samples out of 17 that had the luster.
Had you thought of using TEM or something? Or...
We did, not enough time.
Okay.
Yes.
Thank you very much.
Thank you.
Other question? So it was the same question. Okay.
Nice.
That's a very good idea. Yeah.
Maybe in the future. Maybe in the future.
Hopefully, yeah.
Yes.
Hopefully. I have another question.
Yes.
But Coimbra and Mertola, I maybe lost the chronology. Are there?
So the samples from Coimbra are of the 11th century.
Okay.
Typologically, but as I mentioned, the technology of the luster and the glaze is compatible with Abbasid luster from the 9th century. So there is this discussion. And from Mertola, the samples are from the 11th up until the first half of the 13th century.
They said the two different technologies are chronologically distinguishable. So.
Yes, it's a bit more complicated than that because in different regions they had different technologies. But we know that for luster in the Iberian Peninsula, we have lead and alkali glaze. So it kind of differentiates with the samples from Coimbra that have a very low glaze, a very low lead glaze.
Thank you. Any other question? Seems no. So it's time for coffee. Thank you very much, all the participants. So next session starts in 11:20. We have
So, welcome back. After this fantastic photographic event, we shall proceed to our fifth session, which is targeting on conservation. And first, I would like to invite Professor Stamatis Boyadzis, who will deliver the keynote talk about, entitled, actually, Let Mother Nature Teach Us, Bio-Inspired Materials and Strategies for the Study and Conservation of Cultural Heritage. Professor Boyadzis, the floor is yours.
Thank you, Jorgo. Thank you. First thing, thank you for having me here. It's a really great honor to deliver this presentation to you. So let Mother Nature teach us. This is going to be about recent endeavors in the field of bio-inspired materials. One of the things that we are involved in our Department of Conservation and Antiquities of Works of Art in the University of West Attica. And of course, nature is a language, of course. And it goes back at the beginning of the previous century when the Wright brothers had this idea of imitating the flight of birds, and they constructed their first flight machine. Or George de Mestral, that is the guy that, I don't know if you know him, but he's the guy, he's became very, very rich by inventing the Velcro thing, because he observed these little birds from the burdock plant that stick stubbornly on your furry clothes. We all know that. And of course, the wings of a butterfly with beautiful colors. This is the morpho butterfly, but there are other butterflies with other colors. And that is because there are certain crystalline crystals of proteins that are have a certain orientation that reflect light to a suitable direction and gives us the impression of color. And there is no pigment involved, no pigment. Okay, and if we count the possibilities, there are quite many. Okay, nature has more than 8.7 million species. Among those are animals, plants, fungi, protists, bacteria, and so on. And so it seems that we have a lot to learn. We're still starting, I believe. So what exactly is biomimetic? I don't exactly like the term. I think bio-inspired is more general, and I think it's more better suited for this idea. And we can categorize the bio-inspired approaches into this. One category is the synthesis of materials inspired by nature, how nature synthesizes some materials, inspiring from what nature does for functioning the materials, mechanisms of action, and finally, how some materials are structured, and nature takes care of that as well, and we are being taught from that as well. Okay, so there's a little parenthesis here. I would simply put this question: can we really mimic nature? Because, as I said, for instance, the example is the wings of the butterfly, and has this nice photonic behavior for us. But is this the only one? Besides the light manipulation that gives us the impression of color, the same wings they are also capable of are thermally efficient. They are mechanically flexible. They are enduring for flight, and they are hydrophobic. Okay, what can we do with any of those additional properties besides light manipulation for a single material? Not that many. Okay, nature does. So we're not that very good students still, but we are working on it. So I'm gonna present you 3 of the projects that we have been recently involved. in our department. The first one is focuses on bio-inspired synthesis, and that concerns the synthesis of hydroxyapatite and mimicking how nature synthesizes hydroxyapatite to consolidate our objects, mainly bone and marble objects. The second one will be focusing on the structure, bio-inspired structures, and that has to do with how fatty acids are oriented, and that is resembling how the cell membranes are organized in our cells. And the third one is the functioning mechanisms of action, and that has to do with how microorganisms take care or get their nutrients, iron-rich nutrients, from their sources, which are otherwise unavailable to them. And we are being taught to that as well. So let's go to the first one, hydroxyapatite. Okay, we use hydroxyapatite. The general idea is that we use hydroxyapatite to consolidate bone. Why? Because hydroxyapatite is the main component of bone, the main inorganic component of bone. Okay, this is something that we have published 5 years ago. And hydroxyapatite is one of the many calcium phosphates. And here you see some, and the lower part of this table is hydroxyapatite. Actually, this is the stoichiometric hydroxyapatite. And if we count the number of calcium and phosphorus atoms, it's 10/6. And that gives you a ratio 1.67. What does this mean? This means that if we want to characterize hydroxyapatite through elemental analysis, then this ratio should be that. Okay, and if we go higher or lower, then something is not exactly going wrong, but we don't exactly, not necessarily producing this very compound or just alone this compound. However, nature does not exactly make this stoichiometric hydroxyapatite. Nature does something which is a derivative of that. Before going to that, if you see the last column here, this KSP. KSP is a measure of how insoluble in water is the salt. So you see the value of KSP is 10 to the minus 117, which is quite little. This means that this is very, very, very insoluble, possibly one of the most insoluble salts on Earth and maybe in the universe, hydroxyapatite. Okay, but nature makes a derivative, as I said, and this is the carbonate hydroxyapatite, and that has slightly worse, it's slightly worse in solubility, but still is okay, 10 to the minus 103. It's okay, I believe. And what is the meaning of carbonate? Carbonate ions insert into the crystal structure of the stoichiometric apatite to first replace hydroxide ions, and they take certain positions for that, and we call it type A, and another type that goes replacing the phosphate ions. This is type B. So how do we know about that? Okay, infrared spectroscopy is my main tool in what I'm going to present you, but not the only one. So infrared spectroscopy is not by accident the main tool, because it can give you a panoramic image of a panoramic chemical, I would say, image of what's happening in the compound or the compounds present in the material. And besides, I think it's the best technique for giving you insights of what's happening when the materials change. Okay, infrared spectroscopy is the technique for observing changes. So if we focus into this right part of the spectrum, the red square, we see that we can see the phosphate bands with a red arrow, and the calcite, the calcium carbonate, bands with the blue arrows, and two different bands, if we can see, one close to the other, is the carbonate type A and type B. Okay, and we also see the other components as the organic components with orange arrows. Okay, so if we focus on that, it's a better, to get a better idea. These are the phosphate peaks. These are the carbonate peaks, carbonate type A, carbonate type B, and there's another carbonate B peak. So we can detect what's going on. So let's go to the question. The question is, can we consolidate bone using something compatible to bone itself, okay? And why we need to consolidate bone, archaeological bone? Because bone in its burial environment, when it's excavated, it has suffered centuries, maybe millennia of a complex process called diagenesis. And diagenesis can be either part of processes that deteriorate collagen, that's mainly microorganisms and hydrolytic degradation, or in longer time range, damage of the inorganic materials. And that's interesting because inorganic materials can, such as the hydroxyapatite, can dissolve by the moisture of the environment. First dissolves, of course, the carbonates, and secondly, more difficult, but they do dissolve, is the phosphates, the phosphate part of hydroxyapatite. And then it comes back, because if they don't go very far, if you don't have like a stream of water damaging, and that's very bad news for your finding, if you don't have that, then the moisture environment is suitable for reprecipitating the ions back to their original salt, hydroxyapatite. However, the newly formed hydroxyapatite, although it's similar in chemical composition, is not similar in structural composition, because crystals are formed slower and they are bigger, better formed. Okay, so bone is something like a marvel of nature. It has an organic matrix, which is mainly collagen, a protein, and has an inorganic matrix, which is mainly hydroxyapatite, and also has water, which is a very important part, but this is a different story. How bone is built in our systems. Collagen is firstly synthesized in the cells, and then on top of the fibrils that collagen is being arranged, there are crystals of hydroxyapatite being formed by combining phosphate ions with calcium ions, which are taken again from the immediate environment in the cell, and in the with the help of other ions, which compose what we call the body fluid. Okay, and that's actually the fluid in the cell itself. Okay, and let's go back to the question. Consolidating bone, the traditional techniques or methods that conservators used to do years ago are consolidating them with organic resins like acrylates and butyrols and things like that, or sometimes with natural waxes or natural resins or gums. Okay, but all these are problematic because they have poor penetration typically. They suffer yellowing, they may become brittle, they shrink, they delaminate, and they're generally not reversible, or at least not 100% reversible. Okay, so a couple of decades ago, maybe more, a different approach came up. Why not using something which is more compatible, which is, okay, the first level of approach is just use something which is inorganic, because it's the loss of the inorganic matrix that's most the one that deteriorates the behavior of bone, right? So there have been approaches with nano dispersions of calcium hydroxide, barium hydroxide, or the in situ precipitation of very insoluble oxalate salts. Our attempt is based on the in situ synthesis of another insoluble salt on the surface of deteriorated bone, which is hydroxyapatite itself. Okay, and for that, the starting material is providing the immediate environment of the bone we want to consolidate with the necessary ion, the phosphate ion. Okay, and for that we use a water-soluble salt, which is diammonium phosphate, DAP. Okay, we got this our inspiration from an earlier work by the team of Ioanna Kakuli back in UCLA, and they actually did that. They used the DAP to precipitate hydroxyapatite on the surface of bone. So looking at that, we say, okay, maybe we can contribute to something into the characterization. Ioanna and the team used a lot elemental analysis. We said maybe we can contribute with some molecular analysis in using FTIR for characterizing what we get here. Plus, could we possibly optimize the synthesis? And here we are. Generally, the formation of hydroxyapatite is a slow process. It's a process that I have to watch my watch here. Yeah, it's a process that takes some time because it passes from some precursor phases like the DCPD here, which is dicalcium phosphate dihydrate, which it's a mineral called brucite by geologists, and that's not very insoluble. You see here that it's 10 to the -7 the KSP. After that, there is a more insoluble salt, which is called octacalcium phosphate, OCP, which is quite insoluble, and that's possibly the most interfering phase with our final target, which is the stoichiometric hydroxyapatite, or the carbonated hydroxyapatite, which is in the end of the chain because it's the most thermodynamically stable. And the process is called biomineralization. It's the same process that our system does to precipitate hydroxyapatite on our bones during the period that we grow up, okay, or even continuously until now. Some hydroxyapatite is being reformed and so on to conserve the bone in its present condition. So our technique, our method involves the soluble ammonium diammonium phosphate. So we give the phosphate source for our reaction. It's a chemical reaction. And the environment is similar to the body fluid that I mentioned before. We call it synthetic body fluid. And although we can have different idea about that, it's a cocktail of inorganic ions. It's purely ionic, inorganic ions. And so we used SBF as a medium to boost our or optimize the synthesis. Plus, we try to add gelatin because gelatin, there have been some documentation, not exactly firm and unquestionable, that the collagen part of bone might interfere with the formation of hydroxyapatite. So I'm going to give you just one, I'm not going to confuse you with FTIR spectra, just one spectrum showing what happens with various conditions. On our, we built some mockups, which are bone powder mockups, and on those we did our reaction. And just with DAP, the result was pretty good. It's the red spectrum that you see here. What we see here is that, where is the pointer? Yeah, there. So it's the red curve over there. So all these spectra close to be 100% sure that we having this material on the surface of our marbles. And I'm going to the next project, which focuses in structure. We're being taught by nature and on how nature builds structures. And we're going to see that one of the most intriguing structures of nature is the one we see in cell membranes. So be patient and go back to that pretty soon. This is something that we published 1.5 years ago. This is quite recent. And that what sparked our interest was an earlier publication of ours, where we wanted to analyze the organic residues inside brass vessels from the Egyptian collection of the Benaki Museum. Okay, so there were a lot of organic residues, and specifically from oil lamps like those ones, we expect to be oil in there, and we finally found fatty material, okay? What we normally do, we do an initial screening with FTIR. This is what you totally do, and we get a rough idea of what your material is about. Okay, and here you have a panoramic chemical picture of what's going on. However, it's not very detailed because we have many peaks overlapping. So sometimes we want to be more detailed. And what we do, this is a detail of the spectrum. And what we see here in the panoramic view, as I said, is esters. Esters is oils themselves. So there is a surviving oil. There are acids, and acids here is fatty acids, which is the result of the hydrolytic degradation of oils. And some new peaks there. And these are copper salts or copper carboxylates, to be more precise, that are formed from the interaction of the fatty acids that I mentioned just before with the copper surface. So there's something happening, some interaction happening between copper as a metal with the fatty acids. So scratch our heads saying, okay, that should be very well known, and running through literature, trying to find out what's known on the interaction of fatty acids with copper metal, right? There was nothing in there, to our surprise, nothing. Okay, and nothing systematic, nothing that gives you a firm estimate that there is something really happening for fatty acids. Okay, gas chromatography was one of the techniques that we also use and confirms our data. There is a whole series of free fatty acids in our mixture, and also there is another category of fatty acids which we call dicarboxylic fatty acids. Keep that in mind and come back to that later. Okay, so one of our protocols is to isolate, in terms of fractional solubilization, the crude mixture of ours, the organic part, the organic mixture, according to their solubility in various solvents. So a solvent dissolves preferentially the ones that they like it, like the ones that have chemical affinity to the solvent. So we kind of isolate through the solvent some of the components, and we drip the components as and let the solvent evaporate on the surface of a gold mirror. Why gold? Because it's inert. Sometimes we use copper mirror in the case that copper is quasi-inert, is a quasi-noble metal, not exactly noble metal, but for most of our samples, which are not very reactive, it works okay, but not in our samples. So after doing the same thing on a copper mirror, after 1 or 2 days, we found a green thing on it. And we say, oh, that's interesting. And analyzing it through our FTR microscope, we got spectra like that. Okay, this spectrum is what happens on gold mirror soon after we drip it, the day after, and the month after. Stays there forever. Doesn't react, and it shouldn't react, okay, because gold is unreactive. And we see fatty esters, which is the oil, the surviving oil itself, and the fatty acids, the free fatty acids, okay? But what happens on the copper surface, the copper alloy surface? After day one, we see the formation. I think it's the other way around here, the numbers. Day one is the formation of some bands here, which are copper carboxylates. Day two, day three, day four, something is being formed. And this is similar to what we saw on our real samples, which again were on copper, inside the copper vessels, the archaeological copper vessels. So there should be some reactivity, okay? Here we see the carboxylates or the copper salts. And one might say, okay, wait a minute. Copper is reactive with acetic acid, with vinegar. That's the way a well-known pigment, verdigris, is being formed since antiquity, at least since the Roman times, and that was a huge synthetic pigment during the medieval times, the medieval era, and also during the Renaissance. How is verdigris being formed? Verdigris is copper acetate. And you have some foils of copper on a beaker of vinegar. The fumes of acetic acid fly and they attack copper, and hence you form the pigment. You can see after 1 day or so the green crystals, which are nice and ready to use them as a pigment. But why does this react? I mean, we know that copper is quasi-noble, and that it is shown in this equation here. It is the oxidation of copper, and it has a negative oxidation potential. Negative means doesn't happen, not spontaneously at least, which means now that we know that it happens, it should need a boost, okay? And the boost is acid, vinegar or acetic acid, and oxygen, which in the presence of acid gives you water. And you see here how hugely positive this is. And if we sum up this...
Sorry, Professor, you're running out of time. Sorry for the...
I'm already out of time?
You're running. You're closing.
Running, yes. Thank you, Yorgo. So we detect the product, which is verdigris, okay? So the questions that may come up concern how a fatty acid now, which is not acetic acid, a fatty acid is like acetic acid, but with longer chain. How does this, do they react in a similar manner? Well, this is a series of fatty acids, okay? Different number of carbons. And we tried all those on the copper of surfaces. And in most cases, we got green products, except in case number 3 and number 4, we didn't see anything. We only saw the white spots, which are the dicarboxylic acids. This is the case that we applied the dicarboxylic acids that we stayed there forever with no reaction. Okay, this is a better picture showing the green product with C8 carboxylic acid. C8 means 8 carbons. Okay, and we followed that with continuously scanning our spectra, which I think everybody can see how consecutively and steadily the acid peak goes down because it reacts, and it goes completely off after 2.5 hours, okay? And there are some other peaks going up, which are the carboxylates. The yellow ones are copper carboxylates, and the blue ones are zinc carboxylates. And we can also come up with our nice kinetics with the peaks going down and the pink peaks going up. And we see that longer chains take more time, and even longer chains take even more time, okay? And the C16, for instance, demands 24 days to be totally reacted, or even more, okay? So why does this happen? Just give me a couple minutes for that. Running through the literature, there is this issue of self-assembled monolayers. And this is a technology thing, trying to replicate what's happening in cell membranes, okay? And what's happening in cell membranes is the parallel, this is a better image, a parallel arrangement of carbon chains and having polar head groups on either side, up and lower, and that is a stable arrangement, and that's stabilized by energetic and entropy factors, okay? So in self-assembled monolayers, or SAM, this idea is being replicated on, this is actually what has been so far studied is gold surface or silver surface, which are inert. So these are stable on an inert substrate, okay? In our case, if we have short chains, they're not stabilized in the same situation because the chains are not long enough. But if we elongate the chains like C16 or C18, then we achieve this orientation that it is governed by parallel alignment of the carbon chains because of the hydrophobic attraction between them. Okay, and what does this mean? This means that if we achieve that arrangement, oxygen has to run through, but doesn't run through very easily because the path is quite steep for it. It has to run a long way down to react. So that's why it takes so many days for C18. Okay, but how about the carboxylic acids? The carboxylic acids are a different thing. If we do the same idea, we don't get any problem and any product. Okay, they stay there forever, and the explanation that we give is that they also conform in a kind of self-assembly monolayer thing, but there's a second layer and a third layer in a multi-layer arrangement, which are stabilized by attractive forces between the carboxylic groups. So oxygen, here it goes. Yeah, it doesn't find a way very easily, or maybe it doesn't find it at all. So that's why it does not react. So that gives us an idea that first, the longer chain of the monoacids are a governing factor that the reaction can be controlled. The detrimental deterioration reaction, that forms the salts, which is something unwanted, of course, may be controlled by the longer chains. But more importantly for us in conservation, you can use the diacid concept to make material that finally prevents and preserves the copper surface by further degradation. Okay, how we are from time, Yorgo?
You're already 35 minutes.
Already, or do I have 1 minute?
34 minutes, actually.
34?
From my side, you have.
Okay, I will.
I think it's very interesting
okay.
for the audience as well. So.
Okay, 1 minute and a half. Okay, I just want to run through the latest project very, very briefly. This is the PhD work of our colleague Rula Rapti, and this is inspired by the biofunctional aspects of some compounds. What are these compounds? We call them, okay, this is our recent publication. We call them siderophores. Why? Because they are capable of capturing or binding to iron from iron oxides and hydroxy oxides, as that you see here. So we have this difficult problem like stained wood or stained textile. So the mock-ups that we did, here is a table with some of the oxides and hydroxy oxides, and the last column gives you an idea of the solubility. The solubility is low. That's why it does not dissolve in water or in our typical solutions. Okay, and there are microorganisms that they do this marvelous thing. They synthesize in their cells complexing agents that they are so potent complexers, or chelates as we call them, to bind to iron very, very effectively. Okay, and that was discovered around the 1950s, and that was a bingo thing. Okay, and that was used in agriculture, health, material science, environmental research, and I bet that many of you might know the application for treating thalassemia, mesochiac anemia, where the system produces few red cells, and iron doesn't know where to go, so it's accumulating abnormally. So we need to attract iron, and this is how we treat it. We provide the system with the siderophores, which are complexers taken from the microorganisms. These are very potent, as I said. Plus, this is a model replication was happening, you can imagine that this is a molecule that binds to iron. Iron needs 6 arrows of that because it forms hexadentate chelates, as we call them. And that kind of replaced, this idea kind of replaced the more traditional, that's not a good word, approaches using synthetic complexers or chelators, such as ADTA, I bet most of you know it, and DTPA. These are synthetic and industrial. So they have one bad thing, which is away from nature. We have this little late tendency and trend to go as close to nature as possible. But there's another thing. They are not specific to iron. So they also complex calcium and other metals. So if your object has calcium, it takes calcium as well, which we don't want it, okay? So that's why we use that. This is what ADTA works with, works how. And this is a hydroxamate, as we call it, type of siderophore. And look at that. The formation constant is 10 to the 30.6, huge. And there's another one, another variation of that, which is cyclical. You see the orientation of the molecule, which is cyclical, which is more efficient in capturing iron. And that's why the binding constant is 10 to the 32.5, huge. I don't think there's anything better in nature than that. Okay, so microorganisms seem to be pretty clever in doing their job, and we are being taught of that. Okay, I'm finishing here because I don't want to, but to steal your time. The idea of that is that we did some trials on our coupons of textile and wood, and what we got was pretty promising results of using siderophores loaded inside gels. And these gels would be soft gels like xanthan, or more rigid gels like agar or our agarose, or chemical gels like NanoRestore, the ones that the team of Baglioni makes. And I think that's the end for me today. Thank you, Yorgo, for being patient, and all of you.
Please be informed that Professor Willis is the head of my department, so I was a little bit, manipulating the situation. So now.
I tried not to bring it up, Yorgo.
Okay, so we are running out of time, but I think we have time for 1 or 2 short questions, and I'm sure that will stimulate further discussion at the coffee break. So, any question? Quickly, please. I can't believe there's no question.
Everybody wants to move on.
Then we shall move on. Thank you very much more.
So thank you very much. Thank you very much.
Now, the next speaker is Dr. Scrano, and the talk is entitled "The Vulnerability of Archaeological Artifacts: the importance of innovative conservation." Dr. Scrano, right? No, I was misled. Sorry. You are? All right. Sorry for this, and the floor is yours.
Okay. First of all, thank you so much for this opportunity. And my name is Çağdaş Özdemir, and our project focus on about the importance of the innovation conservations. And today I want to try to explain to our work under the 3 headings. And the first of all, I talk about our motivations and our goals. And secondly, I talk about the materials. And the third one is I'm gonna try to explain to our results and our conclusions. Now I will elaborate these topics. And the basis of our study is metal materials in the Middle Age extracted from the Basilicata, and Basilicata in the region in the Italy, and also And also, as you can see, there are so many studies on these materials on the extracted from this region, and it is important things, in my opinion. And this study targeted the characterizations of the materials and the treatment or removing of possible corrosion. And it's another important things. It's our goals is to find innovation methods for the remove and corrosion layer on the stone. And I'm sorry. Yes. As you can see, left side, its figures show to us, and these archaeological materials, and we have analyzed, and the right side is figures show to us, and we used its copper and the stone for tested its anti-corrosion methods. And another we used its plant extract, its Solanum nigrum, and microorganism, it's the Bavaria bassiana. It's like a fungi, and we used the both natural products for the anti-corrosion effects. And actually, we preparated its plant extracts and with the ethanol, and also we grow to its fungi in the tryptic soy broths. And also, now I will start its about the result of the characterization of archaeological materials. And the first page show to us it's metal materials. It's like a knife, and also some EDX results told about to us. And the materials, it's the main coppers materials, and also it's the down figures. It's the coin, and the coin come from it's the Middle Age, and also the XPS results. It's the XPS results has proven that it's the coin is a copper. And I will continue result with the DAS copper, because our materials it's generally it's copper metals, and that's why we choose to its copper materials on the anti-corrosion tested. And now the figure show to us and the effects of the treatment with Bavaria bassiana on the corroded copper samples. And the further techniques had to us used for analysis on the treatments. And the important things, in my opinion, and this test illustrates the formation of the copper oxalates, and the process that stabilizes degraded the materials. And the formation of the copper oxalates shown that it's Bavaria bassiana, it's the goods perfectly affects on the corrosion on the copper metals. And another results we had, and the anti-corrosion activity of the plant extract and Solanum nigrum extract was examined, and they show to us the effects of the cleaning the plant extracts on the stone materials and the contaminated and any biological detergenic species. And the stone was treatment or removed the corrosion layer, and putting the plant extract on the stone metals. And if you look at the 30 days and 45 days, it's you understand it's how development it's the protecting or the removing the layers. And also, as you can see, its results, and this plant extract can be used. It's corrosion inhibitors, and we have it has been proven that. And also, all results show to us he had his it has been proven that Bavaria bassiana, it's like a fungi, and the plant extract, Solanum nigrum extract, as a natural method for protecting and restorations for cultural heritage. And in my opinion, it can be another additional methods instead of the chemical or the mechanical techniques safe to transfer the cultural heritage next to future generations. And thank you so much for your attention. And I try to, if you have a question, I try to answer to them. Thanks so much again.
Thank you very much.
Thank you. Also, I have its first experience for the face-to-face presence in my life, and if I had any mistakes, I apologize to you.
Are there any questions? No? So thank you again. And let's now proceed to the last talk of this session, which is going to be delivered by Mrs. Maritz, and is entitled The Three Phases of the Material Checker Project, from the project idea to the implementation of the substance. Please, your floor is yours.
Thank you and good morning. The Material Checker Project, in short, MATCH, aims to standardize accelerated corrosion testing for museums and collections. It is a project of the Conservation and Restoration Department of the University of Applied Sciences, HTW Berlin, where I work as a research assistant. The project is of particular interest to me, but should be equally relevant to those of us working with museum collections, because it has potential to improve one field in conservation, which is pollution controls. Within the next 50 minutes, hopefully, I will give you an insight on the 3 steps, the 3 phases of the MATCH project, which started with a project idea and has since then gone through several sub-steps. The purpose of this presentation is to show you the complexity of the project, but also, as previously mentioned, the importance of the topic. Therefore, I've divided my presentation into 3 main parts. First, I will give you a general introduction to the situation in museum environments and to the concept of the project. Secondly, I would like to highlight successes and challenges of the project, and finally report on the current status and outlook. To start with, I would like you to think about situation in museum environments that you have been and maybe worked for regarding preventive measures. Do you feel that in those institutions, the maximum of actions already has been reached? And can each task be given the same amount of attention? In 2021, I conducted a survey with 55 participating German-speaking museums and collections, asking for the relevance of preventive measures and the handling of pollutants. For half of the participants, preventive conservation is given mediocre consideration in their day-to-day work. Based on their statements, climate and pest control dominated the preventive measures. Accordingly, pollutant problems are not always considered as a priority in the museums. Still, we can witness a rising awareness for the impact of pollutants on collections and objects. Additionally to that trend, there are advanced technological developments that offer nowadays more and better ways to detect them. We can distinguish between 3 pollutant scenarios, which are outdoor, indoor, such as the prints on the top right, and those generated in small enclosures, like the LED statue below. As you can imagine, a situation, a closed display case, is the most extreme, as there is a certain microclimate. Added to this is the increased application of new construction materials, for display cases and packing solutions, which can pollute the environment of cultural assets with more harmful substances. This all leads to poor air quality in exhibition and storages, risk of health issues for staff, but also for visitors, and a higher demand on air quality control and material testing. Now, after the introduction, let's move to the main part of my presentation, which is the material checker project. The METCH project explores and innovates the most common and widespread pollution corrosion test, the so-called Audi test. For those who are not familiar with it, it can be briefly described as a test based on corrosion to silver, copper, and lead plates, which are caused by volatile organic compounds. The reactions of the metals coupons occur under accelerated conditions, in this case 28 days at 60 degrees. The illustration of the slide shows the setup of the Audi test. The laboratory glass containing the sample material at the bottom, the water reservoir with the humidity and the metal indicators applied to the stopper. The evaluation is carried out visually according to a traffic light format, which distinguishes between a permanent, temporary, and unsuitable use. To sum up, the Audi test offers simple equipment and evaluation, which has since the 70s been successfully applied in museum contexts. However, the reproducibility and comparability are not yet established due to the non-standardized equipment and subjective evaluation method. Furthermore, it is not suitable due to the indicators consisting of bulk metals. For this reason, it has been subject to ongoing revisions and additions for a long time. The METCH project addresses these potential and challenges of the Audi test by exploring alternatives to equipment and evaluation methods. In 2016, it started with its first project phase. During that time, the project focused on the deficits on the Audi test container. One factor is a silicone stopper, which is used for closing the container. It shows the disadvantage that it has a low air tightness, which in extreme cases loosens completely from the glass vessel. Furthermore, it is not itself free of pollutants and less sustainable if used only once. Another factor is the mini glass, used to regulate the humidity. In connection with a larger laboratory glass, it is challenging to insert it easily. And the last factor is the lab tube itself. It is often too small for placing the test material inside, as they sometimes can be voluminous. Consequently, new reaction vessels have been implemented. The new reaction vessel includes an integrated glass reservoir for adjusting the humidity and hooks for attaching the indicator plates. Matching screw caps and sealing rings ensure maximum vapor tightness of the container. During the second project phase, the indicator plates of the Audi test were inspected. Being out of bulk metals, the tester often had to face challenges. Not only that they are of inconsistent quality, expensive, and less sustainable, but also with their need for manual preparation, they prove to be imprecise and time-consuming with every testing. As a solution, the METCH team came up with reactive indicator plates. Instead of the bulk metals used so far, glass substrates that you can see on the photo are coated very thinly with the indicator metals. The bigger substrate contains silver and copper. The smaller one is only with the lead, which is due to the different coating requirements. But how were the substrates coated with the metal? Our project partner TU Berlin developed the indicators using vapor deposition, physical vapor deposition. To put it briefly, this process has the effect that the atoms of the metals are bombarded with high high-energy ions, then sputtered and made gaseous. The atomized material is deposited on the glass substrate and forms a solid layer. To get the best results for coating the glass substrates, there are different parameters to control the sputtering process. These are the amount of power, the method of voltage, and the movement of the substrate holder. After several tests of the layer thickness, density, and adhesion, we were able to determine the most suitable settings for each metal that you see listed on the slide. First indicator prototypes were examined in several series of tests to explore the corrosion behavior and functionality. It demonstrated its general applicability and appropriate effects for the use in a matched test set. However, there was still a need for optimization for the silver and lead coatings, as they did not show always a precise reaction. Therefore, further tests needed to be run. After examining the progresses of the past, let's turn to the current stage, the third project phase. At this point in time, the reactions of the novel indicator plates were validated by a larger number of test rounds. 32 relevant museums projects of vast product variety underwent the match test. Each material was tested 10 times, plus blind samples, serving as reference. Some of them are depicted here on the photos. In total, we had 384 tests to be evaluated. The results obtained were referenced against the database and evaluation method of the Audi test. On the bottom, you can see 3 different materials tested, representing each stage of qualification in the museum environment. On the left, a permanent tape, in the middle, a temporary, and on the right side, an unsuitable color film. As you might notice, trends in the intensity of reactions for each metal can be identified according to the test material and its categorization. With a few exceptions, mild reactions may result in slight discoloration and the formation of dots, while more severe reactions emerge in transparencies, complete loss of metal, and crystallization. In addition to the macroscopic evaluation, we also carry out microscopic analysis, as you can see the example of a lead indicator plate that has been tested with an unsuitable PVC foil. In order to evaluate the reactions, not only visually, and to investigate the properties of the metal surfaces and characterize corrosion, the listed selection of analysis is carried out. The instrumental analysis provides information on how to optimize the coatings. The goal is to develop a fully functional test until it is ready for the market. Before my presentation comes to an end, I would like to talk about one of our next step planned. A future project will be match images. It is intended to innovate the purely visual and subjective evaluation method using digitalization and machine learning with artificial intelligence. The METCH project is a very complex initiative with many tasks from different areas of expertise. I was happy to present you the results we gained from the steps so far and curious about your questions. Further information can be also found in this literature. Thank you for your attention.
Thank you very much for this indeed interesting talk. Are there any questions? We do have time for questions. No questions? There are no questions. Thank you again.
Thank you.
Now let's invite Dr. Gagnatsou to take the floor for as the chairperson of the next session, which is about bioarchaeology. Thank you.
Hello, everyone. Welcome to the second session of bioarchaeology. And since we're running a little bit late, I would like to kindly ask all our speakers to please keep the time and introduce our first presentation by Smith and colleagues, two-step laser mass spectrometry analysis of food residues in pottery, wine, and cacao. Is the presenter online?
I am.
Great. We can
Hello?
see your presentation.
Wonderful.
You may start. Thank you.
Thank you. Well, thank you very much. It's a pleasure to participate. Good afternoon. I have to say it's in California right now. It's 2 o'clock at night. And I would first like to thank all the people who have contributed to the things that I'm going to be telling you about. I will highlight people, some individual people as we go along. The tool set for chemical analysis in archaeometry and cultural heritage science is very varied, but it's not always sufficient. There are many techniques for elemental identification. Those are among the most sensitive ones, but they don't always give information that is important for chemical understanding. There are techniques for biomolecules, and so this is the bio session, which I'm not entirely sure that everything I present fits in, but that's all right. Techniques for molecular identification, sometimes there are not enough of those. There is IR spectroscopy, which is heavily used. It's a workhorse. It gives information about functional groups. It doesn't always give very specific identification that allows you to identify really individual molecules. The same is true for Raman spectroscopy. Chromatography is a separation technique. Sometimes things have very comparable retention times, for example. Mass spectrometry is among the most sensitive and informative techniques, but everything has its own advantages and disadvantages. And so very often it's most powerful if we can combine different techniques, or if we can devise techniques that combine different approaches. And so the thing I want to tell you about today is our work with two-step laser mass spectrometry, which is a hybrid technique which combines high resolution UV-vis spectroscopy with mass spectrometry in one instrument. Sometimes this is called REMPI. You may encounter this acronym, Resonance Enhanced Multiphoton Ionization. So let me tell you what this is. The first step is to vaporize the sample, because we're going to do this in vacuum in the gas phase. And you can vaporize many things by heating them, but then you also destroy them by thermal degradation. But it turns out if you heat something very, very rapidly, like 1,000 degrees Kelvins in 1,000 degrees in 10 nanoseconds, that desorbs most molecules intact. In fact, we have not yet encountered any case where we couldn't vaporize our molecules intact. But now we have very hot molecules and we want to do spectroscopy. So we want cold molecules, and we have a bag of tricks. And one of them is to use a supersonic expansion. If you have a high pressure gas and it goes through a little hole into low pressure, thermodynamics tells you that the temperature is going to go down. In our case, we're going from a couple of atmospheres to 10 to the minus 6 torr, which is a 9 order of magnitude drop in pressure. And so the temperature goes down actually to close to absolute zero, 10 or 20 Kelvin. So the material that's now vaporized with our desorption laser is entrained in this gas, usually argon gas, that comes out of these holes and forms a jet, a beam into our vacuum machine, where our molecules now are entrained at this very low temperature so that we can actually do spectroscopy. So downstream, we're going to excite these molecules with our lasers, another laser. And one of the slogans in our lab is when in doubt, more lasers. And so this is electronic excitation in the visible or near UV range. we're not going to do absorption spectroscopy here because we have so few molecules flying through our vacuum chamber that there's no way that we're going to see any absorption. But when in doubt, more lasers. And so we're going to ionize with another photon, whatever the first one excites. So this first laser is being tuned, is being scanned, and whenever it hits a resonance in the excited state, then ions are going to be formed by this second photon, which could be from the same laser, that would be one color multi-photon ionization, or from a different laser, and then it's multicolor or two-color ionization. Once I've got ions, I might as well do this in a mass spectrometer. And so this happens in the source of a time-of-flight mass spectrometer. The heaviest ions arrive latest and the lightest ones arrive first. They get spread out in time according to the mass. And now I can vary my excitation laser and get a mass spectrum, excitation spectrum that is mass selected. So 2 dimensions of information, a hybrid approach. On paper, very easy. In practice, you build a machine, it gets a little more complicated, and nothing like this works unless you have great students who actually make it work. So this is the idea. We get mass selected spectra. We can, once we have that spectrum, we can turn this around and tune our laser to one specific peak and get a very clean mass spectrum, because we're now selectively ionizing the only species in there that is absorbing at that one given wavelength. And so we can ionize something in a matrix of all kinds of other things and still get a very clean mass spectrum. So we can find a needle in a haystack, provided we know the color of the needle. In other words, this is not a very general technique where we can look for a survey of unknowns. We need to know the spectroscopy first of what we're looking at, but then we can apply this to look for specific target molecules as tracer molecules or biomarkers. And so, example, this is a picture of the use of cacao by the Maya, who are thought to be among the first users of cacao. And our target molecule, our biomarker, is going to be this molecule, which is theobromine. When I first heard about this is in chocolate, I thought, that's pretty bad as we are eating bromine when we're eating chocolate, but it's got nothing to do with bromine. And of course, to this audience, I may not have to explain this because it comes from Greek. Theobromine is food of the gods, and it's actually a metal xanthine. This is a family of molecules. So this is the theobromine, dimethyl xanthine. Theophylline is an isomer of it, same mass. Caffeine is trimethyl-xanthine, and in different ratios, this appears in these different plants. And so if you want to identify a particular plant as a part of a food residue, it's really helpful if you can distinguish these different xanthines, which is particularly tricky if they have the same mass. But this is what we can do. This would be a traditional absorption spectrum of a mixture of xanthines in solution, very broad. If we just look at a very small part of the spectrum and do the spectroscopy the way we do this with our resonance enhanced multiphoton ionization, we get a very high resolved spectrum. So we can put our laser wavelengths on this peak, for example, and then get a very clean mass spectrum. And if we just change the wavelengths of the laser a little bit, there will be no excitation and no ionization. So we get an identification of the target molecule, both by mass and by wavelengths. And so we can be very certain, very specific, and also, by the way, very sensitive. The sensitivity depends on what molecule it is, because the ionization and excitation probabilities are different for different compounds. But we are typically in the picogram and often in the femtogram range of sensitivity. Now, I said this is a spectrum of a mixture, and if indeed we have a mixture, we get the high resolution spectra that we get, and for each of those compounds, they're different. And so the top two are isomers. They have the same mass in the mass spectrometer, but we can easily distinguish them by their wavelengths. And so we have this project that we did with Annabelle Ford from the Mesoamerica Institute at our university, the University of California in Santa Barbara. She has a dig in El Pilar, which is in Belize, and she gave us pottery shards from there. This is an interesting piece of pottery because it's the form of a cocoa bean. And so it's an indication that this may actually have been used for cacao. And so this is a very much zoomed in part of those spectra where the theophylline and the theobromine, the two isomers, the two forms of the dimethylxanthine, absorb at slightly different wavelengths, but we can easily resolve those. And then if we look at this pottery, we find that it has mostly theophylline. If we look at this plot chart, it has mostly theobromine. And so in the project that we did, we found cacao to not only be appearing as food residue in pottery that is identified as being used by the elite, which was the common thinking that the Maya elite were the users of cacao. We found it in pottery as well of the common folk in that settlement. Here's another example, another project that we're working on right now, closer to your home, which is in Nubia, which now is Sudan, where there were Egyptian fortresses. This is a collaboration with someone in the anthropology department at our campus. And he has pottery from these fortresses in Nubia, which we are examining and trying to identify. We're still working on this, residues of wine. And so our target molecule here is phenolic acids in wine. The problem with finding biomarkers as targets for these kinds of projects is they need to be unique for the plant or the molecules that you're trying to identify. They need to be unique. They also need to survive over centuries. And so they need to be robust, which phenolic acids by themselves are not, but it turns out they polymerize over time, and that's how they get preserved. And we can then depolymerize them and use them as targets. And so there's this family of phenolic acids, and we're hoping that we can use those to identify not just the presence of wine, but also different batches and maybe different sources of wine. And so these are the spectra that we already have obtained for these different phenolic acids so that we can try and use to identify them. Here's another example of our laser desorption, our two-step laser mass spectrometry, where we looked at the pottery, but we actually at some point turned some pottery around and looked at the bottom and found this spectrum of these polycyclic aromatic hydrocarbons. This is essentially soot. And so it shows that it was used for cooking on an open fire. Slightly different topic. Something else we can do with these techniques is look at pigments. I don't need to tell you in Greece that all these white statues probably were not all white to begin with. Here's a color reconstruction of a statue. And it makes sense that the color is gone, because to have a color means that you're reflecting part of the light and absorbing part of the light. And so any pigment by nature will absorb light, and that will potentially destroy it. And so here's a piece from the 14th century. The bottom part is a digital reconstruction of what we think it looked like. And the red paint has disappeared, but not all red paint has disappeared. So these pigments are from the family of hydroxyanthraquinones. We've looked at these two. The difference is just one hydroxyl group, but it makes all the difference because the bottom one, the purpurine, fades over time, and the alizarin is the stable version. Again, if you look at just a traditional absorption spectrum, it looks something like this. We look at just a small section of that. The way we look at it, it gets highly resolved. Another example is you can do this by Raman spectroscopy. This is Raman spectroscopy of this family of pigments, and they're all pretty much the same. It's very hard, especially when they're in a mixture, to distinguish them. But if we take our Rempe spectra of just an example of two of these from the family, they're totally different spectra, in addition to having a different mass. And so we can very specifically distinguish them. Another thing that we can do while we're at it, we can vary the time between the excitation and the ionization laser. And that tells us that the purpurine, in this case, stays in the excited state much longer than the alizarin. And that explains why the alizarin is more stable, because when you excite something to an excited state, it can undergo all kinds of photochemistry, which will lead to degradation. And that's what happens with purpurine. If you can go back to the ground state really fast, then you can dissipate your energy, your excitation energy in the form of heat to the environment, and that's much more stable, photostable. And in the case of alizarin, that happens with a proton transfer in the excited state, because that's a really fast process. Now, here's another pigment that also can do that, and that's indigo. And so, again, this is from the Maya, still bright blue. This piece of textile is 6,000 years old, and it still has blue in it. That's how stable indigo is. We've done a lot of spectroscopy on it. I'm not going to give you the details, but it's another example of how well resolved we can do this. And so we can use that to detect. We can also use that to figure out why it's stable in this case, and that's this proton transfer. And actually, it's a sequential double proton transfer. The interesting thing about this molecule is not only that it's so stable, but it's also part of something that is well known around the Mediterranean. 2 years ago, I presented at this meeting, and that led to a contact with Ioannis Karapanagiotis, who has synthesized a little bit of this dibromo indigo. And what this is molluscan purple. And so we studied it and found that we could figure out what makes it so stable, and it's a similar process. And so in addition to using this technique to detect things, we can also use it to understand some of the chemistry of these compounds. So one more thing that we are working on, once you're using light, you can think of imaging. And so many techniques are very specific. And so there are many imaging techniques that are great at spatial resolution, but not so great at chemical identification. And they're very highly specific chemical techniques that are not so good at imaging. And so if we can combine these two, then we would have a powerful approach. Now, one of the examples of applications is actually something that will be in a later session and on this conference, and that's looking at paint cross sections. If you have a little chip from a painting, and something of the order of maybe 100 micron little piece, and you turn it on its side, you expose the individual layers. And it's very powerful to be able to then chemically analyze those, but that requires a high spatial resolution. You cannot really do that by focusing, for example, our desorption laser, because there's a diffraction limit. You cannot measure something with a ruler that is larger than the thing that you want to measure. And so you cannot, with optical microscopy, get better than about the wavelengths of the light, so maybe half a micron. A much higher resolution microscope would be an atomic force microscope.
2 more minutes, please.
Excellent. So a atomic force microscope works by having a tip moving over the surface. It's like a blind person reading Braille, and it moves up and down, giving you the topography. That's a very high resolution approach. What we do is we hit the tip with our desorption laser, and then the tip works as an antenna, and we heat the material under the tip, and we then remove the material that we desorb onto a substrate, which we can then take out and analyze with our two-step laser mass spectrometry. And so we can get features that are 50 to 100 nanometers and then analyze them with two-step laser mass spectrometry. And so this is another project that we're working on. This is an example of analyzing a cross-section with different paint layers, pigment layers like that. So that's a quick overview of two-step laser mass spectrometry and how that can contribute to archaeometry and cultural heritage science. Once again, thanking everyone who's actually done this work and thanking you. And we're always looking for opportunities to collaborate and explore new projects where we can apply these techniques. Thank you.
Thank you very much for the interesting and informative presentation. I will take one question. Yes, please.
Thank you very much for a great dive into very powerful techniques. I would like to ask a couple of questions about your first, your use of mass spectrometry that you used for identifying theobromine. And I noticed that some of your mass spectra had only molecular ions, but no fragment ions. So what is the energy? Another question is, after the single mass scan, how low can you go in sensitivity?
Right, two great questions. Yes, we actually, this technique produces no fragments. We get the parent mass because the cooling prevents fragmentation, but also the photo ionization is a soft ionization method. And so we typically get no fragments or very few fragments. And so we can identify the parent mass in most cases. Sensitivity, like I said, it depends on every compound because the excitation and ionization cross sections are different for every molecule. And so we've done demonstrations where we had attomole sensitivity, but that of course is the most favorable case that we optimized. So I don't want to not give truth in advertising. Typically, we look for aromatic molecules. These ring compounds are the ones that are most easily ionized, and so those will give us the best sensitivities.
Thank you very much.
Thank you. So we can move on to the second presentation, entitled The Bioarchaeology of Urbanization in Ancient Thessaloniki by Dr. Aidonis, who is online.
Hello.
We can hear you, Sterios.
Mm-hmm.
And we can see your screen.
It's okay?
Yes, but you need to go to the start.
To the first, okay. Okay. Thank you very much.
We still see the 12th slide.
Okay, let's do it again.
Great, you may start.
Oh, thank you very much. I want to thank also the organizers of the conference. Happy to be part of this one more time. My name is Asterios Aidonis. I'm a postdoc in the Laboratory of Physical Anthropology in the Democritus University of Thrace. Our research is about the effects of urbanization in the skeletal population in ancient Thessaloniki. Usually, urban landscapes are places where the living experience of...
Sorry, the slides are not changing.
Συγγνώμη, είμαι τεχνικός. Θα πρέπει να κάνετε stop share, να κάνετε share και μετά screen. Όλο τον υπολογιστή.
Stop share, μετά.
Πατάτε share και μετά κάνετε screen. Όλο τον υπολογιστή. Θέλετε να δοκιμάσετε να μας ανοίξετε την παρουσίαση. Ξαναπατήστε το μία φορά.
Εγώ βλέπω πλέον κανονικά.
Να κλείσετε την παρουσίαση και να την ξανανοίξετε.
Okay.
Κάντε μας πάλι share, μετά screen και μετά ανοίξτε την παρουσίαση.
Yes.
Είμαστε εντάξει.
Please try to change one to slides.
Okay.
Okay, you can resume now.
Okay, thank you. So, cities usually provide better economic and social and cultural opportunities for their residents. Also access to better infrastructure and such as health services, but also rapid urbanization. On the other hand, is also linked to overcrowding, environmental deterioration, poverty, and more pronounced social stratification. There is a growing number of bioarchaeological studies that have been conducted to explore how urbanization evolves in antiquity and whether the urban environment impacted the historical population. Most of these studies use biocultural approaches and investigate the context of health, evaluating skeletal markers such as the stature, the growth, the skeletal growth, diet, diseases, or injuries. This is the classical scheme that introduced by Goodwin and Armilagos about the biocultural models of stress in the skeleton. If we change, if we input the urbanization parameters, we can see that in the first place, the urban environment, there have constraints such as population density or limited resources. There are also a buffering system in every city, which is the infrastructure and the better health services, but also culturally induced stressors, such as social stratification. And the fourth parameter factor is the resistance of the residents, which is the adaptive immune resistance of the residents. And all this results to stress indicators such as stature, health, which produce decrease in health and all social and biological results. So, our research aims to explore whether the level of health in each cultural group of Thessaloniki reflects the fluctuations of the historical transitions that the city experienced between the 3rd century BC and the 15th century after dating. And if so, what was the impact of these transitions to the living population? And even more to explore if there are variations between population subgroups. So cities which have been survived for a long time, over centuries, usually provide a good, a useful record for these studies. Thessaloniki has a continuous urban history more than 2,000 years. It was founded by Cassander in 315 BC and became a significant economic and cultural center and political center due to its strategic position in the trade routes of that connect the Aegean with the Balkan hinterland and the Adriatic with the Black Sea. If we want to summarize these historical transitions, we can find four distinct periods. The Hellenistic era, which was the period of the establishment of the city. The Roman period, which is the period which shows residential constructions and the population growth. The Byzantine period, which have successive periods of prosperity, but also epidemics and riots. And the period after the conquest of the city by the Ottomans. As we can see, this is a scheme of the city and around the area. Throughout the Hellenistic and Roman periods, the cemeteries of the city were outside the city walls. It is the dotted area that you can see in the picture. But after the 7th century AD, the use of cemeteries outside the city walls ceased, and intramural barriers took place inside the city walls. You can see the numbers of the places where the skeletal material under study comes from. This is a sample of 650 skeletons from all the periods that are under study. And we use three different axes of research. The first, the demographic analysis. We constructed life tables to find life expectancy, and we use the Kaplan-Meier survival analysis to explore the effect of urbanization in the population. We also use skeletal stress markers such as stature, body mass, and enamel hypoplasia, which is developmental skeletal indicators, and cranial trauma as a social index. Finally, we use geometric morphometrics to investigate if there is a population influx in these periods. So this is the age and sex distribution of the population. The subadult group consists, it's about 30% of the total population. And the distribution of the adults is what we're usually expect to see in biological studies. But if we see the life tables, we can see that there is a fluctuation in life expectancy, which is about 30 in the Hellenistic period, drops in 36 in the Roman, and increases again in early Byzantine and late Byzantine period, and decreases in the post-Byzantine. This fluctuation is rather a result of the representation of subadults in our saying. As we can see, this is the percentage of subadults in its period, that if you exclude the subadults, you can see that the life expectancy at 20s is much more in the same line, shows no great difference. The Kaplan-Meier analysis on the total population showed a mean survival time of 26 years, which is unexpected for pro-industrial populations. No statistically significant difference between males and females, but which is, I think that it's one more or less unusual in bioarchaeological studies. It's the same pattern of mortality that we can see in males and females in the age group of young adults. Usually, we expect to see in this age group, we expect to see females outnumber males, but because of the risks of pregnancy and childbirth. But in Thessaloniki, this is quite the same pattern, which is, if we drop from, if we analyze it, we can see that this is, we can find it in the Roman period and the undated Sabi. There are some reasons that maybe influence this pattern. There is total there is a term used in anthropological studies of contemporary populations that is the accident curve of the young people. This term describes the link between the increased mortality of young adults in relation to the risks they take. If you consider that Thessaloniki was an urban center that attracted young people and young men people to find jobs, we can, could be explained the reason why the patterns of mortality in this age group of males and females are so similar. And another interesting finding is that there is a differentiation in survival across the cemeteries in periods, especially in the Roman period and in the undated Sabi, there is a distinct, a significant differentiation, almost 5 years. The people of the Eastern necropolis live almost 5 years more than those this in the West necropolis, which is a difference more pronounced in the undated Sabi. And this results are statistically significant. But the answer in this pattern should be explored in a relation with the archaeological data, would be more useful. We use biological standards of living also to explore the effects of urbanization in the living population. Most of the indicators show no significant results. There are some changes, but not significant. The stature decreases, but not significantly. The body mass is more or less the same. And the cranial trauma are the cranial trauma are increases, but not from period to period, but also not significant. And only enamel shows significant differences between the Hellenistic, between the periods.
Stereo, you have 1 more minute to wrap up.
Ne?
You have 1 more minute.
Okay, thank you. I'm almost done. So the last branch, the last research act was the geometric informatics analysis of the temporal bone, which showed that there is a population difference which is significant between the Roman and the Byzantine period. So if we want to sum up, we can say that in the Hellenistic era has the lower rates of skeletal less indicus. The Roman period shows population growth, which is population increase in density and increase in length, and so also shows differentiation in the survival patterns. In the Byzantine period, we have population fluctuations and also higher rates of anamycoplasia and the higher rates of skull trauma. And finally, in the Ottoman era, which is also characterized by high rates of anamycoplasia. Thank you very much for your attention. If there are any questions, I'll be happy to answer.
Thank you very much. We can have 1 question. No, there aren't any. Thank you very much, Tergis, again.
Thank you.
Sorry, there is one.
One very quick question. I was intrigued by this difference in life expectancy from in the west and east of Thessaloniki. Could this be explained by, let's say, that the difference in the social class, for example, the upper classes who would consume a better food would be buried in one side of the city because their dwellings were closer to there. I don't know if that's a possibility or if it's something that you're going to explore.
This is thank you very much for your question. This is an issue that we have to explore much more. There is a very appealing approach to attribute this to differentiation and social stratification, but this should be explored in accordance with the archaeological data, not only the biological. This is the biological data. We should explore if these 2 approaches are not much, let's say. There is not proof, but the East Cemetery, the East gate of that lead to the East Cemetery, it was the gate of Kalamaria, which means in Greek Kalomeros, a good place. But that's an oral tradition, not based on data. So we need to explore more, to research more on this issue in accordance with the archaeological data.
It's also
we need to cooperate with a bigger thing with the archaeologists that have excavated the area to see if there is a differentiation in the material culture.
Well, it's also
similar with biological data.
Yeah, it's also the side of the city where the palace of Galerius is, where the and presumably all the well-to-do people would gather around there. So the name of the area has something to
steeped
in tradition. Thank you.
Thank you very much.
Thank you very much, Darius. We can now move on to the last presentation of the session, entitled A Multidisciplinary Approach to Roman Burial Site, Archaeoethnology as the Preferred Method for Studying Burial Practices in the Buried Site in Romania.
Thank you very much. Good afternoon to everyone. I would start with a thank to the organizers for giving us the opportunity to present today our research questions and preliminary results obtained through an archaeoethnological approach to the Bedaud funerary area located in eastern Romania, more specifically in the Danube Delta. As Valentin Botes presented you yesterday, because of its strategic position, this region has been occupied early, continuously, and in a variety of ways since prehistoric times. The area we are studying lies around 50 kilometers north of the well-known Greek settlement of Istria, and its archaeological density is such that it is now defined as a global archaeological zone. The work we have been undertaking over the last few years has enabled us to gradually draw up an archaeological map of the region, listing the different types of occupation. My presentation today will focus on a funerary sites that we have been excavating since 2021, located near a settlement overlooking the Dulja River. The geophysical and LiDAR surveys we've carried out showed the existence of an extensive occupation made of tumuli, at least part of which are organized in an east-west line, approximately 200 meters from the habitat. Our project began in 2021 with a thematic school, which involved 4 universities from the Civis Alliance to introduce archaeologists to the issues and methods of archaeothanatology. The interest of the scientific issues has led us to continue this collaboration and set up a long-term research project, one of the aim of which is still to train new specialists in archaeothanatology. Archaeothanatology is an approach to the archaeology of death that developed in France over 30 years ago, at the same time as the emergence of preventive archaeology. Under the impetus of Henri Dudet, a new way of understanding death in ancient societies was developed, a global and holistic one that considers all the dimensions of death, whether biological, social, or cultural. Formerly known as field anthropology or archaeoanthropology, this discipline is based on the joint analysis of archaeological, anthropological, biological, environmental, and in some cases, historical data, in order to reconstruct mortuary gestures, devices, and sequences so as to understand their meaning and what they can tell us about the social, cultural, and religious organization of ancient societies. In this respect, it is still a special approach, quite different from funerary archaeology or from the accepted meaning of the term bioarchaeology, as it was presented yesterday also, which focuses essentially on the study of biological data, in the case of human bioarchaeology, but which also concerns other disciplinary fields. As part of the Bedaud project, the excavation and study of the funerary space has several objectives. The first one, as mentioned above, is to train new generation of archaeothanatologists. The second one is to study the funerary area. And the third is to place this area within the surrounding landscape and understand its place within it. So I'm not going to dwell on the teaching aspect today, but rather come back on the first results obtained from the excavation of the funerary occupation. As mentioned above, the burial site is located to the north of a settlement, the excavation of which is also part of the Bedaud project. At present, 15 tumuli are known with certainty, but it's likely that there were at least 20. We have excavated 2 of them to date. Tumulus 1 measures around 20 meters in diameter. The excavation revealed two phases of occupation between the 2nd and the 3rd century CE. On the antique level, the first phase began with both cremation and inhumation structures. So 10 cremation structures, 10 cremation structures, all of which are primary structures, which means pyres in pit. 3 inhumation, all containing non-adult individuals. The area remained open for some time before being covered by the mound at the end of this first phase. The area was then reused for a second phase. And for example, another inhumation of non-adult individual were built from the top of the first mound before it was sealed by the second mound. The memory of the site live on long after the sealing, as pottery fragments at the top of the second mound bear witness to commemorative practices and thus to the use of the site until the 4th century at least. Tumulus 2, which is still being excavated, has different configuration. It has only one phase of occupation and a single mound. For the moment, it seems to contain only primary cremation structures, but this will have to be confirmed by a complete excavation of the surface. 7 structures have been uncovered so far. This initial data already shows some interesting characteristics of these burial mounds. Firstly, inhumation and cremation coexisted throughout the entire period of occupation. However, we also know that for now, only non-adult individuals were not burned. One might think that this was similar to Roman practice, which excluded the very young children from cremation. But here it applies to very young children as far as older ones. The question therefore arises as to whether children has a special status in this community, which did not give them access to certain funeral practices, and up to what age. The configuration of these funerary groups already shows the consequences of the interaction between Roman practices and local practices inherited from earlier periods. The cremation practices observed here are typically Roman, but the use of the mound is a legacy of Thracian and Scythian practices. What we see here is a reinterpretation of earlier practices in a Roman context, since the mound does not house a single central burial, but covers a group that operates as a concession. Here, the tumulus is not a part of a tomb, but a device for closing off and signaling the communal burial plot. The purpose and implementation are therefore completely different. If we look in detail at the cremation structures, we can see that there are only primary structures, which mean the place where the body was burnt. In line with what is generally observed in the Roman world, the shape and dimensions of the structures vary in a huge way. While they are all semi-aerial pyres, some have a bench, some are large enough for an adult body to lie on, while others are too small. Some are deep, while others have a pit only a few centimeters deep, and so on. This variability is typical of Roman context, where there is no standardized funeral practices, but funerals were left to the care of the family and therefore to individual practices. The pyres were only used once, but the study of the burn bond, which is still in progress for some of the structures, show that they can accommodate a single individual or several ones at the same time. For example, an adult and a non-adult in one of the pyres in the tumulus 2. Excavation using vertical and horizontal subdivisions make it possible to geographically reposition the bone elements left in place in the pit and to recognize the initial position of the individual, whether any handling took place during cremation, and how the remains were removed after cremation. The forthcoming anthropological study of the charcoal will also provide essential data on the wood used for the pyres, their provenance, and therefore the supply networks, as well as the method of construction of the pyres and their system of ignition. We have to note that no matter the type of pyre, after the cremation, all the pyres underwent a major removal of the residue, sometimes going so far as to empty the pit completely. This indicates that another structure was created after cremation.
Pour faire cela, vous devez être en...
Sorry. It is these structures that takes on the status of the grave and not the pyre, which is a technical device here. None of these final graves can be found inside the tumuli. This leads us to look at the spatial organization of these funerary groups. Firstly, we note that the organization of the tumulus is completely different between tumulus 1 and tumulus 2. In tumulus 1, the structures are concentrated in a southern half in direction of the habitat. But in tumulus 2, they seem to spread out around the center of the mound. This attests to another characteristic commonly observed in Roman funerary areas, the independence of the groups. The entire area should therefore not be considered as a single burial site managed by a whole, but as a space open to the dead, where a multitude of burial sites were set up, corresponding to as many human groups, families probably, but possibly also other forms of social grouping. As we have said, the evidence of massive removals from pyres indicate that secondary deposits were formed after cremation. This means that, on the one hand, the existence of inhumation graves with markers plus the mound showed the desire to preserve the memory of this space and leave a lasting mark on the landscape. And on the other hand, the cremation graves are in another location. There are therefore multiple places of memory to be imagined, and therefore potentially a pathway through the landscape at the time of the commemorative rites. This special dimension of funerary rite is absolutely essential. But where are these graves made of cremation remains? We need to change scale and look at the general landscape. And from this perspective, the question of the road network is essential, as much as, or perhaps even more, that of the habitat. The east-west layout of the tumuli suggests that there was a road running in this direction and that the burial groups were settled alongside it. However, there are several possible locations. The one we favor now is a location between the tumuli and the settlement, especially as two tumuli are in the immediate vicinity of the settlement. Given our knowledge of Roman practices, it's likely that the secondary cremation graves and perhaps other inhumation graves, why not, are to be found close to this road. Finding this road is therefore one of the next essential stages in order to find the secondary cremation graves and gain a better understanding of the overall organization of this area around the Bedaoud settlement, but also between Bedaoud and other settlement and burial sites in the region. With the continuation of the excavation of the burial space, we will seek to understand the status of the tumulus, both in terms of space and symbolism, in the funeral process and in the perpetuation of the memory of the dead. There is also the question of the legal status of the plot and its extension. Are they limited to the extension of the mound? What about the space or the place where the final graves are located? And what about the circulation spaces between them? All this also raises questions about what kind of element structure the landscape. What is considered to be representative of the presence of the dead? Is that the tumulus or the grave, or both of them, or other structures? Do we need to look at things from this individual point of view, by the way, or on the contrary, is it the belonging of the whole, the group, the tumulus, or the family that prevails? So we have still a lot of work to do, but we have some exciting prospect for understanding how the people of this period and this region view death and therefore manage their death. Thank you.
Thank you very much. Are there any questions for our speaker? Yes.
Okay. Thank you very much for your presentation. It's very interesting, the kind of tumulus you find. So if I understand well, you find the primary cremation, as you say, it's just the remnants of the practice, but you haven't found any skeletal elements, right?
Skeletal elements? You
Cremated
mean?
bones.
Yeah, we have. Not so much because, as I said, the major part of the residue was collected after the cremation. But yes, we have cremated bones as at the same time of charcoals and other, maybe ceramics fragments that were on the pyre before the cremation. So yeah, we have some. And the study is on progress.
Oh, perfect. So based on these cremations that you find, you test that it's a complete cremation, full, or could be another kind of practice like fumigation that they used to do for
No,
purification.
it's a complete cremation. It's a well-known process for Roman funerary practices. It's quite homogeneous, and most of the time it was conduced by an ustor, probably. And then the collection of the bones, we don't know if it's the ustor do it or the family members, but it is done.
Okay, thank you very much.
Thank you.
Are there any questions? Any other? Okay, thank you very much. Thank you all for being here. Let's go to the lunch.
قبله نعم تالية Το λέιζερ λειτουργεί και μπρος πίσω. Πώς?
This is the second talk at the moment. Yeah, 30, that's the one. Thank you. Oops. Yeah, I think we might as well start. I'm Julian. I'm chairing this session on glass, and I happen to be the first speaker. So I've already introduced myself. So here we go. Let's see if we can have the first image up. There we are. Yeah. Anyway, it's an honor to be here and give this talk in memory of my dear friend and close colleague, Nikos Zacharias. So the title of my talk is A Proto-Silk Road in the West, a new glass technology and evidence for East-West connections. Okay, so we published an article in Scientific Reports in 2021 showing the movement of glass, natron glass in this case, along the terrestrial Silk Road from the Levant all the way into China. So my question is there any evidence at all for a proto-Silk Road? So we're talking about prehistoric Silk Road, before the so-called historic Silk Road starts in about the 2nd century BC in the Han Dynasty. We're talking about the 8th and 7th centuries in particular, and the 9th centuries BC. So is there evidence for this proto-Silk Road extending from West Asia further northwest? That's the big question. But I thought I'd just introduce you to the basics of glass technology. So my colleagues won't need to repeat the same stuff, or if they do, there's no problem, but here it is. So this is the technology used to make late Bronze Age and early Iron Age glasses in Western Asia between the 14th and 7th centuries BC, so from the late Bronze Age into the Iron Age. So either a combination of crushed quartz and sand or plant ash, or crushed quartz or sand and natron, which then produces glass. The most common artifacts, I guess, are beads made from that. So that's relatively simple. Around about 1200, and a lot's been written about this, there was a social, economic, and political collapse in Western Asia, as we know, the Mycenaeans, Mesopotamians, and Egyptians. Not only, well, social, economic, and political systems were all collapsed and modified and changed. And amongst that, we also see glass technologies disrupted as well. So one of the results of that was the introduction of natron. So we have plant ash exclusively used till about 1200. And then there's a period of change. Around about 1000, you get the first natron glasses, certainly 11th century. And then also from around 1100 BC, you get mixed alkali glasses being made in Italy. So you get those two new technologies being introduced as a direct result of social, economic, and political collapse in Western Asia, or the Middle East, as you might refer to them. So this is a simple plot of weight percent magnesium oxide against weight percent potassium oxide, something that a lot of glass specialists use as a first look at their data. And you can see on the left there, up here, oh no, it doesn't work, okay. Anyway, the yellow spots are mixed alkali glasses with up to 18% potassium oxide. Anyway, quite a range of potassium oxide levels between 6 and 16%. Then in the bottom right, you've got plant ash glasses with much lower potassium and much higher magnesium oxide levels. Those plant ash glasses continue in Western Asia and in Greece, in fact, until at least the 8th, if not the 7th centuries BC. Then the third main technology that I've already referred to is natron glass with this lowest levels of potassium and magnesium. So natron glass natron is a mineral. Obviously, plant ashes are organic and have much higher levels of impurities. Question is, are there any other new technologies that get introduced around 1000 BC? And I wouldn't be given this talk if the answer was no. In fact, I would stop here. In order to answer this question, we looked at a wide range of glasses from a range of dated sites. So the earliest sites are Wisal Pools in Jordan, Hassanlu in Iran, and Danish, a whole range of glass beads from late Bronze Age Denmark. The second group are 9th to 7th centuries BC, Must Farm in the UK, England's Pompeii, as it's called, because everything's so fantastically well preserved. Kaman Kalyahoyok in central Anatolia, Sardis in Anatolia, and Bidna in Greece. So that's the second dated series of sites that produced the glass. And then the latest 6th to 4th centuries BC are Dren Delian in Bulgaria and Pichvanari in Georgia. Okay, so these are the sites for which I'm going to compare various results from. And here are some of the artifacts. So in the top left, you can see some of the 40 or so glass beads, and amber in this case, also from Must Farm in the UK. The bottom left are those eye beads from Kaman Kalyahoyok in central Anatolia. And the top right, a bunch of late Bronze Age turquoise glasses published by Verbeek et al. In 2015 in Journal of Archaeological Science. So I'm only going to be talking about beads, which is not surprising, I guess. Anyway, so this is exactly the same diagram as I showed you a couple of slides ago. And all I've done here is to introduce some data for the Must Farm glasses. And it's really very simple, on this particular slide at least, that these Must Farm glasses contain lower potassium oxide levels than plant ash glasses, but have overlapping levels of magnesium oxide. So you can raise the question, therefore, are these made out of plant ash or aren't they? And the answer is they're not. In fact, they contain elevated levels of boron. So this is a plot of soda against sodium, I should say, against boron in a whole wide range of glasses. So at the bottom, I'll start with the bottom, colourful little assemblage of group of glasses, I should say, Plantash and natron glasses containing minimal levels of boron. Then above those, we have the results for late Bronze Age Danish glasses, which contain elevated levels between about 500 and 1,000 parts per million of boron. Above that, we have all the data from Must Farm, a lot of the glasses from Kaman-Kaliohuyuk, containing between about 1,000 and 2,000 parts per million of boron, and the glasses from Wisad pools as well in Jordan. And then the highest levels of boron are found in a small number of glasses from Kaman-Kaliohuyuk and mostly from Sardis. So we've got this range of boron levels in these different glass beads. At the bottom of this slide, I've listed the sources for a lot of this data. But essentially, it's not very common to find elevated levels of boron in glasses. So you can cite thousands of analyses for Plantash glasses and natron glasses that contain minimal levels of boron. So it's quite exceptional to be able to point to compositions of glasses that contain elevated boron levels. So there the question arises, what are they using as a source of sodium? What's the sodium-rich mineral that's being used? And the very likely answer to that is boron-rich deposits that occur in Turkey and also Iran. So in the top left, you can see the location of some of these boron-rich deposits in Western Turkey. So there are several deposits, and it's questionable whether we can be sure which one was exploited. And then a picture below that of what those deposits look like, those geological deposits. On the right, you've got the location of Lake Urmia in northwestern Iran, and below that, a photograph of this massive deposit of borax. So the two likely minerals involved in the exploitation of these soda-rich boron deposits are borax and oxalite, as you can see there. If we move on and look at the relative levels of calcium and magnesium, there's no question they're positively correlated. And the explanation would seem to be that they're using a third raw material, deliberately adding a third raw material, probably dolomitic limestone. And here we see a distinction again between the likely Iranian source of boron with the higher levels of magnesium and calcium, and the likely Turkish source of boron with much lower levels of both. And again, the Turkish ones contain between 2,700 and 8,400 parts per million of boron, whereas the likely Iranian ones contain between 1,300 and 2,000 parts per million of boron. So this is really a new technology. Clearly, this was a time of experimentation as a result of being one result of the political economic collapse of late Bronze Age societies. So an exciting time to be looking at glasses and other materials. If we then look at the ratios of lithium potassium against rubidium potassium, we can see there's a nice distinction between the high boron and lower boron. The groups could be better, but nevertheless, they are distinctive. It's worth saying that potassium, rubidium, and lithium are associated with borate deposits, such as in alkaline feldspars. And another thing to notice from this slide is the late Bronze Age Danish glasses actually sitting amongst Egyptian late Bronze Age Plantash glasses. So an explanation for that would seem to be that those plants were actually growing close to or on a borate deposit and were taking up boron in the tissues as they grew and were then used to make the glass. So that's a slightly different, from the Turkish and Iranian glasses. And then you've got obviously a nice distinction also from natron glasses. So essentially what we have here are three groups of glasses made with three distinct types of sodium-rich alkalis, two minerals and one plant ash. And then, well, we only have one isotopic result, the little red spot there for a Must-Farm glass, but it does nevertheless fit into a group, one of the Mesopotamian groups that is well established for neodymium and strontium isotope results. So that does tend to reinforce what we've already come up with as an interpretation for the glasses using trace element analysis. So does this movement of glass from Iran all the way to Must-Farm in the UK, of all places, constitute a Western proto-Silk Road? Well, I'm not going to say yes or no, but at least it's evidence for the movement of human beings across this landscape carrying these little tiny glass beads. Very likely that this would have occurred in a segmented way rather than in a single journey, but nevertheless, it's an intriguing and very, very unexpected result. Indeed, some of the people I've collaborated with in publishing the Must-Farm glass couldn't quite believe it, but I think it's relatively compelling as an interpretation. Okay, so my conclusions are around about 1200 BCE, late Bronze Age society collapsed, probably due to climate change, the sea peoples, amongst other things, and glassmakers searched for new raw materials and started to experiment with new ones too. A new borate flux used at sites as far apart as Hassanlu in Iran, Wishad Pools in Jordan, and Must-Farm in the UK seems to have been used to make the glass. A new three-component recipe was introduced using silica, a soda-rich borate deposit, and dolomitic limestone. So it joins the other new glass technologies at the time, natron and mixed alkali glasses. There's apparent compositional distinctions in glasses made with the borate from Lake Urmia in Iran and the Turkish borate deposits in Western Anatolia. Iranian borate reached as far west as Must-Farm nearly 3,000 years ago. So this could be evidence for a proto-Silk Road. Most people concentrate on the proto-Silk Road going the other way to China, but why not suggest that we have a similar one in the West, although it didn't involve silk as such. So we should call it maybe the proto-glass road. Okay, thank you very much. Any questions? Yes, please.
Thank you very much for the talk. I really enjoyed it. I was wondering if you plan to sample any glass assemblages from the in-between areas of Must-Farm and the East, or if there is the possibility of doing that. Thank you.
Yeah, that's a very important question. That's certainly one of the things we're going to try and do. It's quite a job actually finding these high boron glasses. The other thing that we've got planned is to use boron isotopes, because certainly Lake Urmia and the Anatolian sources should be different in terms of their geological ages, formation ages. So we should get a nice contrast there to support the chemical characteristics. But yeah, I think it's extraordinary that almost all the so-called black glasses from Kaman-Kalahuyuk have this high boron level in them. So maybe the way forward is look at more of those. Others have been published, but for example, from Italy, but actually it doesn't contain boron results, unfortunately. You can suggest that some of them are from other characteristics, but you can't be certain. So yeah. Anyway, thank you for your question.
Thank you very much. I have many questions, but I think there is time at dinner. I just limit to one. The deposits of borax that you show in the map are the only one in that region, or there are many? So they selected some. Can you precise it a little bit more? Is it possible to precise where they source it?
That's a good question too. So Lake Urmia is massive, and it stands alone as an enormous borate deposit. There are, 4 in Western Anatolia and others, two others further northwest. So that's another question to be answered, whether we can distinguish perhaps isotopically, although I doubt it, between those different deposits in Anatolia, but it's worth having a go. Yeah.
Exactly.
Yeah.
Thank you.
Thank you. Oh, one more down here.
Thank you, Julia, for this fascinating talk. I was wondering if there is any evidence using borax in other, let's say, industries. Like, for example, natron was used. We know that it's used. It was used in Egypt for mummification. Was it something similar with borax, or do we know anything about that?
Not that I'm aware of, and as you will know as a glass specialist, of course, borate, very high borate glasses don't really come into the 19th century in the West. It's actually, no, I tell a lie, probably the 17th century, because they get as far as China, because the West glass makers traveled to China to make glass made out of borax, believe it or not, in the 17th century. So that's an example of the Silk Road again. But in the West, not that I'm aware of, no, but it's an interesting question, because certainly, for example, natron was used for embalming bodies before it was used for making glass in Egypt. But anyway, yeah. Okay, thanks for the question. So I seem to be, another one.
One more.
Right.
Do you think there is enough boron in the mix there to influence also the melting temperature or the glass transition temperatures?
Interesting question. So there's a nice experiment for somebody to do. Yeah, we're just at the beginning of a long journey, I can see. Yeah, so that's definitely a master's degree project at the very least, if not a PhD. Yeah, because you've got, I showed you a slide of parts per million of sodium, but of course, in oxide, that's between about 16 and 20% sodium. So they're pretty high. They're getting enough sodium. But whether the boron actually, 2,000 parts per million, probably not, but you just don't know, do you? It's an intriguing question. Yeah. Okay, thank you. So I'll introduce the next speaker, who is Dr. Artemios Oikonomou, and he's going to talk about glass in late antiquity in Greece and overall assessment. The floor is yours.
Thank you, Julian. Good afternoon. I would like first to thank the organizers for giving me this opportunity here to talk today. And of course, this paper is dedicated in the memory of Nikos. So to begin with, I will start with saying a few introductory things which some of you know, but for those who are not very familiar, I would like to put you in the context. Glass production in the first millennium AD is divided into two separate activities. The primary production, where we have the fusion of the raw materials into the so-called raw glass. And then the secondary production, where secondary workshops remelt the raw glass and shape the final objects. primary glass making during antiquity, and especially during from the Roman period until the 7th to 9th century AD, happened mostly in these two regions, the Levantine coast and Egypt. And from these two areas, most of the glass during first millennium AD was further distributed all around Europe, at least to the secondary workshops. In this map now, you can get an idea about the vast amount of the primary glass production centers found in Egypt and the Levantine coast. This probably was not random and must be associated mostly with the abundance of raw materials and favorable conditions to facilitate their fusion. So now there has been a significant amount of work by various scholars the last 20 years on late Attic glass. Through this research, it was possible to identify at least 7 compositional groups with a super-regional distribution. These groups of glass were made in different workshops in the Levant and in Egypt, and can somehow easily be distinguished analytically by comparing specific elements, or at this specific example here, elemental ratios, which are associated with sand. And therefore, we can see that these groups have very distinct positions and hence were made using different sands. This line somehow distinguishes the two production zones. The groups of glass above this line were manufactured in Egypt, while the two groups below the line were manufactured in the Levantine coast. So the main aim of this paper is to explore glass in the first millennium AD, and especially in the Proto-Byzantine period in Greece, and to make an overall assessment of the compositional groups found in various sites in Greek region, and understand how glass was distributed in Greece, and hence identify the possible trade routes. To fulfill these aims, I will present you today data acquired by myself the last couple of years from various sites in Greece. And in particular, for the next few slides, I will be talking about 2 sites in the north of Greece, at Chalkidiki Peninsula, which were consumption sites, since they are coming from 2 basilica churches. 2 sites from Epirus, namely Nicopolis and Ekdikos Georgios, which are in close proximity to each other. And I will give you some further details afterwards. Panagia site in Corinth, and 1 secondary workshop in Crete, in Argyroupolis. And finally, I will use data already published in the literature from sites in Macedonia. As you can see, these are the 3 sites up here from Thessaloniki, Philippi, and Maronia. Starting with Chalkidiki Peninsula, investigated glass material from 2 consumption sites. As I said, 2 basilica churches, 1 in Kalithea, situated here on the east of the first leg, as we say, of Chalkidiki. And the other one was assemblage was coming from Furka, and the assemblage from Kalithea contains window panes, various types of vessels, and of course, the disc bases of beakers, these ones very characteristic ones, and cantilla stems. Furka assemblage, on the other hand, saw somehow bigger variability in glass vessels, including also these base rings and cantilla stems, but strangely very small number of window panes. Regarding the grouping of the material from the 2 basilicas, the situation is rather typical for the era. However, we notice that there are less objects assigned to the Levantine group, and most of the samples correlate well with the Syria 2.1 group, as you see here in the middle. And we have a significant number of HMT glass from both sides. Staying in northern Greece, included in my research the data from 2 papers and the PhD, which all relate to glass from the first millennium AD. To my knowledge, these, I think, there are the only published works for glass in the late Roman, early Byzantine period from Greece. And the glass comes, as I said, from 3 sites, from Thessaloniki, Philippi, and Maronia. We see here a similar situation. For example, in Thessaloniki, we notice an excess of Syria 2.1. They are clustered here in the middle of the graph. In Madonia, we see that all of the glass correlate very well with Syria 2.1 group. And finally, we see a variation in Philippi with most of the glass having a levadine signature. You see they are down here in this graph. Moving now to the west, and we go to Epirus, and the two sides there. I analyzed material from Nicopolis, from two basilicas in Nicopolis, which is one of the major Roman cities in Greece. It was founded by Octavian Augustus to commemorate his victory over Antonius and Cleopatra in the sea battle of Actium. The assemblage consists mainly of these beaker-based discs and candela stems. And apart from the glass from Nicopolis, in a very close proximity, there is a building called Domus of Ekdikos Georgios. It was a rich villa having an occupation, and it was in use from mid-1st century AD until early 7th century AD. As you can see, there is a significant number of glass finds found there. As you can see, various types of objects, mainly foot rings, candela stems, handles of candelas, glass panels, and various fragments from vessels. The situation here is somehow similar to the northern Greek sites. It seems that we do have quite of levadine glass, but most of the samples fall to the Syria 2.1 and the Syria 3.2 groups. What is also interesting is that the Ekdikos Georgios site does not have the variability of glass compositions noticed in the other sites. As you can see here, there are only 3 types of glass: levadine, Syria 2.1, and Syria 3.2. Moving further to the south in Corinth, this is an ongoing project with my colleague, Dr. Metaxia Papageorgiou. I analyzed glass from Panagia field in ancient Corinth. The assemblage dates to the late Roman, early Byzantine period. As you see in these photographs and the drawings, we have a rather big variability of glass shapes. Metaxia has noticed at least 7 different categories of glass types in this assemblage. Regarding the analysis here, things start to get a bit different. As you see, we notice that there is not any Syria 2.1 glass, nothing here in the center. And the majority of the samples correlate well with levadine origin. Finally, the glass assemblage from Crete was excavated at the site of ancient Lapa, which is close to the modern city of Argyroupolis, and both are situated around 15 kilometers southwest of the modern city of Rethymnon. During a salvage excavation, a complex of 5 rooms was discovered, and as you can see here in this top view, and revealed a big number of glass fragments. In addition, they found a circular construction, as you can see down here, which the archaeologists believe was the glass working furnace. More than 1,500 fragments of glass, vases, cullet, glass waste, and test drops were found. And as you can see here in these photos, and in particular here, you can see some characteristic examples of vessels found in the assemblage. Strangely, there was no discs from these beakers, which are usually abundant in other contexts, early Byzantine contexts. Of course, apart from glass vessels, we have a lot of glass-making debris, as you can see here, like semi-fused glass, test drops, and of course, furnace wall fragments and cullet. Coming back to the graph, the same graph, we see that the Argyroupolis assemblage correlates well with some of the typical groups of the first millennium AD glass. Interestingly, we do not see any HIMT glass, which is up here, and most of the glass is levadine and series 2.1, while in the first impression, this group down here, the red triangles, is also a good correlation with Egypt2 glass. However, the levels of magnesium and potash in these samples have significantly higher mean values. As you can see, it's 1.3 and 1.6% compared to Egypt2 glass, which averages only 0.5% and 0.3%. These also glasses here from Margidopolis have also very high phosphate levels than those found in other mineral natron glass groups. So this suggests that probably they were made using plant ash. And this is something that was already identified by Rosno and Retter in 2018 in glass coming from Egypt. This compositional group is very interesting, and it's worth noting that similar compositions are also found in the other Greek sites. As it can be seen here in the table, you see we have few of them, 6 samples from Frouka, 2 in Nicopolis, 1 in Ekdikos Georgios. And also you can notice the differences between magnesia and phosphate and potash between the Egypt CA 3.2 glass. So to wrap up, gathering all the data together, what we can see that Crete, being south, has better access to Levantine glass, since the assemblage is dominated from this category and having few more 2.1 glasses, CA 2.1 glasses, and also there are quite a lot of plant ash glass. This is something also noticed in Cyprus, not shown here, and probably both islands were in the same trade route, having access, let's say, to the same suppliers. We see something similar with the glass from Corinth, which is still in South Greece, which is still dominated from Levantine glass. The picture, though, is totally different in mainland Greece, and especially when we move to the north. We notice that say 2.1 dominates in 6 sites in total, while it seems that they are not very fond of Levantine glass. The only exception to this scenario is the glass from Philippi, which, as you can see here, more than half of the assemblage is of Levantine origin, and this is something which needs more research. As for the plant ash glass, most of it is found on Crete, while there is significant number of them in Chalkidiki and some in Nicopolis and, of course, Cyprus. In general, we see that during this period, this special category do appear in Greece. But as you can see from the parentheses, compared to the overall glass that I have analyzed, is very small in quantities compared to the main groups. What is the case now with adjacent areas? We see that in the Balkans, in a few sites, we do have very low numbers of Levantine glass. Highlighted here, as you can see here in this chart with the dark blue color. And the assemblages are dominated with, in particular, with Egyptian glass, and in particular with Syria 2.1. It's the yellow bars in this bars. In a recent publication, a possible trade route has been suggested for latent in glass from the Egypt and the Levantine coast, which is more or less in line with what we see in Greece. And when we are talking about long-distance trade and how things traveled in the Eastern Mediterranean region and beyond, one should take into consideration sea currents, winds, and low-cost paths. However, I don't have much time to elaborate more on this, and this slide is just a teaser for another presentation, maybe in the future. And to conclude and to sum up, what we see is that Greek sites consumes glass from both Levantine coast and Egypt. The amount of glass depends probably on the trade routes and the markets, and there is a trend that shows that southern sites, southern Greek sites receive more Levantine glass in comparison to the northern sites. And what it needs to be, more analysis need to confirm this, but also put all the analysis into a socioeconomic context of the era, which will, I believe, will shed more light in glass distribution. And before I finish, I would like to dedicate this presentation in memory of Nikos. Nikos, for me, was the main reason being an archaeological scientist. And apart from that, he was a very good friend and colleague. Thank you very much.
Thank you, Artemos, and for keeping beautifully to time.
Thank you.
Are there any questions?
Yes, please.
Thank you for this excellent paper. My question is, so the products, if these different patterns in the trade of the raw material, does this, no, I mean, the differences in the composition of glasses, we are certain that it is the raw material that was traded. And could it also be that finished products, like the secondary process, could there be a trade in secondary products?
Thank you for this question. As far as we know, that would be a little bit difficult and it wouldn't be so effective in terms of glass is a fragile product. So moving in a trip from Egypt, let's say, to northern Greece, for 30, 35 days in the sea, probably they could lose all the goods. So most likely that's why they have organized glass production in these two separate activities, like the primary glass, producing the raw glass, and then with the finished objects made in secondary glass workshops. And actually we have quite a lot of secondary glass workshops in Greece during this period. So I think it was
of course, it would make
yeah,
sense.
yeah.
Yes. The interesting thing is that the pattern, the trade patterns that glass represents are quite different from those of pottery, because in southern Greece, like when it comes to fine pottery, in the south of Greece, we find the products from North Africa mostly. And then it's the products from the Levant and from Asia Minor that dominate northern Greece. So this is an interesting observation that shows the complexity maybe of trade patterns during that period.
Totally, and thank you for this comment. And probably you need to put everything down. I mean, glass as a material, other materials, all the socioeconomic activities during this period, so as to combine everything to give a right answer, because as you said, probably it was a very complex, let's say, activity, the trade from Egypt and Mesopotamia and Levantine coast to Greece. So yeah, sure. Thank you.
Thank you, James. It was really interesting. I have a question on Filippi, which is the strange case in northern Greece. Are you sure that sampling was representative? No, because it could be also.
Of course.
Due to the typology that you selected.
Exactly. This is a factor that apparently you cannot be sure, even with what I have done in analysis. Probably there are more, let's say, Levantine glass in the sites I have sampled. So this is something that you have to take it into consideration for sure. I mean, maybe this is the answer because they have so much Levantine glass there.
I don't know.
Yeah.
Okay, thank you.
Thank you.
Just time for one more quick question, which happens to be mine.
Okay, yes, please.
Is that you mentioned the possibility or likelihood, in your words, that you've got some plantash glass.
Yep.
But to my mind, those levels purities are a bit low. Could it be that they're mixing plantash glass with natron glass? Have you any evidence for that?
Could be an explanation, but I'm not that sure if the other data, the trace element data, suggests so. So I believe that most likely it's something has to do with plantashes, but because they're in a very marginal, you know, in the graph, in a very marginal position, maybe something strange happens there as well. I mean,
because in Northern Europe,
they do it a lot.
They get all kinds of mixing going on.
Yeah.
In the late antique period.
Who knows? I mean, the trace elements that are associated with, with recycling and with these activities are quite low. So I don't think there was a lot of recycling. So it seems that it was quite pure glass.
Yes, you're closer to the primary source.
Yeah, exactly. Yeah.
Okay, thank
Perfect.
you very much.
Thank you.
So, good. So you, Dr. Rumyan Seva and colleagues, glad you're here. We'll talk about glass at the turn of the millennium, glass supply and glass working practices in the periphery of Byzance, a case study of window glass from Vesaloyi, northwestern Caucasus. Please.
Thank you very much. Dear colleagues, dear members of the organizing committee, thank you very much for this opportunity to present here the results of our research, which is a honor for us. So now we will move to the Northern Caucasus. It's the South Russia. And I will speak about the case study of the church near Veselaya. The church near the village of Veselaya was excavated in the vicinity of the city of Sochi in the northeastern Caucasus, near the Black Sea littoral. It was built in the 10th century AD and could be active till the mid-11th century at the latest. From the 8th to the 11th century, this territory made part of the Abkhazian and then of the Abkhazian Kartli kingdoms, being under the strong influence of the Byzantine Empire. The Christian churches known in the region could have been erected here by Byzantine builders, possibly from Trapezund. The church near Veselaya is a cross-domed church having 4 internal piers with 3 apses and a narthex. During the excavations, 2 layers of floor at the altar have been unearthed, suggesting its renovation. Near 1,100 fragments of oculi, blown window panes, were found mainly in the at the north, western, and south walls of the church. First of all, around and within the porches, about which the window openings should be situated. Near a half of window pane fragments are made of colorless and naturally colored glass. The others are made of strongly colored glass of purple, cobalt blue, emerald green, light blue, and olive glass. Some of colored window panes were blown using a deep mold. They are here. So they have relief. It's so-called optic decoration. The parallels of them are well known on the Caucasus, south to the region under discussion, in Abkhazia and mainly in Georgia. They are believed to be manufactured in Georgia. The first study of the chemical composition of a small series of glass from Veselaya have been undertaken just after the excavation campaign with optical emission spectroscopy. And last year, we have got the opportunity to study a representative series of samples with SIM, EDS, and LR-ICP-MS techniques, the first results of which I will introduce in this paper. 63 samples have been studied with SEM EDS, 21 of them also with LR-ICP-MS techniques. The sample set includes a series of glass of each color fouled as a site, taken from all 5 locations near the church. Window glass from Veselaya is especially interesting because the church was built and glazed in the period of fundamental transformations taking place in the glass production, consumption, and supply in the later 1st millennium AD. Early Islamic glassmaking centers in the Eastern Mediterranean survived at the time the transitions from natron to plant ash production. In Western and Central Europe, due to the lack of the imported raw glass from the East, craftsmen recycled the Roman and the late antique glass before the transition to the wood ash recipe. Nevertheless, from the late 10th to or slightly later, the Levantine plant ash glass was also imported to Asia Minor, the Byzantine Empire, and to the lesser extent to Europe from the 9th, 10th to the 11th century. Here I reference to the book by Nadine Shebil, where the latest research data on this subject was summarized, obtained by different researchers which was working with the materials of this time. The glass established from Visiole reflects the model of glass supply to the North Caucasus, the north periphery of the Byzantine world. All the studied samples are of the soda-lime silica glass, both with low and high content of magnesium and potassium oxides, which are in positive correlation. The base composition allows to single out the clusters of glass related mostly to the color. These clusters likely reflect different primary origin of glass and possibly different glazing campaigns, as well as, and first of all, simply different glass batches melted for coloring glass, especially for the Visiole church. The archaeological data confirms that the church was renovated at least once, while 2 layers of floor have been discovered in its altar part. The same clusters are observed upon the LR-ICP-MS data. There are 2 glass types in the sample set. The first is a very homogeneous colorless plant ash glass. The second one is low aluminum, high lithium, high boron glass. It includes the samples of naturally and strongly colored glass. The glass of such composition was likely derived from Western Asia for the Byzantine period by now, but indeed it's low in boron concentrations, so it's possible it's also can be of another origin, possibly also from Iran. But anyway, by now, according to the results of the research, the finds of such glass are connected to the territories within or neighboring the Byzantine world. In the glass of the second group, the concentration of lithium and boron is very variable. Lithium, boron, potassium, and magnesium are positively correlated. The strontium, barium, zirconium, and titanium contents and ratios are also variable and always demonstrate the same clusters of samples related to the glass colors. Further, I will focus on the base glass composition of the groups and on the secondary practices, first of all, on the recycling markers. So, colorless window paints represent a chemically homogeneous group of plant ash glass, decolorized with manganism. The peculiarity of the base and trace element composition, first of all, the concentrations of magnesium and potassium, moderate for the plant ash glass, along with low content of titanium and zirconium, suggests its Levantine origin. The samples of this group, subjected to LR-ICP-MS analysis, feature very low content of the recycling markers, suggesting the use of pristine raw glass, or at least very careful selective recycling. 2 groups of naturally colored glass differ considerably as regards to the base and trace elements composition, as well as recycling markers. One of them, this one, features the highest in the sample set content of lithium and boron, as well as extremely high strontium content. Magnesium and potassium concentrations are also high for the glass with high lithium and boron. The level of recycling markers is very low, suggesting the use of pristine raw glass. Only the antimony content is high, more than 50 ppm. According to the research by Patrick de Gries with his research team, for the Netron glass, based on sand from the European Mediterranean shore, the content of antimony cannot exceed 30 ppm, but possibly for the sources from which this glass, raw materials for which glass originate, is higher. And the low content of other recycling markers in the glass under discussion strongly suggests it. Moreover, antimony content is also rather high in some of previously published lithium high boron glass. The second group of naturally colored glass is here. Is low in magnesium and potassium content, which is below 1%. Such concentrations are more typical for the netron-based glass. The content of lithium, boron, and strontium is much lower than in the first group of naturally colored glass. At the same time, the level of high transition metals is high, suggesting extensive recycling. It is tempting to assume that this glass is a result of the recycling of naturally colored glass of the first group, but it doesn't seem likely because the lithium to boron and strontium to barium ratios differ for the glass of these two groups. One more group consists of light blue glass with deep mold blown decor. It is also high in magnesium and potassium concentrations, but differ considerably by the lowest content of calcium, strontium, and barium, along with high concentration of zirconium and titanium, suggesting another primary origin. Its trace element pattern, excluding high lithium and boron content, is more typical for the Egyptian glass, but this composition finds no parallels among the glass of the Egyptian plant ash groups from E1 to E4 after Nadine Shibil. It should be stressed that the deep blown glass of another colors compositionally differs from the light blue. And for the moment, we cannot explain the nature of this variability. The last group that I would like to discuss is the strongly colored glass comprising cobalt blue, purple, olive, and emerald green samples. These samples demonstrate high level of recycling markers, with the exception maybe of cobalt blue glass, where the same elements could characterize the cobalt source. The presence of near and more than 100 ppm of antimony attested in 4 samples of emerald green glass is usually considered as the secondary use of Roman glass, while antimony was used as an emulsifier and decolorizer up to the late 4th, early 5th century at the latest. Purple and olive glass contain elevated concentrations of copper, tin, and lead, likely suggesting the addition of the translucent window glass of colored and possibly opacified callet. Tin replaced antimony in the 4th century. It could suggest that the callet used in production of the purple and olive glass could be dated to the later period than antimony-containing callet used for the emerald green glass. In deep blue glass, the ratios of cobalt, nickel, and zinc is also typical for the late antique, early Byzantine, and possibly a bit later, early Byzantine period and possibly a bit later. Compared to high lithium, high boron cobalt glass of bracelets from South Central Anatolia of the 12th centuries AD, of the group 3 singled out by Caroline Swan with co-authors, the cobalt zinc ratio is high in Vesuvius, but it's really difficult to to compare these groups because in the publication by Caroline Swain, it's moreover light blue glass with lower concentrations of cobalt. So it should be another group. As it was already pointed out, some of naturally colored glass, namely the group with elevated recycling markers, and of strongly colored glass contain less than 1% of potassium and magnesium oxides, which is not typical for the high lithium, high boron, so-called Byzantine glass, containing as a rule between 1 and 2.5 of these oxides or slightly higher. It supports the hypothesis that natron glass of the earlier period could have been added to the batch. This praxis has been widely attested for the European side of the later first millennium, where the earlier structures, possibly containing Roman mosaic tessera, were used as a principal source of raw materials. The monastery San Vincenzo al Valturna, published by Nadine Shibili and Jans Freestone, can be mentioned here as an example. So, conclusions. The glass for the window panes for the Church of Veselé originates from the Levantine region, colorless, and likely from Asia Minor, strongly and naturally colored, or possibly from another region, but it's related to the Byzantine Empire. All the glass, plantage, and high lithium, high boron should be supplied to the Caucasus through the Byzantine Empire. The clusters of glass singled out for the same set, for the sample set, and evidently related to separate glass batches indicate likely the manufacturing window panes for the church by commission, probably locally, using the imported glass. It can be tentatively assumed that 3 sets of uncolored glass, 1 colorless, and 2 naturally colored, differing in composition, are related to at least 3 different glazing campaigns of the church. Unfortunately, we cannot rank them chronologically by now. Byzantine craftsmen working with the glass of probably Byzantine origin used the same strategies than the European glass workers in a slightly earlier period. We can see the evidence for an extensive glass recycling for some groups. Low magnesium and potassium content in some groups of glass could suggest that it was melted with the earlier natron glass collected elsewhere in the form of cullet. The Byzantine high lithium, high boron glass features a very high compositional variability, as it has been already stated earlier by researchers. Thank you very much for your attention.
Thank you very much indeed for that very interesting talk. Any questions? I have anybody? Please.
Thank you for the talk.
you.
And I just wanted to ask if you happen to know of any shipwrecks in the Black Sea that transported colors potentially for the recycling.
In the Black Sea, no.
In the Black Sea, not
The
really.
only one shipwreck that I know it's Serce Limani, it's near Turkish coast.
Yeah.
No, unfortunately.
Not in the Black Sea. Okay, maybe we have to look closer.
Thank you for your presentation. I was wondering, do you have any evidence for a glass workshop nearby the church?
No,
No.
we don't have.
You don't.
So it could be imported in the already finished
Yeah.
form, but it's also possible that elsewhere near the church it would be convenient. In Georgia, we have some evidence of, so it's to the south of Sochi. We have some evidence of glass workshop of the medieval time, but it's rather old excavations. It's very difficult to say exactly what it was.
Thank you.
I have a quick question. Do you remember what the aluminium levels are in your boron glasses?
Aluminium, the level of aluminium, it's from 1.6 or 1.8 up to 3.3 for the samples for which we have already ICP-MS data, and we have one sample with 4% of aluminium oxide. But for the moment, we unfortunately don't have ICP-MS data, but it seems to be also to belong to this group. So according to it, but it's the highest, at the highest.
Because Nadine Shibilla published that initial paper in 2011 where she identified late Byzantine borate glasses, and they're characterized by pretty high levels of aluminium.
Yes, Nadine Shibilla published with glass with high aluminium, but in the publication of Caroline Swan, there are also low aluminium, high lithium, high boron glasses.
So it's really an intriguing situation. What it all means in terms of production centers and so on.
Yes, they are very different. So it's very heterogeneous compositions.
Sure. Okay, any other questions? Right, thank you very much indeed.
Thank you very much.
So our next speaker is Dr. Frenken and Thilo, co-authored by Thilo Rarin. 10th to 11th century glass workshop in Astrakhan, Uzbekistan, a case study to understand early Islamic vantage glass making. Peace.
Yes, thank you very much for the introduction. And again, not a doctor yet, working on that, but hopefully. So I'm presenting to you the early stages of my PhD, focusing on the case study of the workshop in Aksiket, a plant ash glass workshop of the 10th to 11th century, early Islamic in Uzbekistan. Just a leisurely afternoon stroll away from here, about 5,500 kilometers in the Fergana Valley, situated between vast mountain ranges. And this Google route here illustrates very nicely the first point I will try to make, and that is that our today's roads still follow a lot of the networks that were already established with the Silk Road. And we can really see here that we are trying to avoid mountain ranges. I don't know if the pointer is active here, no. There we go. Especially around the Caspian Sea and then through the Fergana Valley and into the Chinese territories. And these northern Silk Roads, note I'm saying Silk Roads here, not the Silk Road, because it is really a network of different routes divided into a northern and a southern part. And they are distinguished by one very important thing, and that is the mode of transportation. The southern maritime Silk Roads were largely traveled by ship. Ships were engineered to tolerate great depth and high humidity, and they needed a lot of ballast to function properly. So glass-colored and raw glass traveled happily alongside the ships, not so much with the camels that have been engineered by nature to tolerate great heights and high aridity. They can carry a lot of load, but they don't necessarily need extra ballast just to function. And this importance of the split into the northern and the southern maritime roads, we can also see linguistically when we look, for example, at the word for tea or chai, as it called also in the Greek language. For glass specifically, it didn't really travel all the way along the Silk Road. There's this recent publication also by Nadine Shibil showing that we have glass groups, chemical glass groups from the Iranian plateau being traded among different sites in Iran, but very rarely traveling westward into Mesopotamia. The other way around, it is not so rare. Perhaps this is due to the specific groups that we're looking at here. The S1 and S2 groups are famed for their clarity. So we're looking at really specialty glasses here that are clear and not colored, generally speaking. So glass seems to move eastward along the Silk Road, at least in small steps. One problem with this approach of provenancing in this Central Asian region is that we don't really have primary production centers very frequently. We have this example from Herat, which I took into consideration, although this is more of an ethno-archaeological example based on a documentary by a young and dashing Robert Brill, still available on YouTube through the Corning YouTube channel. Highly recommended if you're interested. But I'm trying now to put Axiket on the map as a production center. But more importantly, with my PhD, I will try to move beyond provenance and look at other potential research questions that we can ask to a region where this model of provenancing doesn't really seem to work quite as well as it does for the natron glass in the Levant, where we have big production centers and we can really trace the trade routes very well with this method. So about Axiket. It is a site in the Fergana Valley, as I already mentioned, an oasis town, very important for traveling along the northern landlocked Silk Roads, to have regular stops to refeed and restock on supplies for your desert ships. And the site is divided into a small little citadel, a rest of it that hasn't been eroded by the Sirdarya River yet. And then an inner Sharistan city with the workshop located here near the wall. And then in the outer city, near the Rabat, the so-called industrial quarters, we have a nicely stratified dumping area that we can use to trace changes in potential glass recipes over time, hopefully. The site has been, or the region as a whole, is defined by a very tumultuous history. The early Islamic conquests were even earlier than the era that I'm looking at, the period that I'm looking at. But the region really started to increase urbanization and also industrialization during the Samanid dynasty in the 8th to 10th century. The Samanids were then followed up by the Karakanid state, which then split into an eastern and a western part. And then the Seljuks conquered part of the western Karakanid states. And then the Khwarezm conquered the whole region again and united it. Not for very long, because the last ruler of the Khwarezm Empire made a grave mistake and attacked a Mongol trade caravan, and then also killed an ambassador of the Mongols, which they didn't take up very nicely, and ransacked the entire region and pretty much burned everything to the ground. So what makes Axiket a great case study for learning about glass technology? We have this hub along the Silk Road where technologies were exchanged, where goods were exchanged, where people were exchanged. It is on the edge of the Islamic expansion to the east, so potentially we can even see contact with Chinese glass technologies, which are very different from the Islamic ones. We have here a center for pyrotechnology because we also have very highly sophisticated crucible steel production with beautiful standardized crucibles. And we also have glazed pottery, lead glazed pottery, by the way. And we have this well-stratified dumping area and a glass workshop with working debris, furnace fragments, and frit. This is about what the assemblage looks like. So we have ceramic pieces attached with a glaze on it, so furnace fragments. We have some raw glass chunks with and without ceramic attached to it. And we have some frit samples as well. I don't think you can see one here in the image, but I will show one later. What we do not have is in situ structures, like you can see here from Al Raqqa, but you can sort of tell the resemblance where you have ceramic pieces with layers of glass still attached to it. And whether this was the primary produced glass or just an incidental glaze that happened during the firing is still open for debate, at least in my area. What we know is that we are looking at a structure that combines brickwork and an organic tempered clay. This is from this diagnostic piece, what I can tell so far. But as I said, we sadly do not have in situ structures. We do have a lot of aqua blue working debris, ranging from fluidity tests and something that may be trimmings from working glass vessels. So I will try to look at the local entanglement and the chain or patois. Looking at the time here, I'm only going to glance over this. But I mentioned already that I'm trying to ask research questions that go beyond provenancing. And now I will finally show you some of my frit samples. You can see two examples here, very highly porous material, whitish in color, and generally with a at least very thin layer of glass on the top. Under the electron microscope, you can see the porosity gives ample ground to corrosion. And it is very difficult sometimes to find decent spots for analysis. Here I've focused on pretty much the entire areas that are relatively bright in color here, avoiding the cracks that are depleted in soda due to corrosion. But you can still see in the completely corroded areas residual quartz grains that have been eaten into and partially vitrified or partially dissolved in the glass melt, but not completely. So really looking at a frit here, not a finished glass. And as for the chemical results, we see the typical Central Asian relatively high alumina, varying in degrees though. We have a relatively constant amount of soda, potentially also related to the phase diagram and looking at an eutectic trough here where this collects in. What we do not see is the typical colorants associated with glass, except for one sample, which does have some manganese. And you remember that I showed you earlier one that had already quite a bit of glass on it. And this glass happens to be purplish reddish. So we can clearly see the manganese in there already, although it does not seem to be generally added already to the frit. That's as much as I can tell about this so far. And then for the future, I'm planning to perform more experiments looking into interactions between different fluxes, into time it takes until we reach this equilibrium state needed to produce frit or raw glass. And of course, I will also expand on the chemical analysis of the Axicat assemblage, looking into the furnace fragments, both with the intentionally made glass, but also with the accidentally made glass on it. And I'm hoping that I can also do some more actualistic experiments with real fire and an actual furnace, although the Cypriot authorities are not very fond of fire for some reason. So it's very difficult to do that on Cyprus. But with that, I want to thank, of course, the Royal Society and the Gerda Henkel Stiftung for providing initial funding for the excavation, and then the AG Leventis Foundation for funding my position as a PhD student, for funding the Starsea laboratories, and all of these nice people for helping me personally or helping during the excavation. Thank you.
Much for that very interesting talk. Any questions? I just wondered if you had any plans to examine your frits more closely. As you know, it's quite a rarity when the frit survives and you can identify it as frit. So I think it's the first bit of frit from Central Asia, to my knowledge.
I think so too. I haven't heard about any other frit from that particular region. There's of course Egypt and Fayence and all of this, but frit for actual glass making seems to be quite rare. So yes, I will look at this more closely. And studying also the ceramic that is still attached to it, looking into how the fluxes interact with the glass, and also trying to experimentally recreate the frit, most importantly. On that note, may I ask also a question? These frit samples, they smell like coconut oil, and I don't know why. If this is maybe sunscreen related from the excavation, but they've been already 20 years in a bag. But the smell is quite intense when you take them out. So I don't know what this is about, but maybe something for the audience, since we have also lipid people here.
Anybody know about coconut oil? I'm afraid I can't help there. We found in Raqqa, we found a lot of stuff that looked like frit, but turned out to be melted bricks, because bricks tend to lose, they start to vitrify and lose their iron-rich color. The iron-rich minerals become reduced, I guess. And then it's turn a sort of gray color, a bit like frit.
Yeah.
But so we're always very careful as to, the way, whether we really definitely had frit or not. Are you going to look at those silica inclusions in more detail, for example?
Yes, of course. I'm going to look, for example, if there's more feldspars that we can find. So far, they seem to be quite elusive, although the higher alumina content suggests that they may have been there, only melted first, or potentially we're looking at some kind of flux or interaction with the ceramic matrix that provides this alumina content. But as I said, I will try to experimentally recreate that, and we have quite low potash values in the frit for the Central Asian glasses. So this might be a corrosion issue, that even the areas that we did analyze are not completely uncorroded. We have to look into that, yeah.
Sure. But yeah, very interesting stuff. Any other questions? Okay, thank you very much indeed.
Thank you.
So is the next presentation online? Unless Dr. Cheng is in the audience. I don't believe so.
Hello? Can you hear me?
Yes, thank you. Good.
Hello, Julian. Nice to meet you here.
Nice to meet you too, yeah.
I need to share my screen first. Okay.
So this talk is entitled Interdisciplinary Study on Glass Ornaments Discovered from Chinese Port Site of Shuo Gate, 10th to 13th century CE. Please.
Thank you. Good afternoon, everyone. It's my great pleasure to participate the conference. I'm in Beijing right now, and it's a pity that I could not make a visit to Kalamata for this conference, but it's great that I can present the research online. Today, okay, so it is a collaborated research. The co-authors, my colleagues from the National Institute for Archaeology, Palace Museum, Wenzhou Institute for Cultural Relics and Archaeology, and the China Academy of Cultural Heritage. At first, I would like to give a context of the Chinese ornaments like hairpins. Ancient China is always regarded as the country of clothes and hair ornaments due to considerable archaeological finds that demonstrate the tradition of focusing on dress and hair decoration. Those artifacts reflect the practical use, social status, and aesthetic spirit of ancient Chinese people. Hairpins used for stabilizing hats or long hair, both for men and women, are one of the most common hair accessories in history of China. So even men have this kind of the hairpins. As earlier as the Bronze Age, hairpins made of bone, horn, and precious stone were widely used at different Bronze Age archaeological sites, which was dated about around the 10th century BC. During the Qing and Han Dynasty, between the 3rd century BC and the 3rd century CE, more precious materials, including gold, silver, animal horn, jade, and glass were selected for hairpins making. This is a map of China, but today I will focus on the Pacific period, the Song and the Yuan dynasty, which is between the 10th and 13th century CE. So this is a map of China. The glass hairpins have been discovered in these glass provinces, marked with red stars. Most of them are coastal areas. Those coastal areas, the glass hairpins have been found there. So typically, there are two types of hairpins. One is called fazan. It's a single stick with a decorated head and a sharp foot. And another one is called chai. It's a two-leg hairpin made in a U shape with two sharp feet. Both types were used to secure and decorate various hairstyles by crossing through the combed and strained hair. Although glass ornaments like beads or hairpins are frequently discovered at archaeological sites in China, glass workshops have never been uncovered and reported yet until workshop discovered in Zibo City, Shandong Province during the 13th century CE. And another thing is few scientific analyses have been applied on the glass finds. So I will give a context about the Pacific archaeological site. This is map of China. Here is the Wenzhou city. It's marked with the red spot. Wenzhou city is a coastal city facing to the East China Sea. When I enlarge the map, we can see the Pacific location of the Shuomen port site. The port site is located north of the Wenzhou city. There is a river called the Ojiang River flowing into the East China Sea. This site is located on the south bank of the Ojiang River. Local archaeologists from Wenzhou Institute of Archaeology have been excavating the site since 2021. The site covers the area about 5,000 square meters, and the length of the site along the river is about 400 meters. Archaeologists discovered loads of interesting architectural remains, such as water logs, land gates of the ancient Wenzhou city, 8 piers, 3 shipwrecks, 1 wooden plank road, and numerous porcelain shards. Those remains are dated from the Song to Yuan dynasty between the 10th and 13th century CE. It is also interesting to find that 17 pieces of hairpin glass fragments were found from the site. Although there are only 17 pieces, they can be classified into 5 different types in terms of color and opacification, which are opaque white, transparent blue, opaque blue, translucent light green, and opaque dark green. So we selected 5 representative samples for scientific analysis. Due to the limited and precious discoveries, the non-invasive and mini-invasive analyses were accepted by local archaeologists. So we applied 4 methods, including 3D microscope, laser ablation, ICP mass, Raman spectroscopy, and micro-CT in different laboratories. In order to access the reliable data of chemical compositions, we analyzed the reference glass by ICP mass, such as Corning BCD and the NIST glass. So the Raman spectroscopy and micro-CT were carried out at the laboratory in Palace Museum, where advanced instruments are specifically used for artifacts. So according to the chemical compositions were analyzed and presented for 57 elements in quantitative weight percentage and ppm concentrations using ICP mass. So these 5 representative samples have all of them have a rather high level of potash. You can see from the table, and the big difference is a sample TB contains lead oxide at a very low level, 0.35 weight percent, while the other 4 have considerable high level of between the 20 to 49 weight percentage. So the 5 samples could be classified into 2 types: high potash, high lamp silicate glass, represented by sample TB, and high potash, high lead oxide glass, characterized by samples, the other 4, LG, DG, OB, and OW. So as for the trace element analysis, among the 5 samples, there are compositional discrepancies, not only in major elements, but also in some mineral and trace elements, which were introduced into the glass crucibles accompanied with raw materials. The concentration of the elements, so those 5 in the 4 highlight glasses, are similar to each other, but distinct from those in the potash lime silicon glass, represented by sample TB. And it also consistent with the results of rare earth elements analysis. So when we talk about the possible provenances, according to the result of chemical composition, potassium nitrate could be it's like a 220 weight percent. It can be regarded as a flux, and the high percent of lime could be functioned as a stabilizer in the glass matrix, and both of them were added intentionally into the glass batch. It is possible that this type of the potash lime silicon glass from the Song Dynasty was developed by imitating the receipt of the soda lamp silicon glass and adapting it to the local raw materials. Since the rich raw materials could be obtained from local natural resources, it is likely that it was produced around the areas of Wenzhou city. As for the potash lead oxide silicon glass, it seems that there is different lead sources, but so far we don't know the specific range of this type of glass. There seems a tradition that Chinese craftsmen always produced high lead glasses over the past 3 millennia. During the Wall State period and Han Dynasty, which is dated the 5th century BC to the 3rd century CE, lead barium glass typically produced in China. And the use of lead barium glass gradually declined, with a high lead glass emerging during the Tang Dynasty, dated between the 7th centuries and 10th century CE. And then the lead potassium glass were made between the Song and the Yuan Dynasty. Okay, next I would like to talk about the micro-CT result. Before I talk about the micro-CT analysis, I would like to mention the different part of the hairpins. Many archaeological finds have given us the impression of the integral glass hairpins. The hairpin then can be roughly divided into 3 parts: the head, body, and the foot. And the hairpin chai has a curved head, like a U shape, which is different from the fazan, the hairpin fazan. The head part is always held by hand when it is inserted into the hair. The foot part is sharp and nail-shaped to smoothly across the hairstyle. So in terms of the different shape, the 5 fragments can be classified into 3 groups. The body part for the sample LG and TB, the head part for samples OB and SG. So yeah, so on the left side, this image shows the sample LG and TB, the micro CT image of the sample LG and TB. And in the middle, that's the hairpin's foot image. And on the right side, that's the image of the OB and the SG. So because they have the little bit the curve shape, so it's probably the chai. In terms, so the figure on the left side illustrates the sample LG's cross sections and the longitudinal micro-CT image. Those holes showed in black color indicates the presence of deformed air bubbles within the glass matrix. In the cross-section image, the bubbles appears as regular round shapes, while in the longitudinal image, they present as extremely long and slender outlines. This might indicate that before the glass annealing process, the hot and the soft glass was deliberately stretched into long and thin sticks in hairpin molds. It is also the same situation to bubbles in other samples, like OB, OW, OB, and SG. It is intriguing to observe that the image of the right image displays 2 long bubbles following the curve of the head, which could suggest that the hot and the soft glass was stretched at first and then was bended and makes the craftsman made the U shape.
You have 5 minutes to go.
Oh, sorry. So this is this slide. I want to talk about the colorant and opacified. I just want to give a quick example. So the sample OB is the blue and the opaque glass fragments. So the copper oxide is 1.6 weight percentage, and by Raman spectroscopy analysis, we found a little bit peaks here, which is matched to the peak of fluoride. So probably this glass have the opacified using the fluoride. And generally, the hair accessory were found at part of the funeral suit. It is the first time to excavate this type of glass ornament at port site. The assemblage from this port site with the 5 different visual effects suggests that more glass hairpin commodities similar to these finds were possibly transferred into or out of ancient Wenzhou city through this port. So these glass pin finds should be regarded as commodities rather than personal belongings. Okay, so my conclusion, the hairpins are divided into two glass types based on their chemical compositions, and it's very possible that those 2 types was made in China. The glass potash lime silicon glass type was influenced by and imitated the soda lime silicon glass, and the potash lead silicon glass type was inherited and modified from traditional lead barium glass of the Han Dynasty and high lead glass of Tang Dynasty, spanning the first millennium BC to the first millennium CE. It also probably suggests that they were likely commodities rather than funeral items usually found in the tomb site. And those 2 glass ornaments was possibly produced in local workshops near Shoregate Port and exported to other range of China. And there's still some questions, and we need to further explore to research. So first, we don't know where are the specific workshops for those 2 2 types of glasses, and more scientific analysis should be carried out on other glass ornaments so we can compare to each other. An accurate result on chemical composition of the weathered glass will be more useful for comparison. And the lead isotope need to be applied to trace a possible range of high lead glasses. There's also some institutes to provide technical and scientific support, and it was funded, the research funded by National Natural Science Foundation of China. And thanks very much for your attention.
Thank you very much indeed. Are there any questions, please? I've got one for you. As far as I remember, there's a production site, Song Dynasty production site in Shandong, where glasses are classified with fluorite have been excavated and probably made. I just wonder if whether you've thought about comparing your data with those.
Yes, actually, yes, it seems to be a traditional Chinese manufacturers to use fluoride the fluoride could be added into the glass batch for the opacifier. Yes, because we always have many other discoveries or scientific analysis from other glass finds.
Sure.
One of them is from the Shandong Zibo, the glass workshop there. Yes.
Yeah, because I think
yeah,
that's the only example of a glass making site in China that I've come across, at least in Shandong.
yes, that's so far it's the only glass workshop discovered in China. and
Yeah.
in Yuan Dynasty, 13th century. So it's quite, even it's later, the workshop, the period of workshop is later than the archaeological Schumann port site. So it's hard to say, to confirm that the glass could be produced in Shandong and were transferred to Schumann, to Wenzhou city. No, I don't know. It's hard to see that.
Be interesting if you find there are different compositions and can suggest that there's a separate production center for your glass.
Yeah.
Yeah.
That's because the other people, they already published some scientific results, but we obviously use different methods, and they use the XRF, and they always get some the result from the weathered layer of the glass, or so it's hard to compare to the results to each other. So yeah, so we need more scientific research on this type of material.
Yeah. Any other questions, please? Okay, Xia. Bye-bye.
Thank you. Thank you. Bye.
So our next speaker is Dr. Doris Monka, and her talk is entitled Remembering Nikos Zacharias, Introducing Me to the Field of Archaeometry, New Friends and Fascinating Glass Problems. So Doris is based in upstate New York, so presumably that's where she's speaking from.
Yes. I don't know, can you see the screen? Because...
Yes, we can, thank you.
Okay, and I hope it's moving forwards too.
Yeah.
Yes, unfortunately, I can't be in Greece right now, which I would pretty much prefer to our midterm exams, which are this week. We're in the middle of the semester. But yeah, perhaps I can actually answer some of the questions Julian started at the beginning, because I will also talk about some bone containing late Bronze Age glasses. And it's mostly about how Nikos got a glass chemist like me really involved into the study of archaeological glasses. So I don't have one nice story like all the other presenters in the glass session, but being based as a glass engineering institute, we have other techniques available. And while I get my funding for modern industrial glass research, we just started some more archaeometric studies, and I will talk a little bit about those as well. But first, how I got involved into glass. So I studied in Germany. I ended up at the Glass Institute, Glass Chemistry Institute in Jena. And then I spent 4 years in Athens, Greece with the National Hellenic Research Foundation. And because being in Greece and seeing all the archaeological glasses in the museums, I asked who is actually studying that. And Stratos knew Nikos and got us into contact. And very soon after, Nikos invited me to the second ArcNet conference just to listen in. And yeah, I haven't stopped playing with old glasses since. I returned back to Germany, and it's a very different glass research on historic glasses there. It's more the medieval glasses. I spent a year in Sweden, and there is another glass problem we started with, which we haven't quite stopped. We're still on it, and now I'm in upstate New York. Corning, the Museum of Glass, is just 45 minutes from us. So we are now collaborating with them on some old glass findings and studying those. So yeah, I mentioned some of these things, being in Athens, starting with collaboration with Nikos, and very briefly after just when I returned to Germany, I got a PhD student who was funded on archaeometry project. So we had a lot of collaboration with Nikos and Eleni and Maria at that time. And I will talk about some of his findings. And so the first case study I'm presenting, that's a Mycenian glass piece, the first samples I got from Nikos. And when I measured them with infrared and Raman spectroscopy, which aren't the usual techniques used in archaeometry, but that's what I was doing in Athens. And that's a technique that tells us a lot about the structure of glasses. So the red spectra on the left, that's the 3,000-year-old glass pieces I got from Nikos. And they look like a Pyrex glass, like a modern borosilicate glass in infrared, which we didn't expect. And we remeasured, and front side, back side, it always was the same thing. So the blue spectra you see here in the middle, that's the Duran type, Pyrex type low alkali borosilicate glass, as you know from chemical labs, and the thermal shock resistant glasses you might use in your own kitchens. They have this band at 920, 950 centimeter minus 1, which is absent in pure silica. Otherwise, a fully connected network, which is rather strong, low coefficient of thermal expansion. And the model glasses, they have a band at 1300, but that's a trigonal boride unit, which is very prone to corrosion. And the modern glass pieces I had, which were 10 years old, they didn't have this band anymore at 1400, 1300, like the Mycenian glass pieces didn't have this band. When we took not the nice surfaces on the Mycenian fragments, but on an old breakage where we could probe more the bulk of the sample, that's shown on the right-hand side. We got this blue spectrum, which is representative of a very depolymerized corroded glass piece, more like modern bioglass, a lot of Q2 units that silicate tetrahedra with 2 bridging and 2 non-bridging units. So that's reflective of a broken up network. So here are some references of materials with known structure and composition. And you see on the red one, that's pure silica, all bridging oxygen at each silica tetrahedra. And that looks very much like the orange spectra on the right from the Mycenian fragment. Only that the band at 950 is missing. That's the BO4 assignment. The green one would be just from the composition, the analyzed composition of the Mycenian glasses, a typical soda lime silicate glass, a lot of Q3 units, so 3 bridging, 1 non-bridging oxygen. And as I said, the blue one is a reference glass, the bioglass, a lot of depolymerized species, as we see on the old breakage of the Mycenian glass. Of course, we didn't break the nice fragment you see here in the center to get a fresh bulk glass composition. That's easier with our self-made glasses where we can destroy them for all kinds of analytical techniques. I had presented that at the Boride conference at that time. On the right, that's in Halifax at the Boride conference with Stratos Kamitsos. At that time, I was doing all the infrared and Raman measurements with him. And then we had Ferdinand Drüner trying to replicate those glasses in the lab. And so our idea on the introduction of boron was that inside the glass, we didn't find elevated levels of boron. When I talk about low alkali borosilicate glasses, they have 4%, I'm talking mole percent here, 4% sodium oxide, but up to 15 to 20 mole percent boron oxide. So that's a different boron level than what, the archaeological studies of high boron glasses mean. We only see this boron peak in the outer layer of the glass. So what our idea was that because most of these Mycenian fragments, or many of them, had been gilded at that time, or have this gold layer around it, goldsmithing is a trade or a craft that uses boron. They do know that you can purify gold-containing ores to get the gold out of it. Actually, that's the environmental friendly alternative to the mercury amalgam technique. And so to avoid the gold from oxidation while you handle it at high temperature, goldsmiths used boron for a long time to do that. And so perhaps they also used the boron to help with the attaching of the gold layers to the blue glass fragments. And then we get a surface reaction between the borax and the glass, and a very fine borosilicate layer might form. The problem with boron is that it's such a light element that SEM XRF doesn't readily measure it. So it's overlooked by a lot of techniques. Now that we use more and more laser ablation ICP-MS, we suddenly can measure the boron content. In our glass fragment, if we only have boron in a thin layer, and it's a light element, SEM XRF will not see it. And with the infrared and Raman measurements, we have some ambiguity if it's the band I'd shown you before, where I think it's boron, if it's actually boron or water. We tried to go deeper into that with replicates and original measurements with neutron tomography. So neutron absorption is very, very high for boron. If you have boron 10 in your glass, and we thought if we just have a very thin layer, we actually will see the boron layer outside. And for the replica, that's all the dark spots on this soda lime glass we had treated with the borax coating on the outside. That actually works really nice. Only with the old samples, it's the problem that the water has a high scattering, hydrogen has a high scattering for neutrons, and boron a high absorption. So on the corroded old glass samples, it wasn't sure if we see the water or the boron. So because of this collaboration with Nikos and the Mycenium glass pieces, we had been in Willingen and doing this neutron tomography experiments, and which is being at one of these synchrotron national labs, it's very impressive measuring there at the night. And then because of the neutron radioactivity, you had to make sure you are not contaminated before leaving the building. And so yeah, I wouldn't have been there without this project. So I really got a lot out of working with Nikos. Here on the right, we see the tomography on some really old samples. But as I said, it wasn't the solution we hoped with this measurement. I'm now close to the Corning Museum of Glass. They do have late Bronze Age Mycenium glass samples. We are just in the process of getting samples released to us. We will have infrared microscopy here, so we will find the same peak as before. And infrared also sees water bands. And the original measurements, they didn't have significant water bands, but this boroid band. So if we see that in some of their samples, we can actually go to Corning, the company, and do boron NMR, which is a very, very boron-specific technique. There's no interference from other elements. And then we can be totally sure that we have the boron in our glass. With solid state NMR, we don't have to destroy the sample. Usually we powderize all our modern glasses when we do NMR. There we don't have to do that if we use solid state. Even so, the quantification isn't as good as with magic angle NMR. So this, Mycenium, that's the oldest glass piece I worked with. We continued on colored glasses with Nikos, so he gave us a lot of Roman glass tesserae. And so optical spectroscopy, Raman spectroscopy for the pigments. That got some really nice papers. And so the one was Roman glasses colored by dissolved transition metal ions, redox reactions, optical spectroscopy, and ligand field theory. A nice review on how to apply ligand field theory to get as much information on dopant speciation, coordination, concentration. That came directly, and actually, yeah, Nikos is a co-author on that paper. And that was his prequel for a chapter in the Springer Handbook of Glass, which I wrote with Dominique Deligny on colors in glasses. So it really, there's all kinds of overlap between the working with the old glasses and my modern glass studies. Yeah, after 4 years, I was leaving Greece and I went back to Germany. Of course, they don't have this culture of historic studies. It's much more a non-profit group of very interested people, everything from private citizens to some archaeology professors, so like Peter Stephoon in the middle. He was overseeing an excavation of medieval glasses in the Taunus, and I currently have 2 kilograms of those medieval red glasses in Alfred for some studies on the kappa redox reactions, the microcrystals that cause an opacity, the melting behavior, viscosity, which is very puzzling in a way. If we remade the red glasses, they turn green and transparent. And so, yeah, that was a different community in Germany. And they have this Roman reconstructed glass furnace, for example. And Ferdinand, as part of his PhD thesis, he was remelting glasses there, trying to recreate the antimony opacifiers of the Roman samples from Nikos. So there were still some German-Greek collaboration quite a bit, and really fun playing with these old furnaces. And now in Alfred, we have a very strong art department with gas-fired furnaces. So we are much closer to the actual melting conditions of old times. We also have our own wood-fired furnace, which the art professor rebuilds every couple of years with the art students. And we have a glass art engine where half the students are from engineering and half the students are from art, and together they work on art projects, which is really fun. And recreating these old colors and aventurine and effects on glasses is something we can really motivate all the students to play with.
About minutes.
Okay, I try to be quick on the. So after these I talked about the kappa glasses and all the color changes we can see there. At that time, I joined the SGT in England. They have at the engineering conferences always an art and history session, which is, I think, very, very nice to have this interaction between modern glass scientists and engineers and the artists and history and archaeologists on the other side, which gives all kinds of synergies. At that time, Nikos was visiting us in Jena, and we stopped at Lambert's, where they do the antique glass. So they blow cylinders, cut them open, make flat glass for church renovations, for cultural heritage, but also artists. On the right, Nikos is testing one of the glass melts if it's ready to go with viscosity. Of course, there were the conferences in Greece, where I always love to come back to. As I said, my first meeting with Nikos was actually at the second ArcNet symposium. I'd been fortunate enough to come back to the masters a couple of times. Then in 2022, we had the International Year of Glass, and a lot of engineering conferences invited artists and now had history sessions connected with it. So in January, there will be the International Congress of Glass, next January in 2025, with a very strong art and history session. Tomorrow we are going to the Material Science Technology Conference in Pittsburgh, which also has a archaeology, art, and cultural heritage session every 2 years, which is really nice to interact and have this interdisciplinary collaboration. I now have as I said, I have a PhD student looking into the Mycenaean glasses. Annika has actually a degree in art conservation, and we tried to finally publish the paper we presented at the conference in Athens in 2011. Some of the work just takes longer if you're distracted by modern glass science. Yeah, I'm skipping over this, the low alkali, high aluminum glasses I started in Sweden because we don't have really conclusive results. But yeah, this shows what Annika is actually doing in Athens, in Alfred now, in addition to the Mycenaean glasses. It's her main field is the Frederick Garder Arene glasses with this coating of tin oxides. And so we look into the structure, into the layering, and not just the composition, but Raman, infrared, and all other kinds of studies. And yeah, finally closing the loop to Greece. Just this summer, I got samples from the Jena painter from the museum in Jena with this black and red ceramics glazing. And we're looking in the redox ratio. And I know that there has been quite some studies in Greece, also with the National Hellenic Research Foundation. But yeah, crossing between Germany, America, and Greece. And in a way, it was Nikos and all his connections, and also being like me, but coming from physics, or in my case, chemistry, and then interacting with all the archaeologists and archaeometrists, which gives a really nice site, research options I never had if I had stayed only with fundamental glass research. Thank you very much.
Thank you very much. Yeah, so another person who's benefited enormously from Nikos and his very high level of encouragement into the academic world. Any questions? Please.
Very interesting presentation, in particular about the possibility to have, let's say, 3D reconstruction of the boron composition using neutron tomography. It's not actually a question, just a comment. You are absolutely right about SEM-EDS and X-ray fluorescence for the elemental detection of boron. But there is also another possibility for non-destructive analysis of boron down to parts per million region using particle-induced gamma ray emission using a particle accelerator. So in this technique, you're using an elastic scattering from boron 10 and 11, pp prime gamma, and you are detecting gamma rays coming from, let's say, from excited nuclei of boron 10 and 11. And it has been confirmed, and it has been used also for boron analysis in many laboratories. So all the scholars are invited to use the tandem accelerator in Demokritos for measuring boron in glasses from Mycenaean glasses and any other typology you would like to test. There is an external beam set up, so you don't need to put your samples in the vacuum. And this technique has been already, I mean, it's a well-established technique. It has been used a lot in Aglaé, in the Louvre Museum, in the accelerator, and in other laboratories for boron analysis. So.
Yeah, you're absolutely right. Actually, the original bulk composition from these glasses, where we later saw the boron peak in the outer layer, Nikos gave us the PIG data with it. So seeing that the bulk didn't had considerable amount of the boron. So we think that I can't exclude that there might not be traces of boron but there wasn't enough boron in the glass to give this strong boron signal we see with infrared. So we think that, I don't know if how much boron is really in the bulk. It wasn't much, but outside in a very thin layer, we should have additional boron from this, some treatment on the glass. I think I also have a master student right now. She is remelting some of the Mycenium compositions and also going back to the original data. So she might actually be melting some glasses with 0.5% of boron, and then we will see how the infrared and Raman spectra look different. But I think the outer boron layer, which might be very, very thin, has much higher boron levels than the bulk glass in our case.
Okay, thank you. Any other questions or comments? Okay, thank you very much, Doris.
Thank you.
Well, that brings this session to a close. So thank you very much to all the contributors. As ever, it's been fascinating because it's glass.
We have the poster session now outside, so you can have a look at the posters and discuss them with the researchers that have created them. Ask extra questions to the digital MSc students. Also, if you would like, we have it's not exactly a museum, it's a digital application that we created with Professor Zacharias with the University of Peloponnese and the foundation of Captain Vasili and Carmen Konstantopoulou, which has to do with the liberation of Greece. It's the booth that's right behind the posters. It's a few minutes and it's like an interactive video. It's very interesting if you want to have a look. And of course, if you have time to go by the digital museum at the historic center, at the historic building of the City Hall is also a nice experience. And it has some selections if you want to see things in the city, so you can look at the interactive displays and maybe find some landmarks or something you would like to visit. And we'll see you again in a little bit.
Anybody in the audience presenter of this session? In order to give me your names. That doesn't sound good.
Hello, I'm presenting using the hybrid mode.
Hello, can you all hear me?
Okay, so let's start the 8th session of this amazing till now symposium, which is the 8th session is about digital applications in archaeological research. And I would like to really thank the organizing committee for giving me the opportunity to be a chairperson in this symposium. It's really honorable for me. The first presentation will be done online. It's called GIS Technologies and Systematic Excavation Projects, the case of the sanctuary of Apollon at the Amykleion near Sparta, Greece. So,
hello, can I share the screen? No.
Yeah, we can hear you. Hello, Nicola.
Hello. Can I share the presentation?
Yes, try to share your screen.
Let's see if I can get into.
Okay.
And can you see it?
Yes, of course. Yes. You may start. You have 20 minutes.
Thank you.
I will give you a warning 5 minutes before the 20 minutes arrive. So let's try to keep our timetable.
Thank you very much. So before starting the presentation, I wish to thank very much both the organizers of the symposium and the evaluation committee for this opportunity to present part of our work in this event. And I express this gratitude also on behalf of the whole Amyklis research project and the two my co-presenters, the project's director, Professor Stavros Lidos, and Antti Kyriodaki Vardi, who was in charge of topographical recording of the excavation this season. Our participation to the symposium, let me see if I can, yes, change the slide, in honor of Professor Zacharias is really truly heartfelt, since the work and collaboration of the archaeometry lab under his direction has been really pricelessly valuable to our project, as I'm going to show soon. So the choice of presenting our use of GIS at the Amykleion in this occasion wants to be from us a sign of real appreciation for Professor Zacharias and his work, and also of his collaborators who worked with us. But before getting into the topic, I'm going to spend a very few introductory words about the archaeological site of the Amykleion and at the heel of Agia Kyriaki. The identification of the sanctuary of Apollo Amyclaios on the hill of Yatiriaki, almost in the middle of the Orotas Valley, was confirmed by the discovery of roof tile stamped with the name of Apollo Amyclaios, and other inscriptions were mentioning the deity were found on the hill and in the nearby surroundings. The present state of the landscape responds to the description of Polybius that the sacred site lays in an area of extraordinary beauty and fertility, framed by the mountain range of the Taigetos to the west and that of the Paranas to the east. The importance of the sanctuary and the associated religious ceremonies of the Iakinthia is well documented by ancient authors such as Homer, Pausanias, and Athenaeus. And other testimonia also refer to cult activity in the sanctuary, which continued into the late imperial period. There are in particular two key references in ancient tradition that highlight Amyclae and the Amyclaion as important places in Laconia. First is mentioned in Homer, after which the Amyclaean moved in the ranks of the Achaeans against Troy. And second, it is particularly clear from the detailed description of Pausanias and Athenaeus that the importance of the site from the early Iron Age onwards was focused on the cult. Accordingly, the sanctuary of Apollo Amyclaios as a whole, and its temple, the Thronos, very famous Thronos, with its over 10 meters height cult image of Apollo, are among the factors that have shaped, together with the sanctuaries of Athena Kykos and Artemis Sophia, the religious and social life of Laconia and Sparta from the late Bronze Age to the end of antiquity. When the operations at the Amyclaion began in 2005 under the direction of Angelos Delivorias, GIS systems were quite far to be adopted as they are now nowadays as a standard recording and mapping tools. When in more recent years the research team felt the need to equip the project with a GIS platform, the choice went on QGIS. Out of the many reasons behind this choice, two are perhaps the most relevant. It is cross-platform that can be used on Windows, Mac, and Linux, and it's free of cost and open source, providing really powerful customization capabilities. And if I can open a brief excursus here, very brief, I urge GIS users and especially scholars to employ freeware software rather than their commercial counterparts, because it is, I think, responsibility of an academic environment to train students on the use of free software instead of creating sort of prospective customers for private companies. And differently from the past, the gap in terms of power, usability, and functionalities between QGIS and its commercial competitors is, I think, nowadays much smaller than it was in the past. So when the decision was made to adopt GIS at the Amyclaion, the main problem was not the lack of functionalities, in fact, but how to deal with the old documentation. And in particular, we had to figure out how to take data collected over 15 years without the GIS ecosystem and convert them into a fashion suitable for a GIS. Now, this preliminary process seems to be a minor issue, but instead it's not, or at least it was not really for us. It required, in fact, a rather accurate analysis of the state of documentation before being able to establish a solid translation strategy. In addition, not every piece of documentation one can find, not for every piece of documentation one can find well-established translation procedures. And in these cases, the GIS specialist, mostly me, had to find his way through, mostly by trial and mistake. Essentially, the documentation we had to deal with was made of excavation photographs, site plans, written documentation, finds inventory, and then also was a problem. I mean, it was something we wanted to do a thorough contextualization of the site in the surrounding environment. In addition to this, we put considerable effort into establishing an excavation workflow so that the new documentation could have been produced natively for GIS. But we will deal briefly with this problem later. For the moment, let us start by focusing on how we treated the old documentation by beginning from the excavation photographs. And there is a specific reason why we start from these photographs, as we're going to see now. On the past years, aerial photos were taken quite regularly to record the state of the site at the end of the season. Back at the time, we're talking about 15 years ago, only 15 years ago, not a century ago, drones were very early in their history and not very much adopted. And at the Amiclion, aerial photos were shot with a camera attached to a balloon. And of course, the only purpose of these photos was to provide images of the excavated trenches from above. And yet, even with any photogrammetric conditions whatsoever when they were taken, our recent attempt to produce 3D models and orthomosaics out of these old simple photographs yielded results much better than expected. And the question then was how to georeference these results, since aerial photos did not bear any geographical information. And in attempting our first georeferencing endeavor, we produced orthophotos that were positioned according to some known control points. And the result, I think, was rather good. Again, considering that the pictures taken more than a decade ago were not meant for photogrammetry. On testing the accuracy of these results, we have seen that systematic error across an area of roughly 90 meters, bounding box, let's say, is roughly not more than 1.5 to 2 centimeters. And yet, right now, we're trying to accomplish even better results, if possible, with the help of Taras Katsoulias of the Archaeometry Lab of Kalamata. We are attempting a positioning of the cloud points, namely the processing at an early stage, earlier than the orthophotos. In addition to nuancing the positioning accuracy, the final goal of this process would be exploiting the whole photogrammetric potential of these pictures by employing digital elevation models, as well as point clouds themselves onto the GIS. Their employment in this fashion does not solely allow for visualization, as in this case of the orthophotos, but also for calculation and analysis that you can know how they can be done with GTMs. And the reason why I started from the orthophotography is because it was mandatory somehow to integrate onto the GIS one other type of documentation, the site plans. Among the old documentation, in our experience, site top plans are some of the most challenging to be adapted to GIS. Originally, most of our plans were drawn by hand with pencil on tracing paper and then later polished and assembled onto AutoCAD. Although they were excellently manufactured and perfectly suitable for traditional printing standards, those drawings ended up being problematic when imported onto a GIS. And in this respect, we faced two major problems. The original site plan was drawn according to architectural criteria, and then focused more the focus on topographical positioning was lesser somehow than architectural detailing. And most of the architectural detailing was rendered according to graphical criteria rather than ontological. And this was perhaps really the main problem. Specifically, I mean that archaeological objects, such as pits, for instance, blocks and rock, etc., were not drawn as single and identifiable geometric figures like, for instance, polygons, but they were rather composed by clouds of small lines of various size, weight, and length. In other words, they have been digitized exactly like in the freehand drawing. So how did we solve these problems? In translating the site plan from the excavation rig onto the X87 reprojection, we combined two elements. One, the old photogrammetry that I showed earlier, that provided accurate references of excavation contexts that now are almost completely backfilled. And two, feature implemented recently on QGIS, we use this capability of georeferencing not only raster images, but also vectors. And that has been really a turning point. Thanks to more 300 control points, double-checked with differential GPS and total station, this tool revealed itself as unexpectedly accurate and yielded a precise georeferencing, really to the centimeters of the whole plan. There is still some work to be done in polishing the vectors and transform freehand drawing into more usable vectors, for which some time and, I have to say, quite a lot of elbow grease are necessary, but having all the plans properly positioned has paved the way to further implementation of GIS. For instance, it allows for structure phasing, of course, done by assigning the chronology to each and every object of the attribute table of the features. This phasing work is still ongoing as the study progresses, and this is our work in progress proposal. The next effort now is integrating not only structures, but also deposit into the system. And here you can see a sample. And to link the deposit forms with the finds catalog. This is how our working project looks like. It's still quite plain and fancy for the moment, I have to say, but the core of the work is at a quite advanced stage. And it's progressing along with the excavation material study, and we will fix somehow appearance and usability soon. We are now in the process of implementing communication protocols to connect QGIS with the online finds catalog and documentation database. And for this task, the Amicus Research Project is collaborating with Professor Fotios Kokotos and Professor Luis Carvalho of the Statistical Practice Department of the University of Boston, who have worked on a database structure suitable to accommodate our data. One more thing worth mentioning briefly is the georeferencing of the plans of previous excavation projects. Here we that of Zuntas, for instance, that of Fiske Furtwängler, and that of Bushore, just to provide these examples. And now these plans, so position, really they provide key information to the history and our study of the site. But as I mentioned before, GIS platform is now profitably employed as an essential tool for the current ongoing research at the Amiclion project. And in particular, it is now indispensable for the investigation of new plots around the core of the hill. And in these new areas, the GIS is helping to process those sets of new data that we are collecting there. And now I switch from presenting the integration of the old data with the current acquisition of the new ones. The use of differential GPS with RTK correction at a total station is now a standard procedure to provide x87 coordinates natively suitable for GIS. And also a drone with RTK correction has been implemented for aerial photography, which is now capable of providing imagery with accurate geographical information so that the photogrammetric model and orthomosaics of the investigated context bear positioning information out of the box. And integration then onto the GIS platform can be done pretty flawlessly. In season 2022 and 2023, these new plots around the sanctuary also received intense and extensive geophysical measurements carried out by the University of Münster. For the GIS, for this work, the GIS was essential, as you all can imagine, to collect, organize, display, and analyze the geophysical results. Here you can see some samples, so that then test and investigation trenches based on geophysics could have been really targeted with good, reliable precision.
5 more minutes.
Yes. Yes. Hello? Can you still hear me?
Yes, we can hear you.
Okay. Yeah. Thank you. sorry. And last, I wish to mention how GIS, like no other tool, is helping us now in contextualizing the site within its wider area, the Eurotas Valley, and in particular, and Laconia more in general. And for this, we would like to thank the Archaeometry Lab of the University of Kalamata, in particular, Dr. Vaya Panagiotiri and Tasos Katselias, who provided the Amitless Features project with really excellent remote sensing material, including very accurate and detailed photos of the sanctuary and its surroundings, as well as a digital terrain model out of a LiDAR scan. This material that now populates our GIS and the contribution in terms of knowledge and skills by the people of the Archaeometry Lab are now really indispensable to us for whatever work and research our team is carrying out. But in addition to remote sensing datasets, the use of GIS military maps, was enhanced significantly once these maps have been digitized and georeferenced on a GIS, not only because of the information they provide somehow directly, but a long and painful work of contour digitization can now yield images of the Eurotas Valley that were previously, I think, this is my previous experience, not even conceivable before. By the way, one may ask why we didn't use contours out of the remote sensing DEM, but this is what we've done as well. So to benefit from comparing topographical information from both sources. But GIS was also useful to contextualize the Amiclion within an even larger scale. And for Laconia, archaeological evidence is considered in both amount and significance, but the relevant data tend to be, for the most part, scattered, and they lack quite a bit in consistency. Assembling them, though, in a usable GIS fashion was not easy nor quick, but now that we have accomplished this task, these data can be organized, combined, and displayed in a way useful for the study of the site in its context. And here, for instance, we have an example of GIS-based viewshed analysis from the site. This image leads now to towards the end of this presentation, but before concluding, I would like to mention yet one more implementation of GIS in our research project. From this season 2024, we implemented QField, the mobile application of QGIS. And this app can run on both iOS and Android devices and bring a full GIS project on the palm of the archaeologist's hands working in the field. I'm not going now into too many details, but since its introduction in the fieldwork this year, the app proved itself as a really major update in the everyday documentation workflow. For instance, it allows for straightforward records of pictures, text, and positioning information from the field right onto the GIS platform. And this process was made even easier by then testing a post-GIS online database on which data were recorded right from the mobile onto the cloud. This way, data were centralized and synchronized among devices and computers on the fly, in real time and wirelessly. Not to consider that the app was connected with the differential GPS so that the RTK accuracy points were recorded directly from the GPS into the GIS project. And also it was possible to stake out points directly from the GIS project. So to conclude with this presentation, we didn't want to introduce really any particular novel employment of GIS for archaeological research. As you all could see, we have not done anything really more than every project, more or less like ours does, which is adapting a standard GIS application to the needs of a specific team and research context. But together with remembering Professor Zacharias and his contribution to our work, we wanted to share our experience with you, and we are open to whatever suggestion, comment, or discussion it may come from or be raised from our presentation. Thank you very much.
Thank you so much. As we're a little bit short in time, I will make a quick question for you, and then if we have more time at the end, we will have more questions. You have presented a GitHub repository. Is it an open access repository with data?
No, not at the moment, unfortunately. It's just a working tool for us now. For now, I hope it will. It will be because we're still working on it.
Okay, it's amazing to see the evolution of technology in so let's say little time, and it's amazing to share it with us. And thank you very much for that.
Thank you for the opportunity.
Now we continue with the second presentation. It's digital tools for enhanced management of archaeological excavation data. Mrs. Vaya Panagiotidis, please.
Hello, everyone, again. Speaking after Nicola is a little intimidating, but I will show you our work at the Pilos project. So today we will explore the ongoing development of the Pilos geoarchaeological program and take a look at our effort to bring some innovation to data collection and management. So over the last decade, the integration of digital tools such as mobile apps, GIS, 3D modeling, and cloud computing is reshaping the archaeological fieldwork. These tools offer real-time input, precision geospatial mapping, and instant collaboration of all of the partners that are taking place in the research. So either we're a field archaeologist or a geospatial analysis or a conservationist or any other aspect of geologist, we have a way of communicating through the documentation that each of us create. So digital platforms collect data, and they're gaining more and more ground in the field of anthropology and archaeology, but can continue to be long from dominating in the field. We try to incorporate these mobile apps and the GIS and 3D modeling, cloud computing, in order to create a streamline between the data collection to ensure accuracy and boost our collaboration. So which tools do we use in the field? Key digital tools available include geographic information systems, as we saw previously, storage options from local to cloud, of course, digital photography, as well as other means of site documentation, including photogrammetry and other methods that we'll see further along. Geolocation information is very important. It provides the information we need for further spatial analysis. And of course, we need the sketches and drawings that are an integral part of our archaeological documentation. What is the Pilos Geoarchaeological Program? It was an initiative of Professor Nicolaou Zacharias. The project began in 2021 and is a joint program of the Laboratory of Archaeometry of the University of the Peloponnese and the Ephorat of Antiquities of Messenia. Currently progressing through its final year, the 5-year program has, under the co-directorship of Dr. Evangelia Milici and Professor Zacharias, produced a large number of impressive findings while having covered during this extensive survey of over 8.3 square kilometers, incorporating both coastal and inland archaeological sites. Our goal was to apply the wide spectrum of technologies that the Laboratory of Archaeology has available in the whole survey and all the process that followed. This has led to the creation of a very challenging volume of diverse data. We are currently, during this phase, developing a holistic digital system that integrates data collection, geospatial mapping, and remote collaboration into a seamless platform. So what does the data look like? The data collected in the field work is highly diverse. It ranged from artifacts, contextual information, environmental data, survey data. And we're trying to create a digital documentation system that can incorporate it all and have it communicate with each other. So an integrated holistic system, lack of a better title, would have incorporated into it descriptions, dimensions, material type of what we find in the field. It would be incorporated into the system to reduce any risk that we have of manual error, because whoever has worked in a field survey knows that when we keep our notes written in notepads, that eventually when we try to digitize it, we have a lot of faults and a lot of things that are missing. So we're interested in topography, vegetation cover. We need to know what's going on in the area as a whole. So we continue and we produce aerial and terrestrial surveys. In the case of the PILOS program, we have a lot of photogrammetry, aerial, and LiDAR. So listening to all of this data, it is quite obvious that archaeological programs generate vast amount of data. It's data that goes across different formats, different data types, and that means that it's a very intimidating problem and it's a big challenge to organize, store, and analyze efficiently. So the one major thing that we're trying to resolve is how we can manage the data volume, how we can manage the variety, and how we can have it communicate between itself. We are attempting to confront these issues by centralizing data into one platform, which allows for easy access and management. The transition to The transition from traditional to digital documentation in archaeology has led to significant improvements in efficiency and accuracy. There are several pioneering projects that have embraced paperless data collection systems. One of the most characteristic projects, and probably the first, was the Pompeii Archaeological Research Project that actually named itself the Paperless Archaeological Project. And they followed a open source prototype. So all of the system that they created, the database system, is available to see how they've created it online. And of course, they've evolved very much over the past years, and it's been over a decade. And that's why whenever we see something new in digitization and digital tools and archaeology, it always comes from Pompeii. Other than that, we have significant work that's happened, that's realized in ancient Mycenae. They've adopted 3D scanning and a lot of high precision GPS documentation. And of course, the Amicleon project, which is a very bright example of how digitization and a unified system can work in an archaeological survey or excavation. The field data collection process for our project faces a number of challenges because we have multiple devices that without the proper synchronization can lead to lost data, inconsistent entries, and missed fields. So these issues generally arise due to lack of the interconnectivity, especially when we're in remote locations and we don't have internet access to be able to synchronize and communicate with each other. So to address these issues, our main point is to have the platform integrate all data collection to a centralized database. Of course, that means that we have to have a cloud-supported database to work with it. Key collection methods that we use is aerial and terrestrial survey. That means photogrammetry and drone mapping, aerial LiDAR survey. We use terrestrial laser scanning. And of course, all of these techniques produce very large data sets, whether they are point clouds or orthophotos or the large number of high resolution images that we acquire during capture. And these are the most challenging data sets to manage. So the YAP project is developing the cloud-based database that we said. We're trying to initially use all of the collected field data. That means artifact records, geospatial coordinates, and photographs. The first thing that we have solved is how to securely store them and how to manage these formats, which are easier to integrate into one system. And we're trying to design it in order to incorporate slowly all of the data. Of course, the large data sets from the point clouds and the aerial surveys are going to be the last ones that are going to be able to work with it. So the project has produced imaging archives that is over 20,000 aerial photos and 15,000 field photos. So that's an extensive documentation, and it is crucial for creating all of the 3D models that we use to be able to have analysis of excavation features in order to cross-reference images from the survey data or from the artifacts that we find. So as we mentioned, we're collecting data with different methods. We're trying to transition into a digital field data collection. Of course, at the beginning of our survey and at the beginning of our program, we used paper forms, and data entry was realized at the end of the day. This created a lot of problems in our formats. We had a lot of inconsistencies. Different users in the field were taking different notes, keeping different information. So that means that afterwards, when we come along and try to analyze the data, we can't compare it, and we can't do any analysis further than that. So the first thing that we did was try to create some fields that had specific answers, and they could only choose from those answers. So one of the latest issues that we have of our data collection format is to create a web-based database that actually has a user interface that is quite easy to use. The fields can contain only specific data types, so you can't put in characters in a field that only takes numbers, which was also a very serious problem that we had to face. So the difference in what we initially used was that, first of all, we had the fields that have specific data types. Okay, that was easy to solve. The second was that each form is, when we submit it, it directly goes to the connected database that we have. And when we have an internet connection, that can synchronize to the system that we've created. And of course, you can upload the photos that you take either with the tablet or your phone. And we've added a space for people to create their sketches, because one of our main issues that we don't have where to make the sketches while we're walking. But that also creates a new problem that we have to have devices that have a big enough screen for somebody to be able to make a sketch, because you can't sketch on a small phone. So one solution sometimes creates a new problem. So the result of only the first changes that we've made makes our platform a little bit more versatile. So we reduced the time that we need in order to have our data entry and synchronize the data that we have each day. So we have unified data sets. We have evolved our initial database, which was created in FileMaker, and we've migrated to an SQL base. That makes the digital storage that we have more accessible, and we can make better queries, and we can analyze our database in a more efficient way. So overall, we have integrated to the forms the offline and online functionality. So that means that our web-based data form can work on your device, either you're connected to the internet at that point or not. If you're not connected, it saves it locally and synchronizes once it has an internet connection. We can integrate our multimedia, that means the photos or the sketches. So the sketch that we make on our phone will be saved as a JPEG. And of course, we can have either local storage or cloud-based storage. Of course, for most of our data, it's still on a NAS secure disk because we have very large data sets. And we're trying to convert slowly to the cloud because, of course, that has an additional cost that is not very easy to always have an accountability for. So another important factor is that we have scalability, and that means that we can change any factors that we need, and it's easy to access and easy to edit. Up until now, it has led to significant improvements in the efficiency and reduced the manual data entry that we have, the transcription time. It allows us more time to focus on the analysis and the decision-making for the next days or for the next season. The offline capability has ensured that no data is lost during remote field work. We can sync our data when we have an internet connection. And of course, we have a lot of hopes for the future. We're hoping to incorporate a full cloud-based processing capabilities. We want to enable real-time data analysis and automated processing, but that of course will create more problems that have to do with financing and having sophisticated equipment in the field. And as we move forward with the development of the documentation platform, we envision on creating a centralized, secure, and scalable solution in order to manage all of the different archaeological data. And that doesn't mean only the data from the survey and from the days that we're at the excavation, but also the data that's gonna be created afterwards, which either conservation or an archaeometric analysis or anything else that is created in the field of all of the important factors that we need to take into consideration. So one of the most important decisions that we have to make is to choose the right platform in order to meet all of these needs. We're evaluating our options. Hopefully we can find sufficient options that will have a low cost because the budgets are very difficult. And the ultimate goal is to have a total overall system that can support the needs of today's research, but also could be flexible enough to evolve for our future endeavors. So this is a very short presentation of where we are now, and hopefully will be the beginning of a much more sophisticated platform and system. So
thank you so much. We have some time for questions, if there are any questions from the audience. Okay, pretty sure it was pretty clear what was mentioned. I have to mention, though, a very personal comment. It's really amazing how, and I admire that in this team that was built around Nikos, how amazing it was, the smooth way he was able to combine humanities with the digital technologies. Having only technology background, I have just technological background. I really struggled the last 10 years to convince people from humanities to have access and use technology in a more freely way, but it's almost impossible most of the time. So thank you so much for this innovation. The next presentation is entitled 3D Geospatial Platform and Virtual Tour Application to Visualize Stable Isotopic Analysis Data. It's online.
Hello? Can you hear me?
Hear you. We are trying to see you. Okay.
Hello?
Hello, Mrs. Kyriakoulou.
Good evening, everyone. I'm talking from Athens. I couldn't be here, although I wanted. Just a minute to share my screen.
Okay, we're waiting.
Could I just share the screen? This is because I want to demonstrate the application as well, and I need to share the screen and not yeah. Can you see the PowerPoint? It's fine because I can't really see what you say. So
we can see the application of the PowerPoint, not the presentation.
Okay. Okay now?
Okay, we're good now. Thank you.
Right. Well, the first part of the presentation, and I would like to ask you to stop me 7 minutes before the end, because the presentation is separated on the making of the geospatial platform and virtual tour application. And I would like to demonstrate these two applications in the end, after making clear of what they're all about. I'm very glad to hear the previous presentation because there's a lot of things in common, and all the systems that are previously mentioned by Dr. Panagiotis, they are all pretty much developed here. We have the database, so it was very happy to talking after her. Here I'm going to talk about the Palimpsesto project. This was a 3-year project. It was a cooperation of the ITI department. This is the Center for Research and Technology, Hellas. These are the software engineers of the team that actually developed the platform. The National Center of Scientific Research, where I belong, we actually implemented the technological part and of the project and the archaeological research and the archaeometric actually research. It's the University of Thessaly that they were responsible for the archaeological part from the excavation. And the other partners, it's a small private company, it's Omega Technology, that actually developed the virtual tour application. This project was funded by the European Union. Almost 1 million was spent on this project, and it was on the call Research, Create, Innovate. The research team, you said previously that all these projects need a cooperation. So, okay, this is a cooperation. The National Center of Scientific Research, we were the conservation scientists, the Information Technology Institute, these were the software engineers and architects that they were specialized in imaging softwares. We were all work together. I am also quite familiar with many technologies, and of course the Department of History and Archaeology, that they were actually responsible for the archaeological part of the research. To start with, between many other deliverables that that the Palimpsestor project had, the main aim was the development of virtual reality tools that they actually aim to make accessible all the results of the archaeological research and the research and the archaeometric research to the public, to the audience that will be specialized and non-specialized. So the aim was the access of the results. And this involved development of an innovative, non-destructive, portable device for surface degradation control and a novel degradation tool, 3D documentation of the archaeological area and selected archaeological findings, extensive archaeological and archaeometric investigation of Kythnos archaeological site, and of course, virtual tool in space and time, and application storytelling, artificial intelligence. A few words about our site. The selected archaeological site is actually Kythnos Island, an island with a long history and particular archaeological importance is Kythnos, which is situated between Kea and Seriphos. The ancient city of Briokastro on the island's northwest shore was a fortified polis that was continually inhabited from the first millennium before Christ to the 6th or 7th century after death. The remains of the ancient city occupy an area of approximately 28.5 hectares, including the small islet of Riokastraki, which was connected to the shore in antiquity by a narrow isthmus. During the systematic investigations that have been in progress since 1990, numerous finds and several ancient structures, such as temples, public buildings, port facilities, burial monuments, have been brought to light. These discoveries have provided valuable insights into the urban planning of the city and the socio-political and economic development of the ancient community. These are the sites, actually. They were all dated at from Hellenistic to late classical period, although a little bit later or a little bit earlier, some findings were dated at in this time. A large collection of findings, including stones, slates, mortar, marbles, glass, and bones derived from humans and animals. These are actually the samples that we studied. The analytical techniques used to study the archaeological material and answer questions concerning their technological characteristics, degradation features, and become a basis for a future conservation plan. We actually use stable isotopes. This is our lab, stable isotope unit, carbon-13 oxygen-18, ICM, optical microscopy. Now I'm going to present only a few slides on archaeometric results. They are all published in Scopus in text journals, just some highlights of what we found, and then we will go through to the making of the platforms. At first, we wanted to answer some questions about the figurines and where actually the marble came from. The results are plotted in reference diagram, carbon-13 against oxygen-18, We actually compare Kithno samples from samples of known composition and known ancient quarries from Cyclades. The examination of the samples and their placement in both diagrams, we actually show that the marble comes from and the quarry was possibly located in Kithno, so they are from there. Having an idea about where the marbles came from, then we try to find out where the glass fragments came from and which is the glass composition. All glass could be classified as natron glass made from a mixture of silica sand and natron. The samples of ancient glass objects were selected and characterized with ages ranging from the origin of the first millennium before Christ. From all the data, it appears that the chemical analysis of almost all the samples are quite homogeneous, and the major elemental compositions of all samples are consistent with typical natron glasses produced between the 8th and 4th century before Christ. The levels of potassium oxide and magnesium oxides show that almost all the glasses samples analyzed, regardless of the typology and site of provenance, were produced starting from a sodic inorganic source of alkalis, ascorphine, by the high levels of soda that found in chemical analysis. In fact, the glasses show potassium oxide and magnesium oxide contents below 1.5 and high levels of soda between 17 and 20, confirming that the analyzed glass samples were made of a soda-limb silicate basis and produced using mineral natron as a source of alkaline fluids. Following the analysis of glass fragments and marbles, we tried to reconstruct the diet of the ancient people in Kithnos. And these are all added in the platform, all the information. With just a 5-gram sample, a comprehensive range of isotopic analysis can be performed, including carbon-13, nitrogen-15 mainly, providing detailed information about an individual's origin, immigration history, and nutritional profile. Researchers developed a methodology that distinguishes between different photosynthetic pathways used by plants. These pathways result in different isotopic signatures. The diagram demonstrates the results of isotopic analysis of samples from Kithnos and then compares them from various samples of human bones in Greece. Arrows in the diagram indicate ranges of values occurring in flora and fauna samples worldwide. Compared to the literature data, the values of Kithnos are more positive in both nitrogen and carbon, showing that their diet, while based mainly on terrestrial plants and animals, also contained a small percentage of marine protein. Also, the enriched isotopic values suggest a greater exploitation of the marine ecosystem for nutrition during the classical period. Having a good idea of the diet of ancient people in Kithnos, then we tried actually here to visualize and digitize degradation. And here is the ITI department had an idea and actually developed an innovative, non-destructive portable device that is able to track the penetration of degradation using waves. And this was a very, it's a very good and effective tool to visualize degradation, and degradation caused by rainfall. And a patent was developed for this. And we also allocated sensors to track rainfall and combined all the information together and added them all in the platforms. The context of the 3D imaging is we actually had an Earth-based laser scanner, also digitization into 2D geospatial data, coordinates, and all the others, things that are necessary. Digitization of selected findings using photogrammetry techniques. Within the process of scanning, there are many difficulties that occur in Briocastro. That's a very large area, and usually the scanner has to overcome the differences in heights. And very strong winds was also very difficult for the people to have obtain effective scanning. Although besides all the differences, with the scanning process, here is the scanner, the laser scanner, some technical characteristics for the people who actually use these types of scanners, the time scale, the time scanning, the recorded speed, the range. And this is how the Earth-based scanner was installed in situ. We had sent this reference ball, and we moved all the scanner and the balls one in the next position, one position after the next position, and in that way we obtained 85 georeference scans. Here I'm demonstrating some of the softwares that they used in all stages. SQL, GIS, they were all used in all the stages from when the image was obtained from the scanner until the end, which is the geospatial database. Databases, and GIS, and SQL, and security, all the information is here. So the first scan was obtained, again, a single scan point cloud, after imaging processing, was converted in a 3D model. These are some of the 3D models that developed and added later on the geospatial platform that combines all the information. And the other buildings. And then we go to the 2D geospatial data. The digitization of 2D geospatial data is very important because it includes all the coordinates and the various attributes. Also, here we use an open source code tool. This is the name, as you can see. So the 2D digitization combines the coordinates of the archaeological sites with the coordinates of the sensors and the devices to track degradation, so they can all incorporate together the coordinates of the sensor, the 3D models, and the final input is the geospatial database.
You have 7 more minutes.
7, okay. Thank you. I need to run through more quickly the slides. This is 2D. And finally, this again to see how the commands. And here's the digitization of the objects. Here we use photogrammetry and a DSLR camera on a stable tripod. And in that way, we visualized and produced, of course, again, imaging software always. We visualized the objects. A few words about the degradation tool. The degradation simulation implemented using a 3D environment through the Unity graphics engine. A system particle was produced that subjects the physical forces to simulate water-induced degradation. Bombarding the 3D model with particles. These particles are actually 3D spheres, which are subject to physical forces such as gravity and friction. And these particles roll in the 3D model due to gravity and physical forces following the 3D topology of the archaeological structure. That's the end of the presentation, and now, hopefully, I will be demonstrating the platforms. I had made a check yesterday, so I hope it works. This is the geospatial platform. This is all in Greek, but I will be translating. One of the main aim of the project is to be bilingual, 2 languages. We can hear some information about the space and some tools here on the right. The Facebook tool, how is the application on Facebook, Twitter. It is loading. The user here actually drives the mouse and drives the application whenever he or she wants. In this database, you will see all the information, degradation, history, sensors, position of sensors, information about rainfall in Kythnos, and archaeometric results. Here are the name of the building. So the iconic user here selects one, and then you can see the borders of the building, and then you can see some information. Here is the data. You can see the building, the name, the location, the chronology, the materials, the 3D images. And here we can see the degradation model. Actually, what I talked a little bit previously, the degradation model uses various particles that represent degradation particles and water flow, which is one of the main causes of degradation of archaeological monuments. These particles are subject to realistic physical forces, and they actually act as real 3D objects. The contact of the particles with the three-dimensional archaeological structures, as it here, you can see here, causes signs of corrosion. Corrosion particles acting as droplets following the 3D geometry of the space, such as existing pits and folds, and tend to be more concentrated at these points. Here we can see here, it is in Greek, its size, which is the level of degradation. The red color is for the very high, the current state, the low. So by clicking on it, you can see how far the degradation penetrated in the material, and the rest of the information again. This is pretty much how it goes, and this is the contact for every building. Another important tool that I would like to show is the potential that the application gives to ask questions. We have installed, I'm going forward, because we haven't, I need to show another more application. So this is how we ask questions. This is the user will ask, what are the materials? What is the technology? Ecological information. You can ask a question. You can also ask conservation questions. How this marble will be restored, or which is the isotopic data for more specialized audience. All the information is there and accessible for any level of audience. So I'm going to stop the application now, and I'm going to show you the virtual tour application. This was the Geospatial platform. The virtual tour application encompasses narration. The narration is in Greek, but it actually says the same thing, describes.
With a lot of data, we are losing totally the voice,
Okay.
despite the fact that we have thing, if it's
Now?
loading a lot, we'll lose your voice. Now it's okay.
Okay, I don't now that maybe because we are no, that's not, sorry. This is the platform. How much time do I have? And this is the visual tour application. Can you hear me now?
Yes.
Okay. How much time do I have?
Almost 2 minutes.
Okay, that's enough. And here we select which building. And this virtual tour application is also available with a VR device, which is very, very interesting. It looks like and feeling like being in Kythnos, whereas you are in Athens or everyone else. For this presentation, I will use the mouse. I wish I could demonstrate the VR. It's very impressive. And you can see the voice here. So it actually describes the building and the information. You can also at this point see the images that include more information. These are the images, so people can look at the building while being in there when using the special DVR, and then at the same time you can see images of what exactly is what you are seeing at the moment. And these are the results of archaeometric analysis. And going forward.
Now we really have a problem with the sound. We can barely hear you.
You can't hear the sound?
We can't hear you clearly because it seems like it's loading a lot of data from the applications.
Okay, can you see the pictures?
Yes, we can see everything.
Okay, I will just show you the pictures and some of the results of isotopic analysis that were important in here. Yeah, you can see here. So while watching the video, at the same time, you can click on this tab and see pictures and more information on the side. The problem with the voice does not allow me at the moment to show more information on that, but that was pretty much what I wanted to say. So thank you very much. That's the end of my presentation.
Thank you so much for the presentation. The results from your project look really amazing. It's a very nice project. Actually, we are following this project to see the results already.
Okay.
Okay, we will go on with the next presentation. If there are any questions, we will come back at the end of the session because we are also late. The next presentation is about data fusion as a tool for the characterization of degradation layers on monuments using multi-analytical techniques. Dimitris, please, floor is yours.
I'm ready to go. Okay. Good evening, everyone. I can only hope to keep you interested after the previous presentation. The motivation for this study is particularly driven by a growing interest in the scientific community worldwide for this field. The high pollution levels and number of monuments in Greece, and the significant lack of similar studies in our country. Additionally, the materials are often inhomogeneous when we talk about degradation materials of buildings. So it makes it challenging, really challenging to analyze them without robust automating processes, which we aim to develop. The primary aim is to characterize the degradation layers found on historical monuments, particularly focusing on the elements that contribute to their formation. A key part of this study is identifying pollution sources, which is critical, especially in urban areas like Athens, where air pollution is a significant factor for degradation. We're combining elemental and molecular data from different analytical techniques to create a more integrated picture of the materials and their degradation processes. This multi-dimensional approach to data fusion warrants an automated process which not only saves time, but also allows for an increased comprehension of the results and very important, repeatability of the analysis. The methodology is designed to handle and process this multidimensional data in an efficient and automated manner. After performing Raman and micro-XRF measurements, the process starts with the user inputting objective basic parameters into a data frame that we create. Then advanced statistical analyses, such as PCA, are performed, intermediate results and visualizations. This whole process is done in steps. Once the data is imported in the initial data frame, which we will see in the next slide, the script runs initial analysis and then adjusts the parameter weights to account for a more accurate analysis. The results are then visualized for a final interpretation. These work, so it allows us to combine statistical analysis with the machine learning to streamline the entire process. The research takes place at significant historical sites in Athens, the temple of Hephaestus in the Roman Agora in the center of Athens, which is the most well-preserved classical era monument, and the 11th century Byzantine church of Agi Theodori, also located in the center of Athens. They're part of a broader project that aims to include monuments with diverse atmospheric backgrounds, such as the Tholos of Athina Pronea in the rural area of Delphi, the archaeological site of Elefsina, which is located in close proximity to a heavily polluted industrial zone, the Byzantine church of Agios Charalambos in the suburban area of Kalamata, and finally, the burial grounds of Ellinikon, which, interestingly enough, in terms of their atmospheric background, are in close proximity to both the coastal areas. They are in a coastal area, and they're in close proximity to the old Ellinikon International Airport. In total, for each monument, 6 samples were collected at various heights and orientations. And in addition to these samples, 16 measurements, 16 in situ Raman measurements were conducted across all orientations. The combination of sample variety and measurement techniques ensures that we gather a broad set of data, allowing us to assess how different factors like orientation and height could affect degradation patterns. An important part of the methodology is the creation of the user input data frame, which looks like this, like what you see right now on the screen, which serves as the starting point of the data analysis process. The user can use as inputs essential objective information about the samples, such as the orientation, height, and chronology, as well as a subjective parameter, which is the state of preservation. You can look at them there, the titles of the columns in this particular table. The user can also input a subjective parameter of the state of preservation through, according to his or her macroscopical observation, for later comparison with the actual calculated results. All data are converted to numerical values, such as, for example, integer values, and they are then normalized to be taken into consideration when conducting analysis and to minimize bias. With exclusion of the subjective parameter, all data are then combined with outputs from both the Raman and micro-XRF analysis, creating a comprehensive database that forms the backbone of the statistical analysis that follow. In this figure, you can see the initial Raman spectrum derived from the portable instrumentation used. In the data analysis process, a peak detection algorithm was applied to the Raman raw data. After visualizing the spectra and inspecting the peaks, which were identified with this algorithm, and confirming the accuracy and precision of the peak detection process, specific molecular bond bands were assigned to the detected peaks with 147 manually and in context assigned peaks so far, which are then used for further analysis. By calculating the top contributing peaks, we can identify key markers that differentiate the degradation layers across samples. Values are also converted to binary for ease of comparison and to perform clustering, which allows us to pinpoint the specific molecular structures present in the degradation layers. After the Raman data set is processed, the bonds are assigned based on predefined parameters, such as the coexistence of specific peaks in one spectrum, which translates into a specific molecular structure, like a newly formed mineral, for example. And the goal was to identify which molecular bonds and as follows molecular structures are most prevalent in the samples and how they relate to the pollution sources or specific degradation mechanisms. This helps in forming clusters of samples with similar features, determining the most affected areas of the monument, and understanding the chemical processes occurring within the degradation layers, and also to infer the specific pollution sources. Continuing with the micro-XRF data analysis, line scan measurements were performed across the sample's profiles, sample cross-sections profiles, to assess the elemental composition of the samples. And as you can see in this example from the Temple of Ephesus, by calculating the means of the detected elements, we can quantify the distribution of elements in each sample. Pearson's correlation helps us to identify how different elements relate to each other within the degradation layers and how their distribution relates. And clustering is performed to group these samples based on these relationships. By calculating the top features contributing to each cluster, we identify which elements are most influential in defining the groups. Visualizing the results helps us understand the distribution of elements within the samples and how they correlate with the molecular information obtained from the previous step of the workflow, the Raman analysis. As you can see, in an example, a table is created along with information, As you can see, a table is created along with the Pearson's correlation matrix, which includes key outputs to use in the next step of data analysis. As for example, the mean values of key elements to understand the sample's gypsum content, for example, or trace element ratios, especially for heavy metals and transition metals that are identifiers for specific pollution sources as nuclei for the starting of the degradation process or for driving the degradation process to be faster. After completing the previous steps, the results are compiled for all samples with Raman data analysis to include the user input parameters. Each sample's degradation profile is created, showing its molecular composition. And we then use these profiles to identify patterns or trends like pollution sources, orientation, chronology, or height. We can correlate the calculated top contributing parameters in this way. This approach allows us to have a clearer picture of the degradation mechanisms that affect the monument. In a second analysis, the focus is on samples that were analyzed using both Raman and micro-XRF measurements. Unfortunately, we didn't have the opportunity to have 16 samples from its monument due to restrictions. So we had a smaller data set for this one, a smaller number of samples. The combination of these two analytical approaches gives us a more comprehensive understanding of the degradation layers, as we can now cross-reference the molecular and elemental data and include all the parameters from the user input data frame as it was created in the initial steps of the process. So this into account everything that is now put and normalized and scaled in the initial data frame. This cross-analysis is crucial for confirming that the clusters formed in the previous steps or in each step are consistent across all types of data or different types of this might influence the molecular structure of the degradation layers. In conclusion, the study revealed varying types of black crusts, which are a type of degradation layer formed on the surface. Macroscopic observation for the of the user's input value for the state observation. The pollution sources vary, with domestic heating and vehicle emissions being dominant for the Byzantine Church of Agioi Theodori, while the Temple of Ephesus shows more influence from industrial emissions and biological activity, or the use of pesticides and fertilizers, because it's in close proximity to plants around the monument within the urban environment, when compared to Agioi Theodori. The clusters created from both Raman and micro-XRF datasets show strong correlations with the sample's orientations, confirming that environmental factors like orientation have a significant and distinct effect in the visible type of degradation. Overall, the combination of advanced statistical analysis, machine learning, and data visualization tools has provided a more integrated and insightful investigation through data fusion. It is important to emphasize here that automating the procedure has greatly reduced the time and effort required for repeat runs of the whole process. So each time we fed the script with a different different files, different CSV files, different data sets, it needed even less and less adjustments from our part for the code. And I would like to also mention some challenges and some future work and some hopes. Looking forward, the main challenges faced are the high inhomogeneity of the samples and the need for the user to manually adjust certain parameters during the analysis, however simple they might be. Additionally, the lack of data from different atmospheric backgrounds limits our ability to compare results for more diversity. The ongoing and future work includes or will include increasing the number of samples, the inclusion of environmental data, which is critical for comparison, and further improving the peak assignment algorithm. Developing a graphical user interface, GUI, is crucial for easier handling and automation of the whole process. And this will ultimately and hopefully make the analysis more accessible and efficient for future studies. Thank you very much.
Thank you very much for this presentation. If we have any questions on that. Okay, unfortunately, it's not possible for me to comment on that because I'm really impressed by the progress that Dimitris has made as I'm supervising this this PhD, and he's really doing great. And thank you for that.
Thank you.
Okay. We are going to the last presentation of this session. Advances in the study of Upper Paleolithic engravings with the use of confocal microscopy and the 3D profiler. Mr. Let me try it. Robitaille. Yeah, thank you.
Okay. Okay. Hello, everyone. It is an honor to participate in this conference in the memory of Professor Zacharias. Today, I will discuss the use of confocal microscopy and profilometry in analyzing engraved plaquettes from the Magdalenian site of Gonensdorf in Germany through manual and robotic experimentation. This presentation explores how this technology, which are becoming increasingly popular and accessible, are crucial for understanding artistic engravings on stone plaquettes at a 15,800 years old aggregation site. We will examine how the application of these technologies has enhanced our understanding on the engraving life cycles of the engraving life cycle, the reuse of the plaquettes, the artist laterality, and new interpretation regarding the orientation of engravings on schist plaquettes. The Gonensdorf plaquettes are 15,800 years old schist slab featuring Upper Paleolithic engraving of various pre-animal and human figures, often interpreted as female form. Engraving on portable materials have a long tradition in Upper Paleolithic Western Europe. This engraving holds a wealth of information that can give us insight into the artistic and technical decisions made in the past. Even the apparent simplicity of these engravings contain a variety of technical details. The form and structure of an engraving depend on the tool used, the engraver's gesture, and their technical expertise, as well as the collective imagination of the cultural group. In Gonensdorf, several geographically distant groups likely contribute to this artistic tradition throughout the year, as the flint found at the site come from many different and distant areas. However, user analysis and striation patterns on engraved objects have been understudied, which leave gaps in our understanding of their creation. We aim to address this gap by studying the engraver's laterality. The first robotic experimentation, alongside additional manual experiment, shed light on the way the artist engraved the Gonensdorf plaquette. This experimentation and the use of new technology in quantification in 3D of very small surfaces enabled us to obtain information on the succession of the engravings, the extent of reuse of the plaquette, the artist laterality, and whether different artists engrave on the same plaquette. First, though, a few words about the site of Gonensdorf. Gonensdorf is perhaps the best example of the late Upper Paleolithic Magdalenian of the central Rhineland, Germany. It is located on the banks of the Rhine River at the point where the path of the river changed from an open landscape into a narrow Rhine gorge. The site was protected from erosion by the thick layer of late glacial tephra from the nearby Lasser Sea volcano, and was therefore extraordinarily well preserved. Here we see the excavation from the 70s and the plan of the site with the spread of schist plaquettes. We can see note that how numerous and important the plaquettes were at the site. They were used as a work surface, hearths, construction, and other use, but are mostly known for the image engraved upon them. Okay. Over 427 engraved plaquettes have been recovered from Gonensdorf, all featuring engraved animals and humans, and are part of the study. As we see in this graph, human figure, horses, mammoth were the most commonly depicted. Most plaquettes, about 88% of them, are smaller than 30 centimeters in diameter, an optimal size for manipulation and engraving. The manual experimentation was conducted conducted to better understand the technical aspect of engraving on schist plaquette. By replicating the engraving process, we were able to analyze the impact of various factors on the final product. This table outlines key aspects of manual engravings, focusing on functional constraints and parameters controlled by the engraver. The red box defines task constraints tied to the material properties. The blue window details parameters under the engraver's control, which may be influenced by the rough mechanical characteristic. The strategy box covers engraving approaches, and movement parameters highlight the engraver's spatial positioning. Finally, the diagnostic characteristics box compares experimental results with archaeological evidence using various microscopes and profilometer. To better understand the engravings, we needed to distinguish between natural and unintentional traces and those produced through deliberate technical action. After identifying the different techniques used, we classified the variability of indices that correspond to certain behaviors during the engraving process. Our goal here was to reconstruct the engraver's gesture to understand the sequence of the engravings, to classify the orientation and sense in which the engraver were engraved, shedding light in the sequence of superimposed line and the engraver's laterality. Here's an example of our experiment, a part of the experiment, where we studied the manipulation of the plaquette and the type of tool used for engraving. The result on the traceological analysis on the surface and edge of the plaquette were compared to those from a series of handling and manipulation experiments. The use-wear analysis on the flint showed similar characteristics to those found in the study by Sano in 2012 on the selection of flint tools from the Goneznov collection. Our analysis shows that blades and burins were primarily used to create engravings. Additionally, our experiment revealed that some plaquettes were extensively used or handled, while others bearing limited engravings receive only modest use. One of the distinctive features of schist plaquettes is that they can be easily engraved due to their hardness, which range from 2.5 to 4 on the Mohs scale. Flint, with an hardness of 7, approximately, can easily scratch the surface of the schist. To understand the force required for engraving this plaquette, we conducted controlled robotic experiments. Although this is still at an early stage, initial results provide insight into the pressure exerted on the tools and the morphometry of the grooves create, helping us to identify the sequence in which lines were engraved. To investigate laterality, we use a robotic experiment to examine whether the angle of contact between the tool tips and the plaquette could be observed in the engraved line cross-section. We engraved several semicircular lines using different tools angles, ranging from 7.5 to 30 degrees. To investigate the engraving process and morphometry, we implemented cutting-edge technology, including confocal microscopy and profilometry. These techniques were selected for their ability to provide precise and quantifiable measurements, which are crucial in the detailed analysis of fine engravings that are too small to be effectively studied using stereoscope or standard digital microscope. We utilized confocal microscope, a laser microscope equipped with a high magnification objective ranging from 50 to 500 alongside a profilometer. This combination allowed us to achieve highly accurate measurements, particularly using a 3D microtopography, useful for 3D topography. Confocal microscopy, which uses focused laser light, can capture very high resolution, deep resolve image was essential for obtaining the detailed 3D imaging at a macroscopic scale. In parallel, the high-resolution 3D scanning capability of a profilometer provides a complementary approach. With a larger field of view and lower magnification, the profilometer enabled us to document and quantify larger surface area with precision. We specifically use the SensoFar S-Wide for fast, large 3D surface measurement, leveling white light interferometry. This advanced technology offered a significant advantage over traditional methods such as conventional microscope, stereoscope, or digital microscope, where analysis remain qualitative. Here, the detailed 3D data is quantifiable, providing a more accurate analysis. Following data acquisition, the measurements were processed and analyzed using ConfoMap, Mountain software. This software allowed us to conduct detailed analysis of 2D profile and 3D topographies, this program is commonly used to study surface geometry, roughness, and wear on materials. The 3D model produced through confocal microscopy and profilometry allowed us to measure the depth, the width, the angle of engraved line, as well as their cross-section. We could even determine whether a second tool was used within the existing groove, which helped us to reconstruct the sequence of engravings. This slide shows also an example of a repeated groove created by multiple tool passes. Here are some calculations that can be done with the 3D model. We can calculate all the angles, the bisector angle, the length, the depth of the engraved line, which are indicative of the type of tool used, the engraver's laterality, and the sequence of the engravings. Robotic experiment on the tool's angle in contact with the plaquette revealed that a more close angle of the tool tips result in a more close angle of the engraved line. This pattern is also applied to the bisector angles. Through manual experimentation, I observed that the straight line were engraved with less open or more closed angles, with the bisector angles just shy of 90 degrees. When engraving a curved line, all angles, in this case S1, S2, and the bisector angle slope toward the artist's dominant arm, strongly indicating laterality. So, with the help of the experimentation and the use of different levels of microscopical observation, the investigation of certain characteristics, such as the location of the engraving on the plaquette, the succession of the engravings, the tool used for engravings, the repetitive engravings, the artist's laterality, the trace of manipulation, the evidence of fragmentation, make it possible for us to reconstruct the plaquette life cycle and individuality. Regarding the female figures, we were able to revisit and rethink assumptions made in the early 90s. At the time, it was believed that a figure facing right was created by a right-handed person, while a figure facing left was made by a left-handed artist. There's a couple of more figure representation. Okay, in total, 395 female figures were engraved across 175 different plaquettes. The number of figures per plaquette varies ranging from 1 to 22. However, the 87% of the plaquette include between 1 and 3 figures. 11% have between 4 and 7 figures, and only 1% feature between 7 and 22 figures. Out of the 395 figures, we identified 125, meaning that 32% were facing left, while 270, 68% were facing right. For this study, we faced some limitation on the number of plaquettes we could study due to the conservation issue, completeness of the figurine, on the figure on the plaquette, and the size of the plaquette, which sometimes were too big to put under a microscope. In summary, we were able to analyze a total of 121 figures, most of which appear on the plaquette containing 1 and 3 figures. Of the 121 engraving we studied, 80 were facing right, 24 were facing left, and 17 plaquettes featured figures facing each other. I measured 3 locations on the top line and 5 on the bottom. At each location, I took 5 measurements space of 300 microns apart, and then calculate the means for each. For each location, 6 different angles and length were measured, and as it shows in the figure here. The result aligned with both manual and robotic experiment, which compare straight and curved line. They show that the angle change in relation to the tool position. In this case, the tip of the flint, demonstrating that laterality is perceptible in the engraving. Our analysis indicates that laterality is not necessarily linked to the orientation of the figures. For instance, 58% of the left-facing figure were created by right-handed artists. And similarly, 4% of the right-facing figure were engraved by left-handed individual. Additionally, every pair of facing figure was consistently made by the same artist, whether left or right-handed. Overall, we found that 86% of the engraving were made by right-handed individual, while the remaining 14% were attributed to left-handed artists. Our understanding of laterality would not have been possible without the manual and robotic experimentation, as well as the quantification of the user analysis result by using confocal microscopy and 3D profilometer. Thank you.
Thank you so much. Do we have any questions on this presentation? I have one.
Okay.
I was wondering, you tried different angles in order to engrave the plaquettes. Do your research revealed as well that this was related to some kind of technique on engraving?
Yeah, but yes, it's when you engrave, actually, it's automatic that when you, I did experimentation with a different person also. When you engrave a straight line with the flint, first we have to see that to engrave a figure, it takes a couple of seconds, take a second or two. Huh? You go a line like this and you go like this. And they usually go like straight line, and then to make the curve, they bend a bit their hands and they go like this. And it's the same when you do the opposite. You're going to do a curve, and they bend also the tools, but they're going to do the opposite direction of the. Yeah.
It's really nice, really nice. Thank you so much.
Okay.
Okay. So this session has finished and was the last of the day. So everybody can take a rest, and we will meet tomorrow morning.